tension, normal reaction, weight, and friction. Okay, now let's start with this. First of all, what are forces? Force is a vector quantity. Vector quantity is something that has both magnitude and direction. So whenever we describe a force, it needs to have both magnitude and direction. Unit for force is Newton. Now, first of all, let's consider this example. Let's say we have a block like this. If we have a force acting towards right side, that's 8 Newton, towards left side, that's 5 Newton. And we have to find the resultant of this. That's fairly straightforward because both of them are acting parallel to each other. We can just subtract the two. We can say 8 minus 5, that's the resultant for that's 3 Newton. If it's vertical in this case as well, it's pretty straightforward. You just do 21 minus 15, and that gives you 6 Newton in the upwards direction. That's the resultant force that we've got. However, when you have forces acting in different directions, for example, if you have one force acting in the horizontal direction like this, 8 Newton, one force acting in the vertical direction like this, how do you find the resultant of a set of forces that looks like this? Now, for this, when you have forces acting perpendicular to each other, what you can do is you can make a right angle triangle, use the head to tail rule, and you say, okay, if this is the base, this is the perpendicular, then this hypotenuse is going to be the resultant force. You can find the magnitude of that resultant using Pythagoras, and that turns out to be 10 Newton in this case. But now, since force is a vector quantity, we also need direction for that. Direction means at what angle is the force acting? How do you find that direction? You can use tan for that. In this case, you can say perpendicular over the base 6/8. That should equal tan of this theta. And that will give you the angle. The angle turns out to be 36.9 degrees. So then you say the resultant force here, it's acting at an angle of 36.9 degrees above the positive x-axis, and its magnitude is 10 Newton. So whenever you write down a force, unless they specifically ask you just for the magnitude, you should also tell the direction in which it is acting, right? In this case, when you have resultant force, you will say it's 10 Newton acting at an angle of 36.9 degrees above the positive x-axis. Now, how do you describe this? How do you do this description like this? So there are four possibilities. You could have forces acting in these four different directions, as in the first quadrant, in the second quadrant, in the third quadrant, or in the fourth quadrant, right? You'll have forces acting in one of these directions. How would you describe each of them? You need to know this. For example, if you have a force acting here, 35 degrees, how would you describe this force? You look at the starting point of the force. The starting point of the force is this. We consider that the origin. Starting point is considered the origin. From that, you say, this is the positive x-axis and the left side is the negative x-axis. So when you describe, you would either say it's above the positive x-axis or below the positive x-axis. For example, this 35 degrees, you would say it's 35 degrees above positive x-axis. If you had force acting in this direction, 40 degrees, if that's 40 degrees, that means that this angle is 50 degrees. So description of this force, the green one, that would be that it's acting 50 degrees above the negative x-axis. The left side is considered negative x-axis. Similarly, if you had this force acting in this direction, you would say it's 30 degrees below the negative x-axis. And this, you can say, this angle, since that is 80 degrees, this is 80 degrees below the positive x-axis. So that's how you would describe forces acting in these different directions. You say what you write down what the angle is, and then you write down whether it's above or below positive or negative x-axis. Okay, that's the description that I would recommend. You can also use anti-clockwise, clockwise, but some people end up getting confused with that. This is a very easy description. Angle, positive, negative, and above or below x-axis. Okay. Now, we talked about how to find resultant of two forces that are acting at right angle to each other. We can just make a right angle triangle from that and find the hypotenuse. However, what if we have forces acting in some random directions like this? How do you find the resultant of this set of forces? Now, for this, we need to do something that we call resolving forces. Since we know how to find resultant of forces that are perpendicular to each other, what we try to do is we convert these forces in a form such that the forces are only horizontal and vertical. Now, since it's a vector quantity, the force is a vector quantity. We can say this 40 Newton force, that's the same thing as saying that you go this much in the horizontal direction and this much in the vertical direction. So you can break it into two parts like this. These are called components of this 40 Newton force. And this process is called resolving forces. Now, how do we resolve any force? For example, if we have that force 40 Newton, we can say it has two components, one acting in the horizontal direction like this, and one acting in the vertical direction like this. That 40 Newton force is equivalent to saying we've got one force acting in this direction, another force acting in this direction. This combination is equivalent to that 40 Newton. So we can break it down like this. Now, how do you find the values of these horizontal and vertical components? We have this right angle triangle. We know the angle. The angle is 30 degrees here. We can use sine and cos to figure out what these values are going to be. So for example, if we say the horizontal component is x, x over 40 becomes cos 30. And the vertical component, if that's y over 40 becomes sine 30. And that gives us that the horizontal component is supposed to be 40 cos 30, and the vertical component is going to be 40 sine 30. So the component that is adjacent to the angle, that will have cos with it. The component that's on the other side of the angle, that is going to have sine with it, right? Using those trigonometric functions. Now, I will be resolving these forces in a slightly different way, as in it's the same thing, it's the same logic behind it. But since in diagrams, you have a lot of forces acting a lot of times, for example, in this case, we've got three forces. You could have another force here that acts in this direction. Then making all of those triangles becomes makes a lot of clutter on your diagram. So for example, in this case, if you had these forces, you'll have a triangle here, you'll have another triangle here, you have another triangle here, you have another triangle here, and that ends up making you do careless errors sometimes. There's another way that I'll be using, and that is, we say, if this is the force 40 Newton that's acting in this direction, that 40 Newton is supposed to have two components, one acting towards the right side, one acting in the upwards direction, right? So we, instead of representing this vertical component here, we could do that. That's perfectly okay as well. I'm just representing that here at the point where the force starts. So I'll be representing the components in the rest of the session like this. Wherever the force is starting from, we make two components starting from that point. So one towards right side here, one upwards direction in this case. So one component will always be on one side of the force, and the other component will be on the other side of the force. And both of them will be making acute angles like this. Now, what are the components going to be now? What are the components going to be? If this is 40 Newton, and we know that the angle here is 30 degrees with the horizontal, the component that is adjacent to the angle, that'll have cos with it. The component that's on the other side of the angle, that will have sine with it. Now, these are equivalent to, if we were to use this angle 60 degrees, in that case, we would say the vertical component is 40 cos 60, and the horizontal component is 40 sine 60. Right? These two are equivalent. Sine 30 is the same as cos 60. Sine 60 is the same as cos 30. We could do it both ways. So in general, we could do something like this. If we have a force like this, a force F, it has two components, one acting in this direction, the other acting in this direction. The component that is adjacent to the angle, that will have cos with it. And the component that's on the other side of the angle, that's going to have sine with it. Okay. If you have something like this, for instance, if this is the angle that you're using, you would say the force is acting in this direction. Now, you will be resolving the force like this. You would say you've got one component acting on one side of that force, the other acting on the other side of the force, such that they're at 90 degrees with each other. The component that has side of the angle. So that's how you'll be resolving these forces. When you have an inclined surface like this, in an inclined surface, so generally what we do is if we have no surface involved, or if we have a horizontal surface involved, what we do is we resolve forces in horizontal and vertical directions. However, when we have an inclined surface, that looks like this, we resolve forces along the surface and perpendicular to the surface. These are the two directions in which we resolve these components. So how are we going to resolve them? Let me show that to you here, because this is like foundation of mechanics. So if you're given that this angle, for example, is theta, this is 60 Newton force, this angle is 30 degrees. So what about 60 Newton force, first of all? We're going to resolve in these two directions. So what are the components of 60 going to be? One component is going to be towards the right side, the other in this direction. The component that's adjacent to the angle, that's going to have 60 cos theta. And the component on the other side of the angle, that's going to be 60 sine 30. Now, this is very important. Whenever you have a force acting in vertically downward direction, generally you'll have weight acting vertically downwards. This is very important when you're resolving forces. It will come up again and again. If the angle of the plane is theta, for instance, if the angle of the plane is theta, the components of weight, what are they going to be? If this is the direction of weight, that's always the direction of weight, vertically downwards. If the angle is theta here, that means, what is this angle going to be? This angle is going to be 90 minus theta, right? Because this is 90. If this is theta, this is 90 minus theta. And if that is 90 minus theta, then this angle here, that turns out to be theta. So in a diagram like this, these two angles are always going to be equal to each other. If this angle is theta, this angle here is also going to be theta. So what are the components of weight going to be? The components of weight on an inclined surface, they will always be like this. Along the plane, you would have sine theta. So this would be 80 sine theta. And perpendicular to the plane, you would have cos. So it will be 80 cos theta in this direction. Okay, so that's how the components are going to be look like for this weight. Okay. All right, so that's how we resolve forces. So now let's get back to that example that we started from. We had this force acting 40 Newton in this direction, 30 degrees with the horizontal. What we do is we want to find out the resultant force. Now, for finding the resultant force, we do something like this. We say, okay, let's resolve these forces. So for this 40 Newton force, first of all, what are the two components that you get for this? One component to the right side, that's adjacent to the angle, that's going to have cos with it. The other component is on the other side of the angle, that is going to have sine with it. So this component has sine. These are the two components that we've got for the 40 Newton force. If we have this force 60 Newton acting in this direction, what are the two components of this going to be? One acting towards the left side, that's cos 45, because this angle is 45 here, and the other is going to be 60 sine 45. And similarly for the third force down there, that was 30 Newton. This 30 Newton force has two components, one acting towards left, one acting downwards, 30 sine 10 and 30 cos 10 respectively. Now, if you have to find the resultant force, how would you do that? You would represent these forces like this. You've got some forces acting in the horizontal direction. You've got some forces acting in the vertical direction. These are horizontal forces, the yellow ones, and blue ones are vertical forces. Now, to find the resultant, what we do is we first of all find the horizontal resultant and the vertical resultant. So the yellow forces that you see here, what we do is using them, we find the horizontal resultant. So what we generally consider in cases like these, we consider one side positive. For example, we can say right side is positive, left is negative, upwards is positive, downwards is negative. Just like we have it in Cartesian plane, XY axis that you have, right side is positive, left is negative, up is positive, down is negative. So we consider it like this as well. So in this case, resultant in the horizontal direction, what would that turn out to be? You would say 40 cos 30, that's acting towards right, minus the forces acting towards the left side. They are 60 cos 45 and 30 sine 10. So that's going to be your horizontal resultant. That turns out to be minus 13. What does that tell you? Since it's negative, we were considering the right side positive. The resultant of these forces is going to act towards the left side. It's 13 Newton towards the left side. Now, similarly, what we do is we find the vertical resultant. What is the vertical resultant turn out to be? We add these forces, subtract this from that. And the vertical resultant turns out to be something like this. 40 sine 30, that was one force acting upwards. 60 sine 45, we add them up together, subtract from that 30 cos 10, and that simplifies to 32.88 Newton. That's the vertical resultant. And now what we do is, once we've got the horizontal resultant and the vertical resultant, what we've got is that there's a horizontal resultant acting towards left of 13 Newton. There's a vertical resultant, since this is positive, that's acting in the upwards direction, that is 32.88 Newton. How do you find the overall resultant now? You make a right angle triangle like this. Now you say, okay, we've got one horizontal force now that's acting towards the left side. That's this 13 Newton. We've got one vertical force that's acting in the upwards direction. That goes like this. So we make a horizontal force like this, a vertical force like this, and we make a right angle triangle from that, because we know when we have a right angle triangle, finding resultant from a right angle triangle is pretty straightforward. You just make a triangle out of that. The hypotenuse gives us the resultant. So that's what we do here. We've got these two forces. these two resultants, one acting in the horizontal direction, the other acting in the vertical direction, the hypotenuse of this is going to give us the overall resultant. Okay, now how do you find the hypotenuse? Using Pythagoras, you say 13 square plus 32.88 square. That gives us the value for r. Using tan, you can find this angle theta. And how would you describe this angle theta? You would say this is theta degrees, 68.4 degrees above the positive x-axis. That's your resultant. You say the resultant is 35.4 Newton at 68.4 degrees above the negative x-axis. This is the negative x-axis. It's above that. That's your final result. Okay, that's your final resultant. So that's what we do. When we are finding resultant of a set of forces, what we do is we resolve forces. When we have resolved the forces, we find the horizontal resultant, that's Rx. We find the vertical resultant, that's Ry. We square them, we add those two numbers, take square root of that, that gives us the overall resultant. And then using tan, we find the angle of that resultant, and then we can describe that resultant. Okay, now this is one example of this. You can have a look at this. Fairly straightforward. You've got some forces acting like this. And what you want to do is you want to find the overall resultant. Again, what we do is resolve the forces, find the horizontal resultant. That turns out to be this 5.018. Then we find the vertical resultant. That turns out to be this. Using Pythagoras, we find the overall resultant after making a right angle triangle like this. And then we would describe the direction based on the angle that we've got. Okay, you can have a look at this. This is another example. Now, this is important. Sometimes what they do is, instead of asking you to find the resultant, what they'll do is, they would say, the resultant is given, and there's some force that is missing in the original data. Let's have a look at this example. It says two forces that have magnitudes of P Newton and Q Newton like this. The resultant has magnitude 12 Newton. So they have given you what the resultant force is, and they have shown you that resultant here as well. That's 12 Newton. And then they want you to find the value of Q. We've got the angles of the other forces there as well. They want us to find the value of this Q force. Now, how do you do that? Now, when you are finding the resultant, do not consider 12 Newton as an actual force. That's the resultant of the actual forces that we're applying. The actual force is this P Newton and this Q Newton. These are the forces that are acting. 12 Newton is not a force. It's the resultant of these two forces. Now, how do you find the value for Q in this case? You say the resultant is 12 Newton, right? The resultant is 12 Newton. That's what they've given us. And the angle at which it's acting is 80 degrees. What we can do is we can find the horizontal and vertical components of this resultant. So this will be Rx and this will be Ry. So Rx is 12 cos 80 and Ry is 12 sin 80. And then what we do is we say, okay, these are the values of Rx and Ry. Using these original forces, which were P and Q, we find our own resultant. So for example, what is Rx going to be? After we've resolved the force P, horizontal resultant would be Q minus P cos 60. That's the horizontal resultant. But they told us that the horizontal resultant is supposed to be 12 cos 80. So we equate it with that and we get an equation like this. Similarly, the vertical resultant. In the vertical direction, we only have one force that's acting, and that's in the upwards direction in this case, and that is P sine 60. That's the vertical resultant that we've got. The value for that is P sine 60. They gave us that this is actually supposed to be 12 sine 80. So we equate it with that. We get two equations like this. We solve them simultaneously, find the value of P and Q from that. Sometimes this can happen as well, that they give you the value for resultant, and you have to find some missing force in the actual data. So you compare both of them. You find the horizontal and vertical resultant from the given resultant. You find your own values of Rx and Ry, and then you equate both of them to find any missing force that is there. Now, the next is the concept of equilibrium. Now, before we do that, just a quick question that somebody asked here, so I'll just respond to that. So it was about reaction. So there is going to be reaction in this case as well, yes. So we would have reaction in this example that's acting in this direction, but that was not the point. We were considering how to resolve forces. So this is how we resolve the 60 Newton force, this is how we resolve the weight. But yes, reaction is going to be there in this case, but that's already perpendicular to the surface. So we don't have to resolve it in this case, because we only resolve forces in these two directions. The resultant is the normal reaction is already in this direction, so we don't resolve that. So that's why I did not show that there. But yes, that will be there, of course. Okay, now the next is the concept of equilibrium. So we talked about how to find resultant of a set of forces. Now, what is equilibrium? Equilibrium is when you have a set of forces that when they act on an object, the overall impact, the overall resultant is equal to zero. Or in other words, we can say, in this case, for instance, the resultant is zero, but it also follows from that, if the resultant is zero, the forces acting towards the right side, they should equal forces acting towards left. 7 plus 5 should equal 12 in this case. It does equal 12. That's why it's in equilibrium. Similarly, in the vertical direction, 6 plus 3, that equals 9. So in the vertical direction as well, we've got forces that are equal to each other. So whenever you have equilibrium, whenever they say something is in equilibrium, what we do is we just equate opposite forces. So if it's a horizontal, if the forces are horizontal and vertical like this, we say the forces acting towards the left side, they should equal forces acting towards the right, and the forces acting in the upwards direction, they should equal the forces acting in the downward direction. Now, that's not always true. It is only when you have equilibrium. Don't put them equal to each other in every single case. This is only true when you have equilibrium. Otherwise, they are not necessarily going to be equal to each other. So left equals right, up equals down. That is what you do when you have equilibrium. When you have an inclined surface like this, what about that? On an inclined surface, we consider directions like this. So we think of yourself as standing on this plane, on this surface. So standing on the surface, what would be the upward direction for you? This will be the upward direction. This will be the downward direction. This will be your left direction if you're facing the screen, and this will be the right direction. So in an inclined surface, the understanding of left, right, up, down changes like this. Okay. Now, a point to note here: whenever you have an inclined surface and the object is moving, for instance, these forces are always going to be equal to each other. Perpendicular forces to a surface, they will always be equal to each other in your syllabus, because in your syllabus, objects can only move in a straight line. There can't be any projectile motion like this. So that means the perpendicular forces, these forces, they will always be equal to each other without exception in your syllabus. If the object is moving, that will only be along the surface like this. So right or left, if the object is moving, one of them will be bigger and the other would be smaller. But these forces are still going to be equal to each other, no matter whether the object is moving or not. Okay, now this is one thing that confuses some people. So they say there's a particle P that is in equilibrium on a smooth horizontal table. So we have a horizontal table under the action of horizontal forces. We've got these forces that are represented there. We need to find the values of F and G. Now, since it's equilibrium, what we can do is we can just find the components of each force, equate the opposite forces, left equals right, up equals down. That's what I've done here. Resolve the forces, equated the opposite forces, left equals right and up equals down. However, they've also given, they've not given, but you could also think of sometimes what happens is, in this case, it's not given, but sometimes what happens is in the next part, you need the mass as well. For some reason, you might have to use Newton's second law of motion, and they might give you the mass of this particle. Let's say that's 5 kilograms. Now, do not represent the weight of the object on this diagram. You do not say that there's a weight of 50 Newton acting in this downward direction as well. That is not going to be there. It's a horizontal table and the forces are all horizontal. So you think of it like this, that it's a table like this, the yellow table, it's horizontal. The forces that you have, let's say, this is from another example, this is a 2.5 Newton force, this is an F Newton force, this is the 2.6 Newton force. They are all acting within the table, right? Along the surface of the table. Weight acts perpendicular. Weight acts vertically downwards. So the table is horizontal. Weight will be acting vertically downwards. Now, weight does not have anything to do with the rest of the forces in the table. That's a perpendicular direction. Weight does not have any component acting in this direction. So when you have horizontal forces acting on a horizontal table, on a horizontal surface, weight is not going to be considered as one of the forces. You are not going to represent weight here in this case. Okay, so even if they gave you mass, that would be used for some other part. Maybe they want you to find acceleration in the next part, but do not add that as a force here. That is not going to be relevant here. Okay, now we've got some forces that you need to know about. So in a lot of cases, they will tell you some forces in the question itself, but there will be other forces that you'll have to represent yourself that they will not tell you about in the question statement necessarily. So what are those forces? There are 4 forces like that you always need to think about in any situation, that whether they are applying or not, the other forces, they will always tell you. So what are those forces that you have to think about yourself? We've got weight, normal reaction, tension, and friction. These are 4 forces that you'll have to think about yourself, that whether they're acting in a particular situation or they're not acting. Okay, weight, normal reaction, tension, friction. Now let's start with weight first of all. What's weight? Weight is just the force that Earth is applying on an object. Its definition is mass into gravity. In mechanics, what we do is we take the value of gravity as 10 meters per second square. You should use that value. Do not use 9.81. They instruct at the start of the exam that you should be using 10 here. 9.81 is going to complicate a lot of calculations for you as well. So make sure that you use 10 here. Weight is defined as mass into gravity. For example, if something has a mass of 15 kilograms, its weight is going to be 150 Newton. Just multiply that by 10. Now, weight is also a force. So its unit is going to be Newton. The direction of weight is always vertically downwards. It always acts vertically downwards. That's important. So if you have a horizontal surface like this, for instance, where is the weight going to act? Weight is going to act vertically downwards in this direction. If you have an inclined surface, that does not change anything. Weight is not because of the surface, it's because of the earth. It still acts vertically downwards. The direction of weight is going to be this. It acts vertically downwards like this. All right. But then since it's an inclined surface now, you would have to resolve it in these 2 directions along the surface and perpendicular to the surface. How do you do that? If the angle of the plane is theta here, we talked about earlier that this angle here is also going to be theta. So the components are going to be W sine theta and W cos theta along the surface, W sine theta and this W cos theta when you resolve this weight. Then you've got normal reaction. What's a normal reaction? Normal reaction is the force that a surface applies on an object. It's the force applied by a surface on an object. Now, for example, let's say you've got this horizontal surface. In this case, you've got a weight acting in the downward direction. That's 150 Newton. Now, because of this 150 Newton, the object is not going into the surface. It's staying in its position. Why is it staying in its current position? Because there's an equal and opposite force acting in the upwards direction, and that's normal reaction. That's 150 Newton in this case. In the absence of any other forces, this will be 150 Newton as well. This is reaction. Now, normal reaction always acts perpendicular to the surface. It always acts perpendicular to the surface. So whatever the surface is, the direction of normal reaction is going to be perpendicular to that. It's not always going to be equal to or opposite to weight. Now, in this example, you can see that it's equal to weight and it's also opposite to weight, but it's not always going to be true. For example, if you have a situation like this, still have a horizontal surface and the weight is 30 Newton. However, there's also an upward force that you're applying and that's 10 Newton. Then the reaction is not going to be 30 Newton. It's going to be 20 Newton. That's going to be the balancing force. So if you have 30 Newton acting downwards, upwards as well, you should have 30 Newton if the block is not moving. Then R plus 10, that means reaction plus this force. This should equal 30. So the value of R that you end up getting from that is 20 Newton. If the block is in equilibrium, that's the value of R that you get. So it's not equal to weight every single time. And on an inclined surface, for example, if you have weight acting in this direction, 90 Newton, vertically downwards, where does reaction act? Reaction does not act opposite to weight in this direction. It acts perpendicular to the surface. Now, the surface is inclined like this. The direction of reaction is going to be this. Okay. And what is that going to be equal to in this case? This component of weight, 90 cos 40, reaction is actually going to be equal to this component. It's not going to be equal to 90. It's going to be equal to 90 cos 40 in this case. So in this case, you can see it's not equal to weight and it's also not opposite to weight. It's always going to act perpendicular to whatever the surface is. Now, sometimes you'll see situations like this as well. You'll have something vertical. For example, you have a rod like this, and on this rod, you have a ring that is tied like this. So this is a ring that's tied to the ring. Now, in this case, let's say we've got some forces acting. We've got the weight acting in the downward direction, of course. Let's say that's 0.5 Newton. There's a force acting in this direction, that's F Newton. What are going to be the components of F? One in this direction, the other in this direction, F sine 25 and F cos 25. You can see them on the diagram. If this angle is 25, this is cos 25, this is sine 25. Now, if the object is in equilibrium, if the ring is in equilibrium, what does that mean? Opposite forces have to be equal to each other. Now, this force is actually applying this force is actually acting towards the right side. It's trying to make the ring move towards the right side, but the ring is not moving. It's tied to the rod. It's not moving to the right side. Why is it not moving? Because the rod is going to apply a force and towards the left side, and that's going to be the normal reaction in this case. A rod is the surface. This normal reaction is perpendicular to that rod. It acts towards the left side. Why? Because this force was acting towards the right. Reaction is going to balance that force to keep this ring in equilibrium. Now, if there was a force acting towards the left side, for example, that was a bigger force. Let's say that was a 70 Newton force, and if we knew that F was less than 70, then reaction could act towards right as well. So reaction can act either towards right or left in this direction. It could be this, it could be this. It would depend on the rest of the forces. If you have more forces acting towards right, reaction will be to the left to balance those forces. If you have more forces acting towards left, reaction will be towards right, again to balance those forces. But it has to be perpendicular to the surface, like in this case, it's going to act towards the left side like this. So that can also happen. All right. Okay, now let's have a look at this example. It's pretty straightforward. You've got some forces acting here. You're given that it's at rest. At rest means that it's in equilibrium. Opposite forces are supposed to be equal to each other. In the first figure here, you can see you've got some forces acting like this. You've got P Newton acting in this direction. That's the only force that they give you. Now you have to think about the rest of the forces yourself. The weight is 12 Newton. Where does that act? That acts vertically downwards. Since you have a surface involved, whenever you have a surface in contact with an object, you would always have normal reaction, and that is going to be perpendicular to the surface. The direction of normal reaction is this. Now, if we want to find the value for P, what we can do is we can just equate the opposite forces in this case. In the first case, P is equal to 12 sine 40, and that gives the value for P. You can see what that is. Okay. In the second example, if the force is acting like this, it's P Newton. What about the value for P? In this case, again, we resolve the forces, equate the opposite forces, and that's going to give us the value for P. Now, this is very important. Whenever you have a force acting like this, a lot of people end up resolving it wrong if it's represented like this. If it's represented like this, in which direction is the force acting? The force P, it's acting towards the right side, right? The force P is acting towards the right side. I would recommend that you represent that force on the side that it is acting. Now, it's pushing the object to the right side. So the direction of force is towards the right side. It's going to make you do less careless errors while resolving this force if you represent it on that side. Okay. Now, if you represent it on that side, we can clearly see this angle is 40. This angle here is also going to be 40. These are corresponding angles. And then you can resolve it like this. This angle, this component is P cos 40 in this direction. The other component in this direction, that's going to be P sine 40. Equate the opposite forces, and that's going to give you the value of the unknown that you have there. And you can find that like this. Okay. This is an example that we've already talked about before. So for example, in this case, you see the first part, you are given that this is in equilibrium. This object is in equilibrium, and they've given you mass because that is actually required for the next part of this problem. In the first part, a lot of people end up doing this mistake. They say that there's going to be a weight. There's going to be weight acting in this direction as well. That's 5 Newton, but that's not true. That's not going to be true because the forces are horizontal. These are horizontal forces. It's a horizontal plane. So weight is not going to be considered as one of the forces in this case because the forces that we've got here, they are all acting inside that horizontal plane. Weight acts perpendicular to that. That does not contribute to the forces acting along the surface. So we do not consider weight here. Okay, so we already talked about this before. let's move on to the next force. That's it. That is tension. Yes, that's correct. That's correct. So reaction will be acting towards the side that has less forces. Yes. Now, what about tension? Tension is a force that a string applies on an object. It's a force that a string applies on an object. Let's consider this example. You've got this rod, and this rod has this string tied to it at this particular point. So this is the point at which the string is tied. Now, the block is hanging from this string in the vertical direction like this. The weight of the block is 50 Newton, mass is 5 kilograms. Now, since there's weight of the object, that's pulling this block in the downward direction, but it stays in its current position. Why does it stay in its current position? Because the string is applying a force on this block as well that is keeping this block in its position. What is that force? We call that force tension. And the tension in this case is going to be 50 Newton. Why? Because if it's an equilibrium, if weight is 50, to balance that, tension is also going to be 50. Now, tension is the force applied by a string on an object. It's the force applied by a string on an object. What about the direction of tension? Tension always acts away from the point of reference. Away from the point of reference. Tension always acts away from the point of reference. Now, what exactly does that mean? Okay, so this is on going on. We'll have a 1 minute break and then we resume after that. I'll continue from here. We will have a break from Maghrib after forces in equilibrium. Inshallah, hopefully we'll get done with it in about 20 minutes and then we will talk about the next forces. Ali, which live? No, that's not public. You'll not be able to access that. I'll share the recording later on. Okay, let's resume. So what about tension? Tension, as I said, is the force applied. Tension is the force applied by a string on an object. Now, tension always acts away from the point of reference. It always acts away from the point of reference. Now, what does that mean? If you consider tension from the perspective of the block, on the block, the string is applying tension in this direction, away from the block and towards the string in the upwards direction. But at the same time, the string is also tied to this point on the rod. So if you consider from the perspective of the rod at this particular point, on the rod, the tension acts in the downward direction. On the rod, the tension acts in the downward direction, away from the rod and towards the string. So whatever is the point that you that's your point of reference, from that tension is going to act away in this direction and towards the string. Yes, if it's a single string and on both sides you've got one point here and you've got another point here, the tensions on both sides of that, they're going to be equal to each other. Yes, because it's a single string is in its in equilibrium position as well. It's not moving. If it's not moving on the string, you have equal forces acting in both directions. That is why it is in its current position. So if this tension is 50 Newton, this is also going to be 50 Newton. They're both going to be the same. Now, why is it that the tension is always going to act away from the point? Because think about a string. If you have something placed like this, and you have a string tied to it, tied to that block, tied to this block. Now, with a string, you can only pull the object towards yourself. You cannot push something with a string, right? If it was a rigid object, as we'll see later, sometimes what you have is a rod like this, and that is tied to an object. With a rod, you can both push and pull, but with a string, you can only pull something towards yourself. So that is why with a string, the tension always acts away from that object and towards the string in this direction. Now, a lot of times what will happen will be you will have multiple strings. You'll have multiple strings. Okay. Yes, of course, direction will be different. Magnitude will be the same. Direction will be different. Yes. If you've got multiple strings like this, let's consider the scenario. You've got this ring that is hanging from a string like this, that one part of the string is tied to the point A here, and the other part of the string that is tied to the point B here. And the string is passing through the string, and the ring is hanging like this. Now, when you have anything like this, a single string and the object that is attached to the string, the string is easily able to pass through that. It's easily able to slide through that. In that case, the tension on both sides is going to be equal. Compare that with something like this. In this case, we've got two different strings. One that is string 1 on the left side, the other string 2 on the other side. But in this case, what's happening is the strings are tied to this object. There's a knot on this object. So in this case, the string is not free to move through the object. When you have a situation like this, the tensions on both sides are not going to be considered equal. If you call one of them T1, the other will be called T2. In the first situation, we called both of them T. Now, what exactly is the difference between them? Tensions are going to be equal when both of these conditions are met. It should be a single string. And it should be free to slide or move through the object. For example, if you have a ring like this, string can easily slide through that ring. So in this case, tensions on both sides are going to be equal to each other. This is one common case that you'll see, the case of a ring. The other common case that you'll see here would be of a pulley. If a string is passing over a pulley like this, in this case as well, tensions on both sides of the pulley for that same string, they're going to be equal to each other. So if you call one of them T, the other is also going to be T. Okay. In the other case, the tensions are not going to be equal. What's the other case? It could either be a single string that is not free to slide because of this knot, or it should be two different strings. Whenever you have two different strings, in that case as well, we do not assume that the tensions are equal. They may sometimes end up being equal, but we are not going to assume that. So the common cases that you will have in your syllabus when the tensions are going to be considered equal, they are going to be either when you have a ring like this, or when the string is passing over a pulley, the general rule is when it's a single string that is free to slide or move through the object. Because think about it, if you have a ring in this position, if you were to apply a force towards the right side, because of that force, what would happen would be, let's say you've got this force F that's acting towards right side. Since the string is free to slide through the object, the length of the string on the left side and the length of the string on the right side, this is going to adjust in such a way that the ring comes in equilibrium position again like this. And the tension on both sides, they're also going to adjust and they will become equal to each other. Compare that with the other case. If there was a force acting towards right side in this case, since there's a knot here, the string, they cannot change their length as because the string is not free to slide through the object. Because of this force that's acting towards the right side, there's going to be more pressure on T1, right? When you pull this object towards right, there's going to be more pressure on this point. So T1 is going to be bigger than T2 in this case, right? So that's the idea behind it. But that's what you need to remember now. Single string free to slide, equal tension. But that condition is not met. Any of these conditions, whether it's a single string, if that condition is not met, or if it's not free to slide, you say the tensions are not going to be assumed to be equal to each other. All right. The common cases are ring and pulley, as we discussed. Let's take this example. Let's say we've got an object like this. It's a ring, and this ring has a string passing through it. One end of the string is tied to the point A here. The other end is tied to the point B here. Now, at the ring, we've got some forces acting. What are those forces? We've got X Newton acting towards right side. We've got weight acting in the downward direction. And there are going to be tensions, one in this direction and the other in this direction. These are two tensions that we've got. They are both going to be equal to each other. Why? Because it's a ring. The string is free to slide through the ring. The tensions are going to be considered equal to each other. Now, the question statement is also going to hint about it in some way, because in this case, you see the question says find the tension in the string. They're not using a plural here. Find the tension. That means it has to be equal. It can't be multiple tensions. If they specify, find the tension in the lower string, find the tension in the upper string, find the tension in one of the strings, or find both tensions. In that case, you know that the tensions are going to be different. Okay. Yes, it's free to slide because it's a ring. Through the ring, the object can move. It'll always be smooth if it's a ring. It'll always be smooth. You don't consider friction in case of ring generally, at least not until now in past papers. There's always a first time. But in that case as well, the tensions are going to be equal. There's just going to be some friction added there. But I think that will become too complicated. Let's not get into that. You'll always have a smooth ring. And in that case, yes, it's going to be equal. But the main reason for that is, in the second case, there's a knot. So the string is not free to slide, as in it can't, the length on both sides, that cannot change. That will remain the same in the second example. And that's what is causing the tensions to be different. Because of this extra force that might act, there's going to be more pressure on one of those tensions and there's going to be less pressure on the other one. Okay, all right, let's move on. So in this case, the tensions are going to be equal to each other. All you have to do now is, since it's equilibrium, resolve the forces, equate the opposite forces. Forces acting towards left equal to forces acting towards right. Forces acting upwards, they should equal forces acting in the downward direction. This is another example. We've got this, what's this? It's this particle. We've got this particle, and the particle is attached to two strings. One is S1 and the other is S2. Now, these are two different strings. When you have different strings, tensions are not going to be equal to each other. So we're not going to assume them to be different from each other. Again, in this case as well, what do? Since it's equilibrium, we resolve the forces, equate the opposite forces, and that will give us the result. And what's the new thing here? Sometimes what happens is they give you the lengths of the strings like this. One string is 0.52 meters, the other is 0.2 meter, the other is 0.25 meter, and this height is 0.2 meters. Whenever they have these lengths given for the string or some distance like this, that the only reason why that is given is going to be to find the angles. You can use those lens along with a right angle triangle to find those specific angles. Once you've got the angles, there's no other use of these lens. Okay, so these lens are only going to be used to find angles. Once you find those angles, just get rid of them because they're not forces. That we are not going to consider them anymore. And then we just equate the opposite forces. First resolve the forces, equate the opposite force, and that's going to give us the result. Okay, all right. Let's move on. We can sometimes have something a bit more complicated like this as well. What I'll do is okay, I'll just zoom in a little, and that might help. So we've got this point X in the middle, this point X in the middle, this point here. And there are three strings that are attached to this point. There are three strings that are attached to this point like this. One is going here, the other is going, another is going here, and the other, another is hanging below like this. There are three strings. Now consider the one on the left side. This string is passing over a pulley. Now on both sides of the pulley, the tensions are going to be equal to each other. So whatever is the tension on the left side here, that's going to be the same as this tension on this side here. Now we know at the point A, this is an equilibrium situation. So point A is also in equilibrium. The particle is in equilibrium. That means downwards we've got 5.5 Newton. Upwards we've got tension. So tension is also going to be 5.5 Newton. If this is 5.5 Newton, that also implies that this tension here on the other side, that's also going to be 5.5. Right? So on both sides of a pulley, the tensions are going to be equal to each other. Similarly, on the other side of this diagram here, you can see we've got weight acting downwards, that's W Newton. So the tension is also going to be equal to W because the object is in equilibrium. Now, if this is W, that implies that this tension here, that is also going to be W. Okay. And now you've got a situation like this. You've got this point X. There's one force acting in this direction. There's another force acting in this direction. There's another force acting in the downward direction. That's 7.3 Newton. Weight is 7.3, so the tension on the particle B is going to be this. If that's this, then the tension on X in the downward direction is also going to be 7.3. So we've got three forces acting at the point X, 5.5 in this direction, W in this direction, 7.3 in this direction. You can resolve the forces, equate the opposite forces, and that will give you the result. So in this case, you can see if we've resolved the forces, equated the opposite forces, left equals right, up equals down, and that gives you the result. You can go through the working. That's how it would work. Okay. All right. Then now this is something that's not explicitly part of the syllabus, but sometimes they give this as an alternative solution in some questions, and it makes some specific questions very straightforward and very quick. And what's this? This is something that we call Lami's theorem. And this can be used when two conditions are met. Number one, object is in equilibrium. And number two, you have exactly three forces. When both of these conditions are met, you've got equilibrium, and you have exactly three forces. In equilibrium, when you have exactly three forces, they have to be coplanar, of course. You can't have forces acting in different planes. They have to be coplanar, of course, but exactly three forces. You can't have 4, 5, exactly three. When you have three forces, then this holds true. F1 over sine of this angle, the angle opposite to that, that equals this F2 over sine of the angle opposite to that, and that equals F3 of the sine of the angle opposite to that. Now, as you might have guessed, this comes from sine rule. If you make a triangle out of that, you get the sine rule. It comes from that, but that's what Lami's theorem says, and that makes some problems very quick. Some 5-mark questions. The normal way would be to resolve the forces. You find the horizontal component, vertical component for this. Find the horizontal, vertical components for this. And similarly for all the forces, all the three forces, then you equate them, solve simultaneous equations. Using Lami's theorem, you can do some of those questions in like 2-3 steps. And that makes it a lot quicker, a lot more efficient. Let me see if I can find one example of that for you quickly, where I've used Lami's theorem somewhere. Just give me a second. This is forces and equilibrium. Lami's theorem. No. Okay, so a similar example to what we saw previously. You can see the solution. We've got the angles given. We've got this point P. We've got this point P. At this point P, we've got a force acting in the downward direction. There's another force acting towards right. That's T2. Another force acting here. That's T1. Three forces, and the object is in equilibrium. The object is in equilibrium. Three forces. What we can say is, we can use sine rule. It's a 5-mark question. You can do this in 2 steps like this. What do? You say this force T1 that's acting in this direction, what's the angle opposite to that? You've got these lengths, you can find those angles using that. Okay, so the angle opposite, this turns out to be 112.62. You can see the calculations for that above here. This angle is 104.25. This angle is 143.13. So make an equation like this. T1 over sine of 112.62, that equals 21 over sine of this angle. And that also equals T2 over sine of this angle. And you get 2 equations from that. You can make an equation from these two. You can make an equation from these two. Find the values of T1 and T2 from that directly. You won't have to resolve the forces. You can just do it directly like this in this case. Okay, have a look at this. If you don't know this and you think it's complicated, just leave it. It's not required. But those of you who know it, you might know that this is pretty helpful. But the condition has to be met. The condition is 3 forces and equilibrium. That's the only case you use it. That's a very common case in past papers, so that's why it helps sometimes. But remember, no other case can you can use Lamy's theorem. This is the only case: equilibrium and 3 forces. Okay, let's move on. Okay, let's assume that. So the next force that we've got is friction. Now, we talked about normal reaction before. Normal reaction is when an object is in contact with a surface and the surface applies a force in the perpendicular direction to the surface. There's another force that we also have when 2 objects are in contact with each other, when the surface is rough, and that is friction. Now, normal reaction always used to act perpendicular to the surface. Friction always acts parallel to the surface. Friction always acts parallel to the surface. And both of these together, they're called contact forces, right? This terminology is important. Sometimes they use this in questions. Contact force is the force that is due to contact between 2 objects. When 2 objects are in contact with each other, the forces that we have because of that contact are called contact forces. There are 2 of them. One is normal reaction, that's perpendicular, friction, that is parallel to the surface. Now, let's consider this example. Let's say you have a force, you have an object like this. It has a weight of 500 Newton. If you were to apply a very small force in one direction, for example, just 0.1 Newton towards the right side, now because of the small force, practically speaking, it's very unlikely that the object will start moving to the right because it's so heavy, 500 Newton. You're just applying a very small force in this. Practically what happens is the surfaces that you have, they have some roughness in them. So if it was a perfectly smooth surface, theoretically, then even a small force will make it move. But generally that does not happen because you have some rough objects. So if you apply this force 0.1 Newton, why does it not move? Because the surface applies an equal force towards the left side that keeps the object in its current position and does not let it move. Okay, that's called friction. It's the force applied by a force applied by a surface on an object that opposes the motion of the object. It opposes the motion of the object. It does not let that object move. So it always acts parallel to the surface and opposite to the possible direction of motion. Why possible? Because in this case, the object is not actually moving, but in which direction can it possibly move? It can possibly move towards the right side because of this force. Friction stops it from moving, so it's acting opposite to the possible direction of motion. So it acts in this direction. Now, what do we need to know about friction? It has some maximum value. So for example, in this case, if you have an object, 50 kilograms, 500 Newton weight, if you apply a force of 90 Newton to the right side, let's say the object does not move because of that. But if you were to apply a force of maybe 9,000 Newton on the right side, what about that case? If you apply such a large force, it's very likely that the object will start moving even if there is friction between them because we're applying such a large force. Now, so let's actually compare 9,000 and maybe just 0.9 Newton. So if you're applying 0.9 Newton, it's very unlikely that the object will move. 9,000 Newton, that's extremely large. It's very likely that the object will move to the right. What's that cutoff point at which the object starts moving? That is going to be somewhere between 0.9 and 9,000, right? That cutoff point is what we call the maximum value of friction. So friction always, in any context, will have some maximum value after which it would not be able to stop the object from moving. Let's assume for now, in this case, that the maximum possible value of friction was 100 Newton. We'll see where this comes from. Let's say this was 100 Newton. Now, if this was 100 Newton, what happens is, if we apply a force of 90 Newton to the right side, the object does not move because friction is able to counter that. If we apply a force of 100 Newton to the right side, again, it does not move because friction can equal 100 Newton as well, and it stops the object from moving. However, if you increase the force even slightly more than that, let's say apply a force of 101 Newton to the right side, maximum possible value of friction was 100, so the friction cannot stop the object from moving anymore. Friction stops at 100 Newton. It cannot increase to more than 100. So what happens because of that is the object has a resultant force of 1 Newton that makes it start moving to the right side. So friction has a maximum value. Friction has a maximum value. If you apply a force that is greater than the maximum value of friction, the object will start moving. Now, where does that maximum value come from? There are two things that basically decide what the maximum value of friction is going to be in a particular context. Number one is something that we call the coefficient of friction. This basically quantifies the roughness of the surfaces. So the more rough the surfaces, the higher its coefficient of friction is going to be. It's represented by mu. So if a surface has more roughness, it has more friction. And the second thing that friction depends on is normal reaction, because normal reaction basically captures how strongly two objects are connected to each other. So if the strength between two objects between an object and a surface is more, strength of contact between two objects, if that's more, then the friction is going to be more. For example, take this case. In the first example, you've got a weight of 200 Newton. There's a normal reaction of 200 Newton as well. These are connected to each other by a force of 200 Newton, the object and the surface. In this next example, we've got the weight acting downwards, that is 200 Newton, but we are also applying a force acting in the upwards direction, that's 50 Newton. Now, the net force that is actually applying on the ground, and the ground is applying on the object, that is only 150 Newton. So in this case, the strength of contact between the two objects, that is reduced, and that strength of contact is actually captured by this normal reaction. So that's the other thing that maximum value of friction depends on. Now, that's the logic behind it, but now you just need to remember, maximum value of friction is given by mu times r. Okay, that's the formula that you need to remember. F max equals mu times r, where mu is the coefficient of friction and r is the normal reaction. These are two things that the maximum value of friction depends on. Now, let's go back to that same example that we saw before. In that case, if we knew that the coefficient of friction was 0.2, in this case, you can see that the weight was 500, so normal reaction in this case would also be 500. So mu times r, that gives you 100 Newton. So that's the maximum value of the friction. And then we looked at these cases. If we were applying a force of 90 Newton, the object will not move. 100 Newton, the object will still not move. 100 Newton, the object will start moving. So when the force that you're applying becomes greater than the maximum value of friction, what happens is the object starts moving. When the force that you're applying is equal to the maximum value of friction, we call this equilibrium, but it's a specific case of equilibrium, and it's called limiting equilibrium. It's called limiting equilibrium. Why? Because the equilibrium has reached its limit. Even if you were to increase this force even by a very small amount, what would happen would be the object will start moving. So equilibrium has reached its limit when the force that you're applying is equal to the maximum value of friction. So in both of these cases, you see, friction is at its maximum value. When the object is moving, F is equal to mu r. the friction will stop at that point. And also, when you have limiting equilibrium, friction is at its maximum value in both of these cases. If the force that you're applying is less than, it's a force that you're applying, so it's any force that you're applying, right? So we're applying a force to the right side. We're calling that P. We could call that anything. If you're applying a force of 90 Newton, that is less than the maximum value of friction. In that case, we call this non-limiting equilibrium. That it's equilibrium. The object is not moving because friction is also 90. This is also 90. The object is not moving, but it's not at its limit yet. If we were to increase this force by 1, for example, 91 Newton, friction will also become 91 Newton. If we increase it to 90 Newton, friction will also increase to 92 Newton. So it's not limiting equilibrium. We call this non-limiting equilibrium. So we got these three cases that you need to remember from this. Whenever an object is in motion, or its limiting equilibrium, we have F equal to mu r. Okay. This is the limit, maximum value of friction, mu times r. In both of these cases, when the object is in motion and when it's limiting equilibrium, F is equal to mu r. When it's non-limiting equilibrium, friction, that means it's not at its maximum value. It will be less than that. You can see that here. The value of friction is less than the maximum value. F is less than mu r. If you were to combine these two cases, in equilibrium, friction can either be equal to the maximum value or it can be less than the maximum value. When it's limiting, it's equal to mu r. When it's non-limiting, it's less than mu r. If we combine these two cases, we can say whenever we have equilibrium, that means friction is either less than or equal to mu r. Now, this case is not used a lot in past papers when you have non-limiting equilibrium, but you'll see this used a lot whenever the object is in motion or limiting equilibrium. In both of these cases, remember, you will say F is equal to mu r in both of these cases. And sometimes they will say that the object is in equilibrium. And they will ask you to prove some inequality or find some inequality. In terms of mu, the coefficient of friction, they'll ask you to find some inequality. In that case, remember, whenever an object is in equilibrium and you want to form some kind of an inequality, in equilibrium, the general rule is F is less than or equal to mu r. F is less than or equal to mu r. We'll have a look at some examples of this. So this is what you need to remember. F is equal to mu r when it's in motion or it's limiting equilibrium. F is less than or equal to mu r when it just says that it's equilibrium and it does not specify whether that equilibrium is limiting or non-limiting. Now, for limiting equilibrium, sometimes they will say in the question that the equilibrium is limiting or it's limiting equilibrium. Sometimes they say that same thing in some other words. You need to be familiar with these phrases. When an object is just about to move, just about to slide, just about to slip, that means the equilibrium is at its limit. It's on the point of moving, on the point of sliding, on the point of slipping. Again, that is another way of saying that this is limiting equilibrium, that the object is just about to move. And in this case, what you would do would be, you would say F equals mu times r. Let's take an example. Let's say we've got the surface. Let's just look at the second part of this. First part is fairly straightforward. And the first part, surface is smooth. So you would just resolve the forces since it's equilibrium and equate the opposite forces. Now, in the second part, it says the surface is rough. So we have a rough surface. And the block is on the point of slipping. What do we understand from that? It's limiting equilibrium. It's on the point of slipping. That's limiting equilibrium. So F is equal to mu times r. So what you do in this case is, it's on the point of slipping in what direction? Do we know that in what direction it's on the point of slipping? Let me just read the question statement quickly. We've got tension acting in this direction, 75 Newton acting in that direction. Okay, so they have actually told you in which direction friction acts. I was just thinking about that, in which direction friction is going to act. They have told you explicitly that it's going to act towards A, because otherwise you could not figure that out, because it would depend on whether 75 cos 30 is bigger or T cos 60 is bigger. So in this case, since that's not specified, they have told you the direction of friction. So it's acting towards the left side. All you have to do is just represent all the forces, equate the opposite forces. T cos 60 plus F in the second part. They should equal 75 cos 30. That's one equation. T cos 60 plus F equals 75 cos 30. And in the vertical direction, you have these three forces. In the downward direction, you have 200. So you say sum of those three forces, that should equal 200. You get two equations. Now, since it's limiting equilibrium, you would replace F with mu times R in this case, although in this case, we have to find what coefficient friction. Okay, so you could replace F equals mu R. In this case, what I've done is I've just input the value of F here. That gives me the value for tension and the value for reaction. And once I have that, since it's limiting equilibrium, F equals mu R, and we can say 25 equals mu into 93.301, and that gives us the value for mu. Another way of doing this could be that in place of friction here, we could just write mu times R, or that will be the same thing. It doesn't make much difference. So that's the idea. When you have limiting equilibrium, F is equal to mu R. That's what you have to do. Okay, equilibrium still means opposite forces are equal to each other. Left equals right, up equals down. But whenever you have friction there, in limiting equilibrium case, you would say F is equal to mu R. Now, sometimes what they do is they ask you something like this. Let's have a look at this question quickly. So we have a rough plane. Cos alpha is this, sin alpha is this. Given that the normal component of the contact force, what does that mean? That's the normal reaction. Is 1.2, find the mass of the particle. In the first part, you just know that the normal component is 1.2. Then this R is 1.2. W cos alpha is the weight component. They should be equal to each other. And that gives us the value for W. We can find mass from that. Now, the first part is pretty straightforward. Second part says friction has this value. You equate these forces along the surface, and that would give you the value for, in fact, the particle is moving. You have to find deceleration. Okay, just skip that. That's Newton's second law of motion. What I want to talk about in particular is the last part here. It says the particle is moving. It's going in the upwards direction. Okay, it's moving up. Now, when it moves up, what happens is it comes to rest at some point. It comes to rest at the point X. Let's say this is point X. It comes to rest at that point. Now, at that point, we need to determine whether the particle is going to remain at X or it is going to start moving down the plane. How do you figure that out? So the particle is at the point X. And now, is it going to start moving down the plane or is it going to stay in its current position? That's what you need to figure out. We think about all the forces that are acting on the point X. We've got weight acting downwards. We've got normal reaction acting here. We've got the component of weight that's acting in this direction. That's W sine alpha. And we've got friction. Now, since the object is going to try and move in the downward direction now when it comes to rest first, now it's going to try to move downward, friction, that's going to act in the upwards direction, in this direction. Now, that's the direction of friction that we've got. How do you figure out if the particle is going to move downwards or stay at rest there? We can figure out the value for W sine alpha and see what that turns out to be. The value of W sine alpha in this case, we know the value of W, we know the value of sine alpha. That turns out to be 0.35. What about F max, the maximum value of friction? We knew that the friction was 0.4 Newton when the particle was moving. When the particle was moving, the friction was 0.4, and we know when a particle is moving, friction is at its maximum value. So the maximum value of friction is 0.4. So the weight component in this direction is 0.35 Newton. The maximum possible value of friction that we've got is 0.4 Newton. That means this force, 0.35 Newton, is not going to be able to counter friction, and the object is not going to move in the downward direction. It will stay at rest. If W sine alpha, this value was greater, if it was greater than friction, in that case, the object will start moving in the downward direction. Okay. The two components of contact force, they are normal reaction and friction. This is the other component. Frictional component, that's the other component. Friction is the other component. Okay. Okay, so F here, in this representation that I have here, F represents friction. F is representing friction. F is not this force. This force is represented by P here. That force is greater than maximum value, yes. With small f, I'm representing friction here. Friction cannot be greater than mu r. Mu r is the maximum possible value of friction. How can friction be greater than its maximum value? That's not possible. Friction has to be equal to the maximum value when the object is either moving or is in limiting equilibrium. Okay, it has to be equal to maximum value. Okay, so this is one thing that you will see as well. You have to figure out whether the particle is going to move or it's going to stay at rest to figure out what the force acting is and what is the maximum possible value of friction. If the force acting in the forward direction is less than friction, the object cannot move. And if that force is more than the maximum value of friction, then the object will start moving. Okay? No, it's not used in the usage sense. So normal, the contact force has two components, as in it has two parts. One is friction and the other is normal reaction. Maximum friction remains the same as long as mu is the same and r is the same. If any one of these two things changes, then maximum value of friction changes. So if mu remains the same, if it's the same surfaces, and the reaction remains the same, if both of these things remain the same, F max is also going to remain the same. Otherwise, it might change from one part to the next. That can happen sometimes. Mostly, it will remain the same when mu and reaction are the same. In fact, it will always remain the same. In that case, if it is changing, then that would also change accordingly. Now, this is something that you will see in past papers as well. Sometimes they'll ask you to prove some inequalities. They'll ask you to prove some inequalities, show some inequalities. For example, if you've got something like this, what we have is a block of 7.5 Newton. It's at rest. That means it's in equilibrium. So we've got this force acting 7.5 Newton acting in the downward direction. And we have its components, this direction and this direction. We've got reaction. And the force that you are applying on this is acting in this direction. 7.2 Newton, you're applying a force in this direction, up the plane. Now, because of this force, they're saying the object remains at rest. It does not move. It does not move. Okay? It remains at rest. That means it's equilibrium. Now, if it is equilibrium, the opposite forces are supposed to be equal to each other. What are the forces that we've got? We've got 7.2 acting towards right. We've got reaction here. We've got weight component here. The other weight component is here. Now, first question is, where does friction act? You will have to check whether 7.2 is bigger or 7.5 sine alpha is bigger. In this case, we are given this value, given the value of tan alpha, we can use that to find sine alpha. I've done it here. If you have tan alpha given using a right angle triangle, you can figure out what sine alpha is, not cos alpha is. You would have to figure out which of these forces is bigger, 7.2 or 7.5 sine alpha. If 7.5 sine alpha is smaller, in this case that's smaller, and 7.2 is bigger, where does friction act? Friction is going to act opposite to that acts in this direction. And now, since we know the direction of friction, we just equate the opposite forces and we say, since it's equilibrium, opposite forces have to be equal to each other. So left forces equal right forces, upward forces equal downward forces, and that gives us the value of friction as 51/10, the value of reaction is 36/10. And now notice, we have to show this inequality. Mu is greater than or equal to 17/24. How can we show this? Remember, we talked about this. When we have equilibrium, in equilibrium, F is less than or equal to mu r. When you do not know whether the equilibrium is limiting or non-limiting, and you have to prove an inequality, F is less than or equal to mu r. F represents friction here. F is less than or equal to mu r in this case. So once you have the value for F, that's 51/10. Value for reaction, that's 36/5. Then we say F is less than or equal to mu r. Input values in this, and you get the result from that inequality that they wanted us to prove. So when you have equilibrium and they want you to prove an inequality, know that you would have to use F less than or equal to mu r. In the second case, they say, when the force acts down the plane, so now the force is acting in this direction. the block slides downwards because now it has the weight component acting in this direction as well, and the 7.2 Newton force acting in this direction as well. Friction is going to oppose that acts in this direction. Now they're saying it's sliding downwards. Show that mu is less than 31 over 24. Now, when the object is moving, when it's equilibrium, we know F is less than or equal to mu r. When the object is moving, the direction in which the object is moving, that is going to be uh, the forces acting in that direction, they're going to be greater than the forces acting in the opposite direction. So forward forces, they will be greater than the backward forces when the object is moving. Now, if the object is sliding down in this direction, what that means is these forces have to be bigger than friction. That is when the object will slide downwards. So that's what we can use to find out another inequality in terms of mu. We can say, in this case, forces acting towards the left side, they should be greater than the forces acting towards the right side because the object is moving towards the left side. So 7 sine alpha, 7.5 sine alpha plus 7.2, that should be greater than friction. Put F equal to mu r. Why? Because it's in motion. In motion, we know the value of friction is equal to mu r. Simplify this and you get an inequality in terms of mu. These forces are still going to be equal to each other. R and 7.5 cos alpha, they're always going to be equal to each other. Perpendicular forces on a surface, they're always equal. These two are always equal. But along the surface, since the object is moving down the plane, we say these forces are greater than friction. And that gives us that inequality. Mu is less than 31 over 24. So when you have to prove inequalities in equilibrium, F is equal to mu r. When an object is moving, when it's moving, you say the forward forces are greater than the backward forces. Forces acting in the direction of motion, they should be greater than the forces acting uh, opposite to the motion. Is that okay? So in whatever direction, forces the object is moving, forces acting in that direction have to be greater than the forces acting in the opposite direction. So basically, the idea is forward forces have to be greater than backward forces. Okay. In this case, forward direction is this direction. That's the left direction. That has to be greater than this direction. Okay. And that gives us the other inequality. Okay, let's move on. Now, sometimes what happens is they ask you to find something like this. Find the two values of T for which this is in limiting equilibrium. So we've got a set of forces here. We've got this force T acting here. And we've got weight, we've got friction, we have normal reaction. Okay. We've got these forces acting. And they're saying we've got weight acting here, that's 20 Newton. That's the weight. If we have a rough vertical rod, there's going to be friction because of that as well. And we have to find the two values of T for which the ring is in limiting equilibrium. Now, these are the forces that are acting. We've got tension acting in this direction. What are the components of tension going to be? One in the right direction, one in the upwards direction. Now, because of this tension having a component to the right side, there will be a normal reaction towards the left side, perpendicular to the surface. What about friction? Do we know the direction of friction? T sine 30 is acting in the upwards direction. 20 Newton is acting in the downward direction. Which one of them is bigger? We don't know. Because this is T, we don't know what that value is. If T sine 30 is bigger, then friction would act downwards. If T sine 30 is smaller, then the friction would act in the upwards direction. So direction of friction is not clear in this. And they're asking us to find the two values of T for which this is in limiting equilibrium. What does that mean? We will consider two cases here. One case in which the ring is in limiting equilibrium such that it's just about to move up the plane, move down the plane in this case. And the other case in which it's limiting equilibrium such that it's just about to move up the rod in the upwards direction. When it's about to move downwards, where does friction act? That acts upwards. When it's about to move upwards, friction acts downwards. So we consider these two cases and we find the value of T from that. And that gives us the two possible values of T, one in this case, the other in this case. These are the two values of T for which the ring will be in limiting equilibrium. Now, understanding the meaning of this is very important. The ring is in limiting equilibrium when T is equal to 68.5 Newton. When it's just about to move up, it means if the force T was even slightly bigger than this, the ring will start moving upwards. The ring is in limiting equilibrium with a value of T equal to 28.3 Newton, and it's just about to move downwards in this first case. If the force acting, this force T, if it was even slightly smaller than this, the ring will start moving in the downward direction. So these are the extreme possible values of T that we have: 28.3, 68.5. If you have 28.3 Newton, you have limiting equilibrium with the ring just about to move down. If you have 68.5 Newton, you have limiting equilibrium with the ring just about to move up. Between these two values, if the tension is between these two values, between 28.3 and 68.5, in the middle region, the ring is going to be in equilibrium, but that's going to be non-limiting equilibrium. So whenever tension is between these two values, we are in equilibrium. Towards the left side here, the object will start moving downwards. Towards the right here, the object will start moving upwards. So these are the minimum and maximum possible values of T as well, for which the ring will remain in equilibrium. So this question comes in multiple forms. In this case, they're saying find the two values of T for which the ring is in limiting equilibrium. Sometimes they would say find the maximum possible value of T for which the ring will remain in equilibrium. In that case as well, you would consider the limiting equilibrium with the ring just about to move upwards. That will give you the maximum value. They'll ask you to find the least possible value of T for which the ring remains in limiting in equilibrium. You would say, in that case, the ring is just about to move downwards, and that will give you this case. So when you have to find greatest or least possible values of a force, in case of friction, you consider limiting equilibrium cases, and that will become clearer in this example as well, in the next examples. You have a very similar situation. You've got a set of forces, and they want you to find the set of possible values of a force P that is acting in this direction, such that the particle remains in equilibrium. Okay. Now, let's look at the forces that are acting. We've got weight acting downwards, 6 Newton. We've got 6 sine 25 acting in this direction, P Newton acting in this direction. Sorry, the components of weight, they are 6 sine 25, 6 cos 25. We've got P Newton acting here. We've got reaction acting here. Now, first of all, which direction does friction act in? We don't know, because that will depend on whether P is bigger or 6 sine 25 is bigger. Any of them could be bigger. We want to find the set of possible values of T for which the ring remains in equilibrium. We consider the extreme cases, the two extreme cases. One extreme case in which the ring is just about to move up the plane, and the other extreme case when the particle is just about to move down the plane. Those extreme cases. So we consider limiting equilibrium with the particle just about to move down the plane. We consider limiting equilibrium with the particle just about to move up the plane. We consider these two extreme cases. Those two extreme cases give us these values of P. One of them is going to be the maximum possible value of P, the other minimum possible value of P, and we say it's going to remain in equilibrium if P was between these two values. If P goes beyond these two values, then the equilibrium would break. Between these two values, as in this example, as I explained that to you here, between these two extreme values, the object is going to remain in equilibrium. This is the greatest possible value of P for which the particle remains in equilibrium. This is the least possible value of P for which the particle will remain in equilibrium. It's a very similar example to this. You can see that. Find the least possible value of P given that the particle remains in equilibrium. Again, we've got this force P acting in this direction. It has one component here, P cos theta, another component here. If we want to find the least possible value of P in this case, what does that mean? We say the P would be least if it's in limiting equilibrium with the particle just about to move down the plane. So that's what we consider limiting equilibrium with particle just about to move down, slide down. In that case, friction acts in the upwards direction. We equate the opposite forces and find the value of P from that. If we had to find the maximum possible value of P, we would say it's in limiting equilibrium with the particle just about to move up the plane. In that case, friction will act in this direction, and that will give you the maximum possible value of P. It's a very common question, repeated quite often in past papers. So whenever you have to find greatest or least values of any forces, and you have a rough surface having friction, consider using limiting equilibrium. One of those is going to give you the maximum possible value of that force. The other is going to give you the minimum possible value of that force. Okay, now, this is another case in which you're asked to find maximum or minimum possible value of a force. These are from recent papers, last examples that we're doing forces in equilibrium, and it turns out that it's taking a lot of time because I ended up going into a lot of detail, but it's okay. I think that should be helpful. So we have got this question now. It says the diagram shows a mass 10 kilograms suspended below a horizontal ceiling by two strings AC and BC. You can see that on the diagram, the block is in equilibrium. We've got some forces acting on this. We've got a force acting in this direction, that's F Newton. We've got another force acting downwards, that's 100 Newton. That's the weight of the object. And we've got the two tensions, one in this direction, the other in this direction. What I've done is I've just resolved the tensions and equated the opposite forces. In the first part, they said F is equal to 20. If the value of F is equal to 20, we need to find the tensions in each of the strings. What are the tensions going to be in each of the strings? How do you find them? You just resolve the forces, equate the opposite forces, and that gives you the result. In the second part, they ask you to find the greatest value of F for which the block remains in equilibrium in the position shown. Now, what does that mean? If this force F was to become too big, what would happen? The object is going to start moving towards the right side. And when it starts moving towards the right side, you're going to have a situation like this. The block moved towards right. The string on the right side here, this is going to become slack. It's no longer going to be taut. It's going to become slack. So in order to find that maximum value of F for which it will remain in equilibrium, after that, the equilibrium would break. Consider that cutoff point when this force becomes too big. It'll just about to be moving. It'll be just about to move upwards in this direction. The second string is going to become slack, so the tension in this is going to become 0. You'll put that equal to 0, T2 equal to 0, in the same equations. You have the same equations as before. Equate the opposite forces. It's just that the value of F is not 20 anymore. That was for the first part. You equate those opposite forces. And what you do is you put T2 equal to 0, because that would become slack if the force F was to become too big. You put T2 equal to 0, and that gives you the value for greatest F in this case. Okay, whenever a string becomes slack, tension always becomes 0. Yes. Similar to this, sometimes they can also ask you to find the least value of a force in a very similar situation. You have an object hanging from these two strings, and you've got a set of forces acting like this. And what happens is you have to find out the least value of X for which the block remains in equilibrium in this position. Now, think about it. If X becomes very small, you're looking for least value of X, right? If X becomes very small, what would happen? There would be no force keeping this object in its current position. Because of the weight, it's going to start moving downwards. It's going to start moving in this direction because of its weight. When that happens, the tension in the lower string, what is that going to become? How do you know which string becomes slack? Because it's going closer to this string, right? It's closer to this point. So the string's length will be longer, and the object will be closer to this point. So it will no longer be straight anymore. It will be slack. So when the object moves down, in this case, the lower string becomes slack. So what we do is we equate the opposite forces just like before, and we put T2 equal to 0. For X to be minimum, the lower string would have to have a tension of 0 because it would become slack, and that gives us the value of X, the least value of X, that turns out to be 86.6 Newton. Okay, so when again, you have to find greatest and least possible values of forces when you have an object hanging from some strings. When you have an object hanging from some strings. In this case, what you do is you put one of the tensions equal to zero. When you have a rough surface and limiting equilibrium, in that case, what you do is you consider limiting equilibrium. When you have an object hanging and you want to find the greatest or least value of a force so that the object remains in equilibrium, you put one of the tensions equal to zero, depending on which string will become slack. In the first case, if F was to become too big, the object will move in this direction, so this string will become slack. In the other case, the object was supposed to move in this direction. If X becomes very small, so the lower string will become slack. We put those tensions equal to zero, and that gives us the result. Okay, I hope that makes sense. I hope that was helpful. We will stop here. It ended up taking too much time, but that's okay. That's one topic. The other topic is kinematics. That's going to take time, and the rest of them will be fairly quick. Kinematics. This is the next topic that we've got. Now, first of all, in kinematics, you need to know some basic terminologies. There are 6 different quantities that we'll be dealing with here. Distance, speed, time, displacement, velocity, and acceleration. Some of these are scalar quantities, the others are vector quantities. Scalar quantities are those quantities that only have magnitude, they don't have any direction, and they're always positive. Distance, speed, time, they always will have positive values. Displacement, velocity, and acceleration, these are vector quantities. So they can sometimes be positive, they can sometimes be negative. These are vector quantities. Now, the corresponding quantity for distance is displacement in vectors. The corresponding vector quantity for speed is velocity. And we have time and acceleration. These are different from each other. Let's understand them. Distance is fairly straightforward. Distance between 2 points, the length between 2 points. I'm sure all of you understand this. Time is time. What about speed? First of all, speed is defined as distance over time, but it's not just any speed, it's the average speed. Average speed is given by total distance over total time. So if somebody goes from one point to another point and distance is this, time is this, you say the average speed is given by 16.7. That's distance over time. It's average speed. You cannot say that at any particular point the speed was 16.7. It's the overall average. So that's the speed formula. It's the rate of change of distance. What about displacement? Displacement is the shortest distance from a starting point. So let's say you've got an object that starts from A and it goes to the point B and then it comes back to C after that. Now, what's the distance traveled? Now, these terminologies are very important. Distance traveled. Distance traveled is 250 in one direction, 150 on the other direction. And distance plus minus does not matter. So we say it's 250 plus 150. That's 400 meters. That's the total distance that is traveled. If they ask you for displacement in this, what's the displacement? Displacement is shortest distance from the starting point. Now, in this case, since displacement is a vector quantity, we consider the right side positive. If the right side is positive, this is the starting point, and you reach the point C. This distance is 100 meters. You would say displacement is 100 meters towards the right side, or you can say it's plus 100 meters. If they ask you for distance AC, what about that? Distance AC. This is different from distance traveled. Distance traveled is this whole thing, 250 plus 150. That will be 250 plus 150, that's 400. But distance AC, that basically means distance between the points A and C. And that's the same as displacement. That in this case is going to be 100 meters as well. That is not 400 meters. So when they say distance traveled, you add these two. When they say just distance between 2 points, that is just going to be the same as displacement value. But since they're talking about distance here, it's only going to have magnitude and no direction, but the value is going to be 100. Okay, so that's the idea of displacement and distance. If you have something like this, it starts from A and it goes towards right 75 meters, and then it comes back by 100 meters. If you consider the right side positive, you can say the displacement in this case is minus 25 meters, because we're considering the right side positive. From the starting point, the displacement is towards the left side. So that's negative 25. That's the value for displacement that we've got. Okay. Next we've got velocity. Velocity is defined as displacement over time. Again, that's the formula just for the average velocity. Average velocity is given by the total displacement over total time. Now, if you have an object that goes like this from point A to point B and then comes back from point B to point C, the same example as before, if you had to find the average velocity in this, you would say that's the total displacement, that is 100, divided by the total time, that's 25. The average velocity turns out to be 4 meters per second. Average speed, on the other hand, that would be 16 meters per second. These are going to be different values. Okay, they're not going to be the same values. If you want to find velocity and speed at a particular point, for example, let's say you've got a point X here, you've got another point Y here, and we know the velocity, the speed at this point X is 30 meters per second, and the speed at the other point, Y, is 7 meters per second. The speeds are going to be 13 and 7. What about velocity? Velocity will have the same magnitude as well. That's going to be 13 meters per second for the point X, if you consider the right side positive. But it's going to be 7 meters per second at the point Y, because minus 7 meters per second at the point Y, because we're going in the left direction. We consider the right direction positive. The velocity value is going to be negative in this case. It's minus 7. But notice the magnitudes remain the same. They're 13 and 7, 13 and 7 for both speed and velocity. So at a particular instant, the values of velocity and speed, they're going to be the same at a particular instant. However, their average values, they may be different when the object is changing direction. When the object is changing direction, what happens is the distance and displacement are different values. For example, in this case, distance is 400, displacement is 100. So their average velocity and average speed, they're also going to turn out to be different. But instantaneous speed and instantaneous velocity, which were the speeds and velocities at these particular points, they will always have the same magnitudes. Only the plus minus would be different, because velocity can sometimes be positive, it can sometimes be negative. Average speed and average velocity, they're always, they can sometimes be different. Instantaneous velocity and instantaneous speed, they're always going to be the same magnitudes. Okay. What about acceleration? Acceleration is defined like this. It's final velocity minus initial velocity, v minus u over t. This is also the formula just for the average acceleration, or when acceleration is constant. If you know acceleration is constant, or you're looking for the average acceleration, you can use this formula, v minus u over time. For example, if you have an object like this, it starts from point A, goes to point B, its velocity increases from 2 to 5. The change in velocity is 5 minus 2 divided by the time taken. That's 15, and that turns out to be 0.2 meters per second square. So acceleration is the rate of change of velocity, the rate at which velocity changes. So in this case, 0.2 meters per second square. What does that mean? In every second, on average, the velocity is increasing by 0.2 meters per second. If it was a negative value, for example, in this case, it starts from 15 meters per second, ends at 5 meters per second, the acceleration turns out to be negative 0.667. That means every second on average, what's happening is the velocity is decreasing by this magnitude, and we say deceleration is 0.667. So negative acceleration, we can write that as deceleration as well. Okay. Now, this is now the most important part from this discussion, and then we move on to the more relevant part for the questions. This is some basics. These are some basics that you needed to understand before we could actually go to the part on which you get problems. Let's say we have a point here, that's point O, and an object goes from O to A, and then it goes from A to B. It goes like this. Now, think about this part of the journey from O to A. When the object is, for example, at this particular point here, what can we say about the velocity value, and what can we say about the displacement value? Considering that the right side is positive. If the right side is positive, what can we say about the displacement value here. The displacement is going to be positive. What can I say about the velocity value? Velocity is also going to be positive. Why are they both positive? Displacement is the position of the particle from its starting point. From the starting point, the particle is on the right side, so displacement is positive. Velocity is also positive because that's the rate of change of displacement. Displacement is increasing here, so velocity is also positive. The particle is going in the positive direction, the velocity value is going to be positive. When the particle is here on its return journey, when it's going towards the left side here, what about the displacement and velocity values at this point? At this point now, at this particular, sorry, where did that go? At this particular point, the displacement value is still going to be positive. Even though the particle is going towards the left side, the displacement value is still going to be positive because what does displacement measure? Displacement tells you the current position of the particle with respect to the starting point. The starting point was this. The particle is here. From the starting point, it's on the right side, and the right side is positive. So displacement at this point is also positive. Velocity, however, at this point is going to be negative because the particle is moving towards the left side. If it's moving towards the left side, what's happening to displacement? Displacement is decreasing. You're getting closer to the starting point. Displacement is decreasing. Because of that, the rate of change of displacement, that's negative, velocity is negative. So displacement being positive, that does not mean that the particle is moving towards the right side necessarily. It just tells you that currently the particle is on the right of the starting point. That's all that it means. So this understanding is very important. Understanding the positive and negative values of displacement and velocity. Displacement is positive. If the displacement value is positive, what that means is the current position of the object is to the right of the starting point. So in both of these cases, at this point and at this point, the current position of the particle was to the right side. It was on the positive side. It's not a number line. It's not a number line. It's an object moving in the right direction first and then going to the left side. This is the starting point. O is the starting point. It's not zero. It's the starting point O. Okay, it's moving to the right and then going towards left. Now, while it was going towards the right side, at this point, displacement is positive because the object is to the right of the starting point. At the lower point here as well, displacement is positive because it's to the right of the starting point. It does not matter if it's moving towards left or it's moving towards right at that instant. Only the current position matters. If the current position is on the positive side, the value of displacement is positive. And a negative value of displacement means that the current position of the particle is to the left of the starting point, assuming that the right side is positive. So in this case, for instance, if the particle was here at this point, you would say the displacement is negative because the particle is to the left of the starting point, that it's negative displacement. What about velocity? Velocity, its positive and negative values tell you whether the object is moving towards the positive side or moving towards the right side. So direction of motion is only given by velocity. Displacement cannot give you direction of motion because in this case, you saw that direction of motion was towards left side, but displacement was still positive. Okay. Velocity, however, is going to tell you the direction of motion. A positive velocity means that the object is moving towards the right. A negative velocity means that the object is moving towards the left side. So you can see in this part, velocity is positive, and in this part, velocity is negative. And what is the positive and negative value of acceleration going to tell you? That just tells you whether velocity is increasing or decreasing. If the velocity is increasing, acceleration is positive. If the velocity is decreasing, acceleration is negative. So acceleration's positive and negative values, they tell you whether the velocity is increasing or the velocity is decreasing. At this point, for instance, for displacement velocity, displacement is negative, velocity is also negative. If the particle was to go in this direction afterwards, maybe it changes direction again, it goes like this. At this point, displacement would be negative, but velocity would be positive because the particle is moving towards the right side now. Okay, so displacement just tells you about the current position, and velocity tells you about the direction of motion. So only velocity can tell us the direction of motion. If the velocity value is positive, that means the object is moving towards the positive side. If the velocity value is negative, that means the object is moving towards the negative direction. All right. Okay, now let's come to the actual concepts in kinematics after this. These are some basics that we wanted to understand. First of all, these basic terminologies. Let's look at this now. So first of all, now there are three different parts of kinematics. One part is where you have to use constant acceleration formulas. Another part where you have to use differentiation and integration. You will have some equations given, and using those equations, you have to find some values using differentiation and integration. We call that variable acceleration, or kinematics using differentiation and integration. That's the second part. And the third part is graphs of kinematics. There are three different sections that we've got here. First of all, we've got these constant acceleration formulas. These are constant acceleration formulas. There are 5 of these equations. 4 are given in the formula sheet. The first 4, they're all given in the formula sheet. You could remember another one as well that sometimes make things slightly more efficient, although you can do everything with these 4 as well, and you can do everything using this as well. That's also fine. For the last equation, if you want to remember that, since this is already given, you can make this last one by replacing u with v, as in that's just a way to remember. That's how I tend to remember this. In this equation, replace u with v and flip the sign. Replace u with v and flip that sign. Now, there's a background to these equations, where they come from. That's not for a revision class. I'll skip that. So we have these 5 equations. S represents displacement, U represents initial velocity, V represents final velocity, A represents acceleration, T represents time. When can you use these equations? Only when acceleration is constant. These are called constant acceleration formulas, or you can say equations of motion. But remember, they're only going to be used when acceleration is constant. If acceleration is not constant, you cannot use this. This is the condition for using these formulas. Acceleration has to be constant. Yeah, so however you want to remember this, this is how they're given in the formula sheet. This is how they're given in the formula sheet. You can rearrange them as well. For example, this has, sometimes people write it as v square minus u square equals 2as. That's also fine. However, you can remember this. That's okay. They're also given in the formula sheet. Now, these are called constant acceleration formulas. We will be using these formulas to find any missing quantities. For example, in the first equation, if you knew value of u, v, and t, you could find displacement. If you knew the values of perhaps v, u, and s, you could find time from that. So you would have 3 things given and the 4th thing missing. You can find that missing thing using these equations. For example, you have this particle that is going from point A to point B. You've got the initial velocity, that's 2, final velocity, that's 10. Time taken for this is 50 seconds. It takes 50 seconds to go from that initial point to the final point. Now, we want to find the displacement from A to B, and we want to find the acceleration from A to B. How do you do that? Displacement is S. Which equation connects these 4 things? S, T, U, and V. These are the equations that are given in the formula sheet like this. That's the only thing that's given in the formula sheet for mechanics. Everything else you have to memorize. All the other formulas, apart from these 4 equations, you have to memorize. You have these 4 equations given. You can see which connects S, T, U, and V. That's this equation. So you just use that equation, find the value of S from that. For this, you have acceleration that you have to find out. Again, which equation connects A, V, U, and T. You can see which one that is. That's V equals U plus AT. You use that, and that gives you the value for acceleration. Now, sometimes it's more complicated than that. For example, you have the situation in which you are given that a car is traveling at constant acceleration, and it passes through 2 points passes through 3 points A, B, and C. The time taken to go from A to B and from B to C is 5 seconds. This is 5 seconds. This is also 5 seconds. The speed of the car at A is given, that's u meter per second. And the distances are given 55 and 65. We need to find the values of A and U. Now, there are two parts of this journey, AB part and BC part. Now, one way to break this journey down could be like this. You could say A to B part. What do we know about this part of the journey? We know the value for time, that t is equal to 5 here. We know the displacement, that's 55. For the second part of the journey, we know the time is equal to 5 and displacement is 65. Now, in the remaining things, when you have multiple parts of the journey like this, what we want to do is we want to write down everything that we know. First of all, these are the things that we know, time and displacement. And then we need to basically identify what other quantities are common, what other quantities are common between these two parts of the journey. Now, what's common? There's acceleration that is common. Acceleration for both of them is same. So we can say if acceleration in AB part is A, and this part of acceleration is A, and the next part as well, this is going to be A. But then for the other quantities, final velocity is not common, and also initial velocity is not common. So the other two quantities are not common. That means we would have too many unknowns. If we consider this initial velocity as U and the other, we consider that something else, that will be a different value, right? Let's call that UBC. We have 3 unknowns. That will be too many unknowns. You would find it very difficult to find those unknowns using these equations. You'll have to solve 3 simultaneous equations. That becomes too complicated. When you have different parts of the journey like this, we want to make sure that we only have 2 unknowns. 3 unknowns is going to be too many. So breaking the journey like this, AB to BC is not helpful here. Instead of that, we do something like this. We say, let's break it like this. We consider A to B part of the journey and A to C part of the journey, because that will ensure we know the time and displacement for both of them. But then the other two other quantities, one is acceleration and the other is initial velocity, they remain the same for both of them. And that will reduce the number of variables that we've got. You only have 2 unknowns here, and both of them are common with each other. We can make 2 equations from them, solve them simultaneously, and find the values of U and A from this. So whenever you have multiple parts of a journey like this, what you want to do is you want to write down all the information that you have already, and then the missing information, try to connect the other quantities, try to find out which quantities are common. So in this case, if you break the journey like this, initial velocity becomes common because that will be the velocity at the point A, and the acceleration was constant throughout. So that's the other common quantity. So we use 2 separate equations here. S equals ut plus half at squared. In both of them, we get 2 simultaneous equations, solve them simultaneously, and we get the result. Similarly, if I will do that example later. So this is one case where you have to connect objects like this. We have to connect 2 equations like this. Okay, let me repeat that. So basically, what we're saying is, if we have multiple parts of the journey like this, you want to first write down all the information that you have for both of those parts. And then for the remaining things, for example, we have U left, we have A left, we have V left. We have U, A, and V left here. We want to write down those quantities that are common between them. They are common between them. Okay. So in this case, final velocities are going to be different, but U and A are common between them. We use those quantities, U and A, because that's going to reduce the number of unknowns that we have. And that's why we break the journey like this as well. We go from A to B and then from A to C, because that makes sure that the initial velocity value is U for both of them, and this is A for both of them, and we avoid having too many unknowns. If we were to use AB and BC, that would be problematic, because even if you say this, that the final velocity of the first part, that is velocity at the point B, that is the same as the initial velocity at for the second part, that's equal to VB. The problem is that's not what we're looking for. We're looking for this initial velocity. How do you find that? That will make it even longer. So you'll first find the value of VB, you'll find the value of A, and then you'll make another equation to find the value of U from that. Right? So that's not going to help. That's going to make it longer. That will be very inefficient. So you want to make two equations such that you get only two unknowns, not more than two unknowns. Otherwise, it becomes fairly lengthy. This is one case where you have to think about this. We will see examples in which sometimes what happens is you've got two separate objects. You've got two separate objects, and they are moving in different directions or in the same directions. And we have to consider what happens when they collide, for instance. In that case as well, the quantities that we know, we will write them first. And for the other quantities that we do not know, we will need to find what quantities are common between them. Okay. We'll come to those examples after we discuss free fall. So constant acceleration formulas, they can either be used when the question explicitly says that acceleration is constant. That's one case, because acceleration has to be constant for us to be able to use those equations. But there's some cases for which you need to remember that acceleration is constant. They will not tell you that. For example, you have motion under gravity. Motion under gravity. What's motion under gravity? When weight is the only force acting on an object in the direction of motion, when weight is the only force acting, we call that motion under gravity. There are two types of this. One is free fall. Free fall is when an object is in vertical motion. In vertical motion in the air like this. In vertical motion like this. In this case, the value of acceleration is always going to be 10. It could either be plus 10 or it could be minus 10. One of these two. Either plus 10 or minus 10. We'll see how to figure that out. But since it's a constant, we can use constant acceleration formulas in this case when we have free fall. Vertical motion with weight as the only force. No resistance, no nothing. In this case, we call this free fall. Now, what happens when an object is in free fall? So let's say we have this object, we projected it upwards from this point at a speed of 15 meters per second. Okay. Now, when it goes upwards, it will reach a maximum point somewhere, then it'll come down. We need to find, for instance, the maximum height reached by the particle or the time taken until the particle hits the ground. How can you find these two things? Now, when it's projected upwards, we can consider the upwards direction as the positive direction. Now, we will discuss how to take directions in some time as well. But for now, just trust me that we're taking upwards positive. Okay. And we will do that throughout the journey. This is very important. Do not break your journey into two parts like this, that you say, while we're going upwards, take this positive, while we're going downwards, take this positive. That will make you do a lot of sign errors in more complicated questions. Plus minus errors, you'll end up getting negative values of time. You'll end up getting some positive value where it was supposed to be a negative value, and that will confuse you a lot. Do not change the positive direction mid-journey. Consider the same direction positive throughout the journey. For example, in this case, the particle was projected upwards. What we're doing is we're taking upwards direction as positive. Now, if upwards direction is positive, the particle was projected at 15 meters per second. What happens is at the top, it's going to come to instantaneous test. At the top, the velocity is going to be 0. Now, while it's going up, its velocity will reduce gradually. So from 15, it'll become 14, 13, 12, 11, 10, and so on. So let's say it becomes 10 here, it becomes 5 here, and eventually becomes 0 at the maximum point. Now, when it comes back, remember the upwards direction is positive. When it comes back, at this point, the velocity is going to be negative 5 because it's going downwards now. We were considering upwards direction as positive. So velocity is going to be negative now. At this point, the velocity is going to be negative 10 meters per second. And then when it hits the ground, it's going to be negative 15 meters per second, the same velocity from which it was projected. So you see throughout the journey, what's happening is the velocity is decreasing. It started from a positive value, it started from 15, then went to 10, 5, 0, and then again, it's still decreasing. It's going to minus 5, minus 10, minus 15. Acceleration is rate of change of velocity, not rate of change of speed. So velocity, you can see, is decreasing throughout this journey. Velocity is decreasing. It's going from 15 to 0 and then to minus 15. Throughout the journey, the value for acceleration here is going to be negative 10. throughout the journey. The acceleration value is going to be negative 10. If you consider upwards direction as positive, remember this acceleration is because of gravitational acceleration. Gravitational acceleration we know is 10 meters per second square. If you are taking upwards direction as positive, gravity acts downwards. That's opposite to the direction that you've taken positive. In this case, the value for A is going to be negative 10. When you're taking upwards positive, the value for A is going to be negative 10 here. When you're taking downwards positive, in some cases, we'll see later, when we take downwards positive, in this case, we're not taking downwards positive at all. Throughout the journey, we're taking upwards direction as positive. But when we take downwards positive in some cases, in that case, gravity also acts downwards. In that case, the value of A that we take will be 10 meters per second square. The sign for A here, positive 10 or negative 10, that does not depend on which direction the object is moving in. The object can be moving upwards, it can be moving downwards. That does not define whether that does not determine the plus minus sign here. The only thing that determines this plus minus sign is the direction that you've taken positive. If you have taken upwards positive, A is minus 10. If you have taken downwards positive, A is plus 10. That's the rule. Okay. So now let's go back to that example. We threw this object upwards. We had to find the maximum height of the particle. Now we know at the maximum height, the velocity is going to be 0. We can say initial velocity was 15. Final velocity was 0. Acceleration is minus 10. Why? Because we're taking upwards positive. And we can find the value of displacement from this. Which equation connects these four things? 2as equals v square minus u square. This equation, that gives us the maximum height. If we had to find the time taken until the particle hits the ground, time taken until the particle hits the ground, there are two ways of doing this. One possibility is that you find the time from A to B and then just multiply that by 2. Or you could do it directly as well. You could say, we know that the initial velocity is 15. That's what it was projected at. The final velocity is minus 15. So you take final velocity is minus 15. And we know that the value for A is minus 10. And we also know displacement now, if it reaches back at the same point, the displacement is also 0. So for the whole journey, we know 4 things. We know initial velocity, final velocity, displacement is 0, acceleration is minus 10. What we can do is we can use any of the equations that have time in them. And that is going to give us the value for t here. That turns out to be 3 directly. You could do it directly like this as well without even breaking it down. You can do this. Why? Because throughout the journey, we know that the value of acceleration is going to be negative 10. We're not going to change that in the middle. That remains negative 10 throughout the journey because we're taking upwards direction as positive. Acceleration remains negative 10 throughout. Yes, so when we take upwards positive, velocity is decreasing throughout. That's why acceleration is negative 10. When we're taking downwards positive, then while the object is, when we take downwards positive, then the velocity will be increasing throughout, so acceleration will be positive. Okay, but you have to remember this now. If we're taking upwards positive, gravity is acting downwards, opposite directions, A is minus 10. When they're in the same directions, then A is equal to plus 10. All right. Okay, now that's one case in which acceleration is going to be constant. Free fall, vertical motion. Now, another case, it also comes in motion under gravity, and that is when you have a smooth inclined surface. Inclined surface that is smooth, like this. And there's a particle that is moving along the surface. In this case, acceleration is given by 10 sine theta. Now, it comes from Newton's second law of motion, but it helps to just remember this directly. Remember, gravitational acceleration in the vertical direction is 10 meters per second square. This is also a vector. Acceleration is also a vector quantity. So that's like we resolve forces. If we have an object moving along the surface like this, what we can do is we can say, okay, in the downward direction, vertical downward direction, the acceleration was supposed to be 10. What would its value be along the surface? What's the component of 10? Component of 10 in this direction is 10 sine theta. If the angle of inclination is theta, that component is 10 sine theta. That will be the acceleration that we have here. In what case? When it's a smooth inclined surface, that means no friction, and weight is the only force along the surface. Yes, there's normal reaction there, but that's not contributing to motion. That's perpendicular to the direction of motion. So that does not really impact the motion in any way. Along the motion, there is only one force, and that's the weight component. In this case, acceleration is given by 10 sine theta. We know the value directly, that's 10 sine theta. We can use that directly. If you had some other forces, for example, you had friction, there was some other force acting here, maybe of 15 Newton, then you would have to resolve the forces, use Newton's second law of motion to find the value for acceleration. But in a lot of cases, you have this, that weight is the only force and it's a smooth inclined surface. Acceleration in that case is just given by 10 sine theta directly. Okay, so that's something that you need to keep in mind. That's the other possible case in which acceleration is going to be constant. Motion in the gravity, free fall, or on an inclined surface, when weight is the only force, acceleration in this case is 10 sine theta, and the previous case was 10. Now, how do we decide which direction to take positive and which direction to take negative? So that's, again, a very important thing. Otherwise, you'll do a lot of mistakes. When you have an object that is moving in only one direction, when you have an object moving in only one direction, for example, if you have this object and it's moving towards the right side, and it's only moving towards the right side, you take right side positive. If you have an object that's only moving towards the left side, like this, you take the left side positive. So if it's a single direction motion, object is moving in only one direction, you take that direction as positive. If it's moving upwards only, you take upwards positive. If it's moving downwards only, you take downwards positive. If it's a single direction motion, you take that direction as positive. But if it's like this, that the particle goes to the right and then it comes back as well, then throughout the journey, you take right side positive. Even if it's like this, it's going towards left first and then it's going right. If it's two-way motion, you take right side positive in horizontal direction. If it's vertical motion, two-way motion, upwards and downwards both, you take upwards positive. However, remember, do not change it in the middle. Do not say that while it's moving here, I'll take this positive, then it's moving here, I'll take this positive. No, don't change that. Unless, of course, the journey breaks because of some reason. Sometimes you have collision happening. So if there was a collision happening here at this point, then these are two separate journeys. This is separate and this is separate. In that case, you can take different directions as positive. But if it's the same acceleration throughout, then you would not change the positive direction. You would keep one direction positive and keep that the same throughout the journey. So what's the takeaway from this? Number one, how do you choose positive direction? For each object, first of all, keep one direction positive throughout the journey. Do not change that in the middle of the journey. Keep one direction positive throughout. If the object is moving in only one direction, you take that direction as positive. If it's moving towards right, you take the right positive. If it's moving towards left, you take that positive. Upwards, you take upwards positive. If it's moving downwards, you take downwards positive. If the object changes direction during motion, in that case, what you do is you use what you do in a Cartesian plane normally, XY plane, XY axis, right positive, left negative, up positive, down negative. If it's two-way motion, you do that. Throughout the journey for one object, you will not change the positive direction. If you have multiple objects, for one object, you can take one positive. For the other object, you can take another positive. That's all right. But for each of them, you will keep that direction positive throughout them. You will not change that in the middle. Okay, let's have a look at some examples now. Let's say we got this. We have a particle that's projected vertically upwards from a point O with initial speed 12.5 meters per second. At the same instant, another particle is released from rest at a point 10 meters vertically above O. So you've got this point A that's projected upwards, 12.5 meters per second. You have another particle here that's released from rest at 0 meter per second from rest. Now, what happens is, at some point, the particles meet each other. I'm calling that point X here. And they were initially at a distance of 10 meters from each other. Now, what do we know about each particle? A is moving in the upwards direction, B is moving in the downward direction. So for A, what I do is I'm taking upwards positive. For B, I'm taking downwards positive, right? Because A is moving upwards, B is moving downwards. Now, what's the initial velocity for A? That's 12.5. Acceleration for A, what would that be? That will be negative 10 because upwards is positive, gravity acts downwards. A is negative 10 for this. These are the only two things that we know for A. What about B? B is moving downwards. Initial velocity is 0. Acceleration value, that's positive 10 for this because we're taking downwards direction positive for it. What do we do now? We've got two things known for both of them. Now for the remaining quantities, what's remaining? We've got final velocity, final velocity, displacement, and time. We need to think about how we can connect these two journeys now. Is there anything that's common between them? Both the particles started at the same time instant, and they're colliding with each other. That means from their starting point until when they collide with each other, their times taken are going to be the same. So whatever is the time taken by A, that's going to be the same time taken by B as well. So we can connect them by time. We say the time for both of them is T. Both of them have time T. Can we connect anything else? We have something known about the displacement. What's that? If B is moving SB downwards and A is moving SA upwards, what's their sum supposed to be? The total distance is 10 meters. SA plus SB, that should equal 10. So that's the other variable that we choose to use here. That's displacement. And now we have this equation. We use this equation to find the value of T. That gives us the value for T. And once we have that, we were looking for the height above O at which the particles meet. That's SA. Input that value here, the value for time here, and that will give you the result. That's the height at which the particles meet. So look at the positive and negative direction. For A, we take upwards positive. For B, we take downwards positive. And then we look for the quantities that are common between them. Okay, now let's have a look at this. There's a particle P that's released from rest at a point on a smooth plane. Incline at 30 degrees to the horizontal. Find the speed of P when it travels 0.9 meters. That's really straightforward. But the key thing to note here is we know it's released from rest. Initial velocity is 0. Displacement, 0.9 meters. And we don't have any other information. But we know it's a smooth plane. It's a smooth plane and the particle is released from rest. That means weight is the only force that is making the object move down the plane. If weight is the only force, remember, what's the acceleration going to be? Acceleration is 10 sine theta. The angle of inclination of plane is 30 degrees. So we say acceleration, therefore, is going to be 5 meters per second. Since the particle is moving down the plane, we take that direction as positive. It's single direction motion. We take that direction as positive. Gravity also, the weight component also acts in this direction. And that's also the positive direction. So acceleration value here is going to be plus 10 sine theta. And that gives us the acceleration. We can find the final velocity from that. So you see, this is very helpful to remember. Smooth inclined surface, where weight is the only force, remember, acceleration is given by 10 sine theta. Let's take another example here as well. In the first part, they ask you for finding the deceleration. That's straightforward. You have three things given. You can find the value of A, and then say the deceleration is 0.5. Acceleration is minus 0.5. The deceleration word already incorporates the negative sign. So when we say deceleration, that will just be 0.5. What about acceleration now? What about the value of alpha now? They're asking you to find the value of this angle. How do you do that? It's a smooth plane and there's no other force acting apart from the weight component. There's no other force acting apart from that. That means acceleration is supposed to be 10 sine theta, right? But since the particle is moving up the plane, we're taking that direction as positive. The weight component is acting in this direction. It will be minus 10 sine theta. We equate minus 10 sine theta with minus 0.5, and that gives us the value for theta. Again, smooth inclined plane with weight as the only force, acceleration is given by 10 sine theta. Let's consider this example. You've got particles P and Q that are projected vertically upward from different points on horizontal ground with velocities of 20 and 25. Now, this is time delay. So these are basically time delay problems. Just write that here. So sometimes we'll see in questions, you have two particles and one starts its journey earlier than the other one or later than the other one? How do we deal with problems like these? In the first part here, they're saying find the time for which P's height above the ground is greater than 15 meters. So what does the journey of P look like? It goes up and then comes down. At some point, its height is going to be equal to 15. That's this point. Its height is equal to 15. For what time does the height remain greater than 15 meters? What we can do is, we can say initial velocity is 20, acceleration is -10, displacement is 15. Find the value for time when the displacement is equal to 15. And that turns out to be two values of time. Time equals 1 and time equals 3. That means while the particle was going upwards, its velocity became 15, first of all, when time was 1, and then it became again 15 when it came down at time equals 3. So what's the time interval for which the velocity was, for which the displacement was greater than 15? That's 2 seconds, 3 minus 2. That's the time duration that we've got. Now that's the relatively easier part. Now the second part says, find the velocities of P and Q at the instant when the particles are at the same height. Now P and Q are projected from different points on the ground. So we've got particle P here, and we've got particle Q here. They were both projected in the upwards direction. Speed for one is 20 meters per second. For the other is 25 meters per second. And they're saying, find the velocities at the instant when the particles are at the same height. Now, what do we know about these two particles? We know their initial velocities. They are 20 and 25 respectively. We know their accelerations. They are -10 and -10. For both of them, we're taking upwards positive. So they are -10. Now, the problem is, what other variables can we connect them by? Displacements. If they're at the same height, their displacements are going to be equal to each other. That's one thing. And we're also given something about time. They are saying Q is projected 0.4 seconds later than P. So Q was projected later. If we consider the time for P as T, the particle that was projected later, we would consider that time as T minus 0.4, not plus 0.4. The particle that starts late, we would consider its time to be less than that of the other particle. Why is that? Think about it. If you have two friends going from one point to another, one starts at 10 p.m. and it reaches the other point at 11 p.m. How much time does it take? 60 minutes. The other starts later. The other starts at 10:15 p.m. The other starts at 10:15 p.m. And he or she reaches the other point at 11 p.m. as well. So they are reaching the same point at the same time instant. But one started late. The one that started late, that took less time. It went at a greater speed to reach that same instant. So the delay was overcome due to more velocity, yes. And the time reduces because of that. So the one that starts late, it takes less time if it is reaching that final point at the same instant. If both of them are reaching at 11 p.m. and one started late, the one who started late, they took less time. That's the idea that we're using here. At some instant, they are at the same height, whatever that instant is. It'll be some value of t here. One of them started at t equals 0, the other started at t equals 0.4. So the one that started at 0.4, that takes less time until that time instant. So if you're considering the time for p as t, the time for q, that will be t minus 0.4. Okay. If we consider this as t, then this would be t plus 0.4. Either of them is going to work. Now, since their displacements are supposed to be equal to each other, we just connect them using an equation like this. That gives us the value for t. Once we have the value for t, we can find the final velocities after that, remembering that the time taken by p was t, and the time taken by q would be t minus 0.4. And that gives us those final velocities that we were looking for. Okay. All right, let's move on. Next thing you have is kinematics graphs. Graphs of displacement time functions and velocity time functions. You'll have to draw these graphs sometimes. You have to interpret these graphs. Okay, you have to sketch these graphs and also interpret these graphs. When you have a displacement time graph, you need to remember, so if you have these three quantities, displacement, velocity, and acceleration. You have these three quantities. As you go from left to right, from displacement to velocity to acceleration, the gradient of the displacement time graph is going to give you velocity, because velocity is rate of change of displacement. Gradient of displacement time graph gives you velocity. Acceleration is rate of change of velocity. So gradient of velocity time graph, that gives you acceleration. And if you go the other way around, if you have a velocity time graph, the area under the graph, that gives you displacement. These are three things that you need to remember. For a displacement time graph, gradient represents velocity. For a velocity time graph, gradient represents acceleration, area under the graph represents displacement. The area under the graph for a displacement time graph, that does not represent anything. Okay, that does not represent anything. Okay, we'll come to that at the end. Okay, at the end when we're done with kinematics and the break, I can come back to that again. Okay. All right, displacement time graph. Displacement time graph. Let's say we got a displacement time graph here. You need to understand what happens at different points in this journey. You can have a look at this table. At what point and what part of the journey, what is happening from O to A, from A to B, from B to C, from C to D, from D to E. Look at these, the values of displacement, whether they're going to be increasing, decreasing, or constant. Similarly, for velocity and acceleration, what can we interpret for each of these graphs? You can have a look at this. In this region, displacement is positive. And in this region, displacement is negative, right? That's the quantity that you have in the vertical axis. Gradient of this graph represents velocity. So velocity is constant here because it's a straight line. Straight line have constant gradients. It's zero here because the gradient is zero. The velocity is negative here because the gradient is negative, and it's decreasing as well. It's becoming more steep in the negative direction. And similarly for the other ones, you can see that here. What about acceleration? Acceleration is the rate of change of velocity. So when velocity is constant, acceleration is going to be zero. When it's zero, then also acceleration is zero. When the velocity is decreasing, acceleration is negative, and so on. Okay, have a look at this. We can't go into a lot of detail here, but this is important. From this graph, what you interpret is the direction of motion. If the particle starts from O, from O to C, sorry, from O to A, the object is going in one direction because its displacement is increasing. And then A and B are the same points. At that point, it's at rest. And then from B to C, what's happening is it's coming back to the same point that it started from, because displacement at C becomes zero. So B to C part is when the particle comes back to its initial point, which was this point here. And then okay, then what happens is from C to D, the displacement is becoming negative. What that means is the object is going in the other direction now. It's going towards the left side if the right side is positive. And then it's coming back to the same point again. Okay, so that's what the journey would look like. It's going in one direction first, and then going in the other direction, passing through the starting point, and then coming back to the starting point again. Compare this with a velocity time graph that looks like this. In a velocity time graph, gradient of the graph represents acceleration. So you can see what happens to velocity, displacement, and acceleration in each of these parts here. You can have a look at this. The y-axis represents the velocity value. Gradient represents acceleration, and the area under the graph, area between the graph and x-axis, that represents displacement. Displacement will be positive in this region. It'll start decreasing in this region. It'll be coming back towards zero. I'm sorry, one note is causing some problems here. Okay, so that's the idea. Now, this is important, understanding when the direction is changing in this velocity time graph. So in a velocity time graph, when the velocity is positive, it's positive in all of these regions, right? Because it's above the x-axis. From O to C, the particle is going in one direction. It's going towards right side, if the right side is positive. C is the point at which the direction changes. And that's the point when velocity is equal to zero. And that's important to remember. We will see that later again as well. When you have to figure out the change in direction of motion of an object, we check what happens at v equal to zero. So when v is equal to zero, that is the point when the direction changes, because the particle is going from positive velocity to negative velocity, or from negative to positive. That means the direction is changing. So at c, the direction changes and the particle starts coming back to its starting point, but it does not reach the starting point because this area was more. So it traveled more in the positive direction, and then on the way back, it traveled less. So it does not reach the starting point again. That's what the journey looks like. Okay, so that's the interpretation of this graph. Now, for more details, you can have a look at this table if you want. That tells you what happens in every single part of this journey. Okay. Now we'll have a look at a couple of questions on that. But this is the third part of kinematics, and that is kinematics involving differentiation and integration. We also call this. So the question is, does the object stop at this point C? Not necessarily. It's coming, so it's stopping instantaneously. It's just like when you throw an object in the upwards direction. At the stop point, it comes to instantaneous rest. Its velocity is going from positive to negative, so it comes to instantaneous rest. When the direction changes, there's instantaneous rest at that point. So it's not just stopping altogether. It's coming to instantaneous rest because the velocity is going from positive to negative, or from negative to positive. Now, this is the next part of this topic, and that is constant acceleration. That's variable acceleration, kinematics involving differentiation and integration. Whenever you have a function given for displacement or velocity or acceleration, for example, this, do not use constant acceleration formulas. Do not use constant acceleration formulas because they will not work in this case. In most of these cases, those formulas are not going to work because they only work when acceleration is constant. And in most questions that involve these equations, acceleration is not going to be constant. So you don't use those formulas. Now, from those graphs that we discussed, remember the gradient of the displacement line graph that used to give you velocity, gradient of velocity line graph that used to give you acceleration. So how do you find gradient for a curve or for any function? By differentiation. So derivative of displacement is velocity, derivative of velocity is acceleration. If you want to go the other way around, area under the graph, how do you find area under the graph? Generally using integration. If you remember P1 integration, so area under the graph, that corresponds to integration. So when you have to go from acceleration to velocity, you have to integrate. When you go to velocity to displacement, you have to integrate. So if you have any function like this, for example, you've got this displacement function and you want to find velocity, what do you do for that? You differentiate that. If you have to find acceleration from that, again, you differentiate that. You get acceleration function from that. If you have a velocity function, and what you have to do is you have to find the displacement function for that in terms of t. Now, when you integrate, you have to remember you always have a plus c. Whenever you do integration, do not forget plus c. So when you do go from velocity to displacement, you have to integrate there. When you integrate, you would also have a plus c. And for finding the value of that c, you'll have some information in the question that you can use. For example, they might give you that at time zero, displacement was zero. Or you might be able to interpret that from the question statement. If the particle is starting from O and its displacement is also measured from the point O, that means initially its displacement was zero. In that case, you could input t equal to zero and s equal to zero, and the value of c will turn out to be zero. But it's not always going to be zero. Sometimes the value of c could be some other value as well. You always have to find that out. If we have this velocity function, v equals 6t squared minus 12, and we want to find the displacement function from this, we always have a plus c. Whenever we integrate, we always have a plus c there. Okay. And for finding the value of c, we'll have some information given in the question that we can use. The c would represent the displacement of the particle in the very beginning at time equal to 0, only for a function that looks like this. Sometimes you can have functions that have t in the denominator. So you might have, for example, something over t like this. In that case, that's not the same interpretation. It might mean something else. So we can't generalize this that c will always mean the displacement at the starting point. We'll have to input the value of t and the displacement at that value to figure out what the value of c turns out to be. Okay, all right. Then sometimes they ask you something like this. For example, you have this displacement function and they want you to find the time instant when the particle is at rest. At rest means its velocity is equal to 0. So you find the derivative of displacement function that gives you v equal to 10t minus 2. Put v equal to 0 and that gives it the time value. That's the time instant when the particle is at rest. So at rest means velocity is equal to 0. Okay, now this is important. Let's say we've got this velocity function and they want you to find the displacement of the particle from time equals 3 to time equals 8. So they want you to find the value for displacement, from one point to another. This is the velocity function. We want to find displacement from t equals 3 to t equals 8. How do you do that? You integrate the velocity function. When you integrate that, that gives you the displacement function. And then what you can do is you can input limits from 3 to 8, and that will give you the displacement for that. Now, why is that? Because think of it like this. It's a function that's a quadratic function. In this part, it's going to look like this. Area under the graph, area under the velocity time graph, that gives you the displacement. This is the area that we're looking for. How do you find this area? You integrate the function with these limits from 3 to 8. So that's what we're doing. We have the velocity function. We integrate that velocity function. Integration gives us displacement function. And we input these limits from 3 to 8 in that. And that gives us the displacement from time equals 3 to time equals 8. And that turns out to be this value. Now you have to make sure that you show this step in which you're inputting limits. So when you integrate, you have to show this step, and then you have to input limits and show this step as well, where you're inputting these values of t in this. Once you're inputting 8, and then you're inputting 3 like this. So for displacement value from one point to another, you can use limits like this. Consider this example. You have a particle going from, you have this velocity function, and you want to find this displacement value from time equals 0 to time equals 10. What you do is you integrate velocity, input these limits 0 to 10, and that gives you the displacement from this point to another. I'll answer your question, Dina, in just a few minutes. It's coming. V equals t square minus 11t plus 24. It's the same function that I wrote above there. In the previous example, we had to find the displacement. The displacement turned out to be 23.3 there. Now, if they say find the distance traveled by the particle during the first 10 seconds of its motion, distance traveled during the first 10 seconds. How do you find this? Distance traveled. Remember the difference between distance traveled and distance between 2 points. Distance between 2 points is the same thing as displacement. When they ask you for distance traveled, in that case, now it could be like this, that the particle starts from t equal to 0 and then goes here and then goes here and then goes here. The displacement it's turning out to be 23.3. That means from the starting point to the end point, this displacement, this is 23.3. But is that the same as distance traveled? No. If the object is changing direction during motion, then the displacement value and the distance traveled, they are going to be different from each other. So how do you find distance traveled? Whenever you have to find distance traveled, you always have to check if the direction of the object is changing at any point. How do you check for change in direction? When the direction changes, velocity is equal to 0. So whenever we have to find distance traveled from one point to another, from one time instant to another, we always do it like this. We say, let's input v equal to 0 first of all. That's the first thing we do. We put v equal to 0. That gives us some time values. These are the time values at which the particle might change its direction. We're getting t equals 3 and t equals 8. That means the particle may change its direction from at time equals 3 and time equals 8. So we cannot find the distance traveled if we directly input limits from 0 to 10 like we did before. That would not work anymore. We would have to break our journey. We have to break our journey into 3 parts. Since the direction is changing at time equals 3 and time equals 8, and we have to find the distance traveled in the first 10 seconds, we break it into 3 parts like this. We say, let's find the distance traveled from 0 to 3, then from 3 to 8, and then from 8 to 10. We find those distance traveled separately, input limits for each of them separately. The first one gives us 31.5. That's a positive value. This is negative value. This is positive value. So what's that telling us is, initially the particle was moving in the positive direction towards the right side. That's 31.5. Then it moved toward the left side for this much, and then it moved toward the right for 38 over 3 meters. What's the distance traveled? The negative value is just telling you that the particle was moving in the left direction. So for the distance traveled, you would just add their positive values. You'll say 31.5 plus 125 over 6 plus 38 over 3, and that would give you the final result, whatever that turns out to be. That will be the distance traveled. So when you have to find distance traveled from one point to another, when you have equations like these given, always check for change in direction by putting v equal to 0. Okay. So just a summary of what we discussed in the last few examples. You can use limits with integration to find value of displacement from one point to another. So when you have to find value of displacement from one time instant to another time instant, you can use limits like this. If you have to find a function for displacement, for that, you always have to add plus c. Do not use limits there. You should always have a plus c there. Okay. You do not generally use limits for velocity or acceleration. It's possible in some cases, but they will basically tell you the change in velocity from one point to another, the change in acceleration from one point to another. Generally, the questions don't ask you about change in velocity or change in acceleration. So in that case, limits would not have any significance. If you have to find a function for displacement, that means this example, for instance, you have a velocity function. You have a velocity function, and they want you to find a function for displacement in terms of t, an equation for displacement in terms of t. In this case, when you integrate this, you need a plus c with that as well. Okay, in this case, you need a plus c. That's what it means. When you have to find the value of displacement from one point to another, that from one point to another point, how much distance it's traveling, or displacement is traveling, then you can use limits. That's the only case that you would use limits in. Otherwise, you'll always integrate and have a plus c with that. Okay. These integrations are giving us displacement values. These are displacements. That's why it's turning out to be negative. For distance, we do not consider that negative value. We make that positive first, and then we add them up together. Integration gives us displacement, not distance traveled. So that's why we are getting this negative value. Okay. Now, sometimes what happens is we need to find the value of C as well. You'll have some information given in the question to find that value for C. You'll have some information in the question to find that value of C. You'll have to find that value of C. Okay. Now, sometimes what happens is you have multiple equations describing a journey. For example, you have velocity equal to this for time between 0 and 3. You've got velocity equal to this for time greater than 3. Now, when you have multiple equations like this, you need to remember something about this. We have v equal to 5t. That's one equation. We have another equation that's v, that's a constant, where v is a constant. And we have another equation where v is equal to 25 minus t minus 15 whole squared. The first one is valid from 0 to 5. The second is valid from 5 to 15. The third is valid from 15 to 20. Now, the points where you're moving from one equation to the other equation, these are called boundary points. Time equals 5, that's a boundary point because that's when you switch from the first equation to the second equation. Time equals 15, that is also a boundary point because that is when you're switching from the second equation to the third equation. That's also a boundary point. At these boundary points, as you go from one equation to the other equation, remember, the displacement value is always going to remain unchanged. What that means is, if you found the displacement function from this and found the displacement function from this, when you input time equal to 5 in any of them, they should both give you the same displacement value. Velocity is also going to remain unchanged. That means if you input time equals 5 here, the value for velocity at time equals 5 in the second equation is also going to be the same. For example, in this case, the value of v at time equals 5 from the first equation is 25. So that tells us that this constant value that they're talking about here, that is also going to be 25. Velocity at the boundary point is also going to remain unchanged. So you input t equals 5 here or t equals 5 here. Both of them should give you 25. Except in some cases, in some rare cases, where you would have collision. So you have a particle colliding somewhere. In that case, it might be like this, that the particle hits this barrier at some speed, and when it comes back, its velocity instantaneously changes to some other value, for example, minus 3 meters per second. In that case, it's possible that it instantaneously changes to another value like this, but otherwise, velocity is going to remain unchanged, okay, at the boundary point as well. For acceleration, we cannot say anything. Acceleration could be different. It could be the same. For example, in this case, if you find acceleration at time equals 5 from the first equation and the second equation, they are different. But from the second and third equation at time equals 15, they turn out to be the same. So sometimes acceleration is going to be the same. Sometimes it's not going to be the same. Displacement is also displacement is always unchanged. Velocity is also always unchanged, except collision. For acceleration, we can't say anything. It could be anything. For example, let's have a look at this case. A particle starts from rest at the point O, and it travels in a straight line. Its velocity v meters per second at time t seconds is given by v equals at minus 2t square, and we've got another velocity function for time greater than 3. We need to find the distance traveled by p in the first 3 seconds. We can find that. First of all, check for change in direction by putting v equal to 0, then use limits to find that. Then they say find an expression for t for the displacement valid for t greater than 3. Now, how do you think about this? This is the velocity function for time greater than 3, right? This is the velocity function. How do you go to the displacement function from this? You integrate it. When you integrate it, you get something like this. Minus 54 over t plus c. How do you find the value for c in this now? How do you find the value for c? Do we have any point given for this interval? We do not have any point given. But what we can do is, we can say, we have found the value for displacement in the first 3 seconds. That turned out to be 18. So at time 3, the value for displacement was 18. There was no change in direction in this case in the first 3 seconds. So displacement and distance are equal to each other. At time equal to 3, displacement was 18. That point can be used here as well to find the value for c. We can say, since at time 3, displacement was 18, it is going to remain unchanged at time equals 3 for this equation as well. We can use that value from the first equation in this equation to find that value for c. And the displacement function turns out to be this. So at the boundary points at time equals 3 here, the velocity values from both functions, they're going to be the same. If there's no collision, and the displacement value, they're also going to be the same. Acceleration may be different. It may not be different. That depends. That can vary. Then it says value of v when the displacement of p from O is 27. Now that's straightforward, relatively straightforward. It says the value of v, that's what you want to find out. when the displacement from O is 27 meters. You find the displacement function. We know that the displacement in the first part of the journey was only 18. So it's definitely not happening in the first part of the journey. In the first 3 seconds, the maximum displacement was 18. We found that in the first part. So 27 is going to be after that. We've already found the displacement function in the previous part. We can put displacement equal to 27 here, find the value for t from that, and put that in the velocity function. You'll get the corresponding value for velocity as well. But the important point was this: at the boundary points, how the displacement and velocity, they remain unchanged, because you can use that to find the value for c sometimes. No, the question says it's greater than 3. So this velocity function is only valid from when time is greater than 3. Greater than 3 basically means 3.0000001, right? Any value that's even slightly greater than 3, this function will become valid at that point. Okay, it's coming very soon. Not very soon, but maybe 10-15 minutes. Okay, now it's just about some examples that I want to show you, and then we complete kinematics. Or maybe I can skip some of them as well. You can have a look at them in your own time. I'll just show them to make it slightly quicker. A particle starts from O and moves in a straight line like this. You've got this velocity function. Verify that the particle returns to O when t equals 2. Returns to a point. What does that mean? The displacement is going to be 0. So whenever they say a particle or an object returns to its starting point, that means displacement should be equal to 0. So how do you do that? You find the displacement value when time is equal to displacement value from 0 to 2 and see what that turns out to be. If that's 0, that means the particle returns to the starting point. Okay. The second part is, you can have a look at that working. They're saying, look at this question. You can take a snapshot if you want, or look at the notes if you want. But the first part was what I was interested in this part, in this question. The other, you can see the working for that. It's not that difficult. This is the next part. Let's have a look at this one. Okay. Now, in this example, yeah. So sometimes they will say, find the maximum velocity of something. Maximum velocity of something. Now, you have the velocity function given. You've got the velocity function given for that part in, that they're talking about. How do you find maximum value of anything? How do you find maximum value of anything? Of any function? You find the derivative, but that equal to 0. You have the velocity function here. You want to find the maximum value for velocity. How would you do that? You would say, this is the velocity function, find the derivative of that, put that derivative equal to 0. That will give you a value for t. That's the turning point. That's the maximum point. Put that value of t back in the velocity function, and that will give you the corresponding velocity value. Right? So that's the maximum point that we were looking for. So sometimes when they ask you for maximum value of something or minimum value of something, you can use differentiation like this, put that equal to 0. Now the rest of this, you can have a look at this in your own time. And go through this slowly. Okay. All right. Now, look at what the question statement says. Given that there are no instantaneous changes in velocity, find P and Q. What does that mean? No instantaneous changes in velocity. What that means is, you see the first velocity function that's valid from 0 to 6. The second velocity function that's valid from 6 to 14. At time 6, that's the boundary point, the velocity does not instantaneously change to another value. Whatever is the velocity value from the first function, it will be the same velocity value that you get from the second function when time is equal to 6. So using that now, you can find the values of P and Q. What information are we given? We're given the acceleration of P is 0 when time is equal to 2. That's one piece of information that you can use here. Find the acceleration function. from the first one because that is valid when time is 2. So that's what I've done here. Found the acceleration function. Put time equals 2 and equal to 0 in that. And that gave us an equation in terms of P and Q. That turns out to be this Q equals 4 times P. And then we know that at time equal to 6, the velocity from both of these functions is going to be equal to each other. So what we do is we put time equal to 6 in both of these functions and equate them. That gives us another equation, and that's going to give us the values of P and Q. All right. Now, in the next part, they say, sketch the velocity time graph. Now, we've got the two parts of the velocity time function here. One is a quadratic function. You draw it like you draw any quadratic function. How do you draw quadratic functions? You need two sets of points for them, turning points and intercepts. You always have to find turning point while sketching quadratic graphs. The second part of the function was a straight line, 63 minus 4.5t. So you've got a quadratic function and you've got a straight line function. Now, how do you draw them? You have to find the values of velocity at extreme points. First of all, this is valid from 0 to 6. How would you draw that? You would find the value for velocity at time equals 0. At time 0, velocity turns out to be 0. Then you find the value of velocity at time equals 6. That's the other 16 point. And that turns out to be 36. That's the 16 point. Then you find the x-intercepts. One is 0. Can you find the other one? Just factorize this. Put v equal to 0. And that gives you time equals 0 and time equals 4. These are the two x-intercepts that you have for this graph. And the turning point, therefore, is going to be in the middle of them. It's a symmetric graph. Whatever are the x-intercepts, the turning point is going to be exactly in the middle of them. So this is the turning point. So the graph looks like this. And then the second part is just a straight line. You can draw a straight line like that. That's what the graph looks like. So sometimes it can be weird like this. It goes below the x-axis like this, and then it comes back. If you just take extreme points like this point and this point, you might mistakenly think that the graph looks like this. Don't do that. You have to consider the turning point as well. So if you just consider this point and this point, that will make you think that it's going to be like this. You always find the turning point as well. You can find it using the standard method as well, minus b over 2a. Yes, you can do that, minus b over 2a, or differentiate, put that equal to 0. Any of them will work. Okay, but in this case, since we had already found the x-intercepts, turning point is going to be exactly in the middle of the x-intercepts for a quadratic function because it's a symmetric graph. So you can do it like that as well. Total distance traveled by the particle during the 14 seconds. You can see direction is changing at the point 4. So you have to break your journey at the point 4, right? That's important because the direction is changing. So what you would do would be the first function, you would find the displacement, you would input limits in this from time equals 0 to 4 first, and then from 4 to 6. And that will give you the distance traveled during the first 6 seconds of motion. And then for 6 to 14, you use the other equation. Or you can just use the area of the triangle here as well, area in the graph. That will be actually easier. Add that number here, and that will give the total distance traveled. You find the distance traveled from 0 to 4, 4 to 6. Make them positive, add them up together, 32 plus 32, plus 144, that's the area of that triangle, and that gives you 208, and that's the total distance traveled. So sometimes you have to sketch graphs like this yourself as well. Okay, now, in very rare cases, this can happen as well, that one part of a journey is dealt with using constant acceleration formulas. And then for the other part of the journey, you have to use these equations. For example, you've got this particle P that's held at rest. It falls freely under gravity. That means the value of acceleration is negative 10 or plus 10, depending on the direction that you're taking positive. In this case, we're taking downwards positive, so it's plus 10. Until it reaches the point A, which is 1.25 meters below O, the starting point. Find the speed of p and the time taken. That's just the use of constant acceleration formula. That's going downwards, and we know the initial velocity, we know the displacement, we know the acceleration. We can find the final velocity and the time. But then it says the particle continues to fall. But now its downward acceleration is given by 10 minus 0.3 times t. So after this point, we have an acceleration function like this. It's no longer constant now. Acceleration is in terms of t. So in one part of the journey, acceleration was constant, that was 10. In the next part of the journey, you have this acceleration function that's not constant anymore. We need to find the total distance p has fallen 3 seconds after being released from O. Now, notice after being released from O. So 0.5 seconds have already passed. 0.5 seconds have already passed before. So we need to figure out the further distance traveled in the next 2.5 seconds. What would that be? You know what happens from O to A. The initial part of the journey, you knew the initial velocity for that. You knew the final velocity. You find the displacement, you find the final velocity. You got all of that information. And then for the next part of the journey, when the particle is going at an acceleration of this, you have to find the distance traveled in this part of the journey. How do you do that? In order to go from acceleration to displacement, you have to integrate twice. You integrate acceleration once, and that gives you this velocity function. But whenever you integrate, you have a plus c there. Whenever you integrate, you have a plus c there. Okay, we're almost done. And then we'll have a longer break. Okay, so I'm just going to do a quick vote. How many of you have an exam on Monday? Raise your hand if you have an exam on Monday, quickly. What are the exams on Monday? What exam do we have on Monday? EM? But that's what people give in AS generally. So, okay, so some AS people might have that. All right. And that's it. Okay. So we are going to continue after the break. We're going to continue. But if you get too tired, can we do early morning tomorrow? Do you think that will work? Early morning, I'm not saying after Fajr. I mean, before noon. Do you think that might help in case it's becoming difficult to digest now? AS English and EM. Okay. All right. So how early can we do tomorrow? So maybe like 10 to 11:30, something like this, 10 to 11:30, 7 a.m. I'm not sure anyone is going to be up at that time. Will that work for everyone? Sure. Because I'm getting messages now that you're getting zoned out. Multiple people saying that. I'm fine with either. I am used to teaching long classes. So I'm fresh. I'm not fresh, but I would like to believe I am fresh. Okay, so we'll have a break and we'll try to do as much as we can. So even if we have to do it in the morning, we could have a very short session, maybe an hour. Then try to do as much as we can right now, and then we can maybe have a short session tomorrow if needed. Around 30 minutes. Around 30 minutes. But it's not right now. It's not right now. It's not right now. In about 5 minutes. So what happens is the particle goes down. So we have this velocity function. It has a plus c. How do you find the value of the c? We had the final velocity from this part of the journey. We had the final velocity from this part of the journey. We can use that here. We can say at time 0, the velocity is 5. Now, remember, the time for this acceleration function is starting after passing A. So at the point A, it's time 0 for this equation. So at time 0, we know the value for velocity is equal to 5. We can input that here to find the value of the c. Once we've got this value of c, now we've got the velocity function. We integrate it again to get the displacement function, and we input limits from 0 to 2.5 there to get the distance traveled in the second part of the journey, and then we add those two distances together, and that gives us the total distance. So the idea is sometimes you can have something like this as well, that in one part of the journey, they ask you to use constant acceleration formulas, and then in the second part of the journey, they want you to use an equation and use differentiation integration to figure that out. So that's also something that happens sometimes. Okay. What I'll do is I will skip this example, move on to this one. Okay. A particle P moves in a straight line, and we've got the velocity function here. And it's defined in 3 different parts like this. 0 to 4, 4 to 14, 14 to 20 like this. We have to find the value of k first of all. How can we do that? Again, use the boundary points. At time equal to 4, for instance, whatever is the velocity value that you get from the first equation, that will be the same value that you get that you should get at time equals 4 from the other equation. So whatever is the velocity at time equals 4, that is 40 here, that should be the value of k in the second part of the journey. Then they ask you to sketch this velocity time graph. Again, it's a quadratic function, so you have to think about the turning points, about the intercepts, and then draw that. The second part and the third part, they are just straight lines. You draw them like this. Now, the third part, that's what I wanted to focus on this question. Find the set of values of t for which the acceleration of p is positive. Find the set of values of t for which the acceleration of p is positive. What does that mean? It's a velocity time graph. In a velocity time graph, acceleration is given by the gradient of the graph. So in what part of this is gradient positive? It's this shaded part in which the gradient is positive. The turning point was at 1. Gradient is positive from 1 to 4. So we say acceleration is positive from 1 to 4. That's the region in which acceleration is positive, from 1 to 4. Okay. You could also do that. You could find the derivative of velocity, put that greater than 0. Put acceleration greater than 0. Would you get something from that? This is velocity. This is 5t squared. The velocity function is this. Yeah, v equals 5t squared minus 10t. If you find the derivative of that, acceleration turns out to be 10t minus 10. When is acceleration greater than 0? From this, you just get t greater than 1. So for this quadratic function, yes, it's greater than 1. But there's an upper limit as well, because this function is only valid. This function is only valid up to time equals 4. So for that reason, we would say that it's positive for time between 1 and 4 like this. That's the region. That's the region. in which it will work. No, in this case, so the question is, do we always have to visualize it like this? In this case, since we had the graph given, it was easier to do it from the graph itself. But if we did not have the graph given, then you would do that. You would say, find the derivative of v, find acceleration, put that greater than 0. That's what you would use if you did not have the graph given. Okay. Find the total distance traveled by p. We have discussed that before. So you break the journey into multiple parts, 0 to 2 separately, because that's where the direction is changing at time equals 2. And then from 2 to 4, because that's what this part of the function is valid for, until 4. And then from 4 to 14, we have a horizontal line. And then 14 to 20, you've got that inclined line, downward sloping line. Then it says, the man fires and, okay, so there's a man who fires a distress signal. So I've just taken one part of a question here. Vertically upward from sea level. The signal is above the sea level on the top of the cliff, and the cliff here is at a height of 40 meters. So we have a cliff that has a height of 40 meters. Let me go back to that. We have a cliff that has a height of 40 meters. We need to find the speed of projection of the signal. Okay, now how do you find the speed of projection? We have a cliff that is 40 meters high, and we are given that this time interval for which the particle is above the level of the cliff, this part, this time interval is under root 17. How do you find the speed of projection, the speed at which the particle was projected in the upwards direction? This is one way of doing this. You say, let's break this journey. You've got one part of the journey from A to B, and then from B to M. M is the maximum point. It often helps to mark those points in your diagram, because you can then refer to those points easily in your working. So B to M is one part of the journey. A to B is another part of the journey. So what we want to do is we want to find the time taken from B to M. And then we can just multiply that by 2. That should equal under root 17. So I'm doing it like this. I'm saying, okay, what do we know about B to M part of the journey? We know the final velocity, that's going to be 0 at the maximum point. We know the time taken for that. If the total time was under root 17, the time taken for this half journey, that is under root 17 over 2. Half of that. What about acceleration? That's negative 10. Now, using this, what we can do is we can find the initial velocity of the particle. That means the velocity of the particle at the point B. And that turns out to be 5 under root 17. Now, this can be used as the final velocity for this part of the journey. For A to B part of the journey, the velocity at the point B, that turns out to be 5 under root 17 meters per second. Now, that will be the final velocity for A to B part of the journey. Now, for A to B part, we know displacement is 40, acceleration is minus 10, final velocity is 5 under root 17. Find the value of initial velocity. That will be the velocity at the point A. That's what we were looking for. That turns out to be 35 meters per second. So you often have to break your journey into multiple parts like this, where final velocity of one part becomes the initial velocity of another part. In this case, initial velocity of one part becomes the final velocity of the other part. Okay. One last example, and then one last concept after that. There's a particle P that travels in the positive direction along a straight line with constant acceleration. So now in the question, they've given us that it's constant acceleration. P travels a distance of 52 meters during the second second. What does that mean? Time equals 1 to time equals 2. And then it travels a distance of 64 meters during the 4 seconds. That means from time equals 3 to time equals 4. Find the initial speed and the acceleration of the point of the particle P. How do you find that? You can say, if it's constant acceleration, then we can write down the displacement of the particle in terms of t like this. S equals ut plus half at square. We can use that function. Let's write down the displacement function in terms of t. we know that from time equals 1 to time equals 2, the displacement is 52 meters. So in this displacement function, we can input limits from 0 to from 1 to 2 and say that this should result in 52. Simplify that and you get an equation in terms of u and a that looks like this. Similarly, from 3 to 4 seconds, the displacement covered is 64. So again, now you input limits from 3 to 4. You get another equation from that in terms of u and a. Solve them simultaneously and you get the values of u and a from that. Okay, so this is the question. This is the type of question that they've given like 2-3 times in the recent papers as well. They tell you the distance traveled during a particular second. So during the second means from time equals 1 to time equals 2. During the fourth second means from t equals 3 to t equals 4. So you can use limits like this after finding the displacement function. One last concept that you will use in the more difficult questions. So we have not talked about the kinematics and momentum questions, right? We'll talk about them when we talk about momentum. Those are, I think, the most difficult types of questions in mechanics, where they have kinematics and momentum, both of them. In many of those questions, we have this concept that you'll have to use relative speed. Relative speed. Now, let me explain what that means. Let's say you've got two particles. This is A, this is B. And they are at a distance of 40 meters from each other. A is moving towards the right side at 7 meters per second. B is moving towards the left side at 3 meters per second. In how much time at what time value are they going to collide with each other? At what time value are they going to collide with each other? That's what you want to figure out. How can you find that? Think about it. Every second, A is moving 7 meters to the right, and every second B is moving 3 meters to the left. So in 1 second, they are getting closer by 10 meters. They're getting closer by 10 meters. We can say the relative speed for them is 10 meters per second. That every second they are covering a distance of 10 meters. So relative speed can be thought of as the speed at which the distance between two objects is covered. Now, the distance between these two objects was 40 meters. If A moves by 7 meters per second to the right and B moves by 3 meters per second to the left, how much distance are they covering in every second? They're getting closer to each other by 10 meters. So we'll say the relative speed is 10 meters per second. Okay. So how do you find time until they collide? 40 is the distance. Relative speed is 10. That turns out to be 4 seconds. So when particles are moving in opposite directions, that means towards each other, the relative speed is going to be the sum of their individual speeds. We add them up together like this. The other possibility is we've got these two particles A and B, again, the same distance between them. Let's say A is moving towards right at 18 meters per second. B is moving towards right at 13 meters per second. And the distance is this. How much are they getting closer to each other in every second? A is moving in 1 second 18 meters to the right. B is moving at 13 meters to the right. So distance between them is going to reduce by 5 meters because A is traveling 5 meters more than B. So distance is going to reduce by 5 meters. Okay. So what's the relative speed then? 18 minus 13, and that turns out to be 5 meters per second. The distance between them reduces by 5 meters per second. So that's your relative speed. How much time would they take until collision? 40 over 5, that's 8 seconds. So when they are moving in the same direction, then the relative speed is going to be the difference of their individual speeds. 18 minus 13, that's the relative speed. A is approaching B at a speed of 5 meters per second. So the distance will be covered in 40 over 5, that's 8 seconds. Does that make sense? Any issues with this? Now let me know if there are any questions. If I missed some questions in the middle, let me know about them.
ठीक सर एक क्वेश्चन था कि जो न्यूटन सेकंड लॉ ऑफ मोशन है उसमें आर एफ इज इक्वल टू एम ए, एक उधर भी एक्सेलरेशन जो होती है वो कांस्टेंट हम एज्यूम करते हैं जब हम निकालते हैं खुद या दी जाती है।
F equals ma में we don't say anything about acceleration being constant or not. F equals ma is used for at a particular point. एक point पे तो acceleration कुछ भी हो सकती है. Constant होती है if a particle is going from one point to another. Now during this journey, acceleration remains constant at a particular value. But F equals ma, that is generally used at a particular point. So let's say the particle is at this point. At this point, we say, okay, these are the forward forces, these are the backward forces. What's the acceleration at that particular point? So this only gives us acceleration at a particular point. So that can be used whether it's constant acceleration or variable acceleration.
और सर एक और क्वेश्चन
It
था
works
कि
for both of them.
अगर वो सारी फोर्सेस इक्वल हों तो उसमें एक्सेलरेशन जीरो होगी या कांस्टेंट?
Constant होगी. सारी forces equal होती हैं, तो acceleration constant होती है. Let me actually add that here as well. That's an important reminder. We generally discuss that in Newton's second law of motion later on, because that's where its questions come. But let me just add that to the notes here as well. Newton's second law of motion. Where would I have that? So, okay, so one case was when the question tells you that when the question tells you that acceleration is constant. The other possibility is it's motion under gravity. That means it's free fall, or it's an inclined surface with the weight as the only force and the surface is smooth. Another possible case is whenever all the forces acting on an object are constant. In that case is where acceleration is constant. So if you are sure in a particular case that all the forces acting on an object are constant, that would mean that the resultant force is constant. If the resultant force is constant, that would mean acceleration is also going to be constant, right? Because mass is always constant, mass does not change. So if resultant force is constant, that means acceleration is also constant. So sometimes you can infer this from the question statement and then use constant acceleration formulas. If any force is changing, then acceleration is not constant, then you cannot use that. Okay? Newton's laws of motion. Now, in terms of concepts, there isn't really much that you have in this topic. There's just one small formula that you have to use everywhere. Now, what's the idea? Let's say you have a set of forces that are applying on an object. For example, you have this object, that's object A. There's a force acting towards the right side, that's 15 Newton. There's a force acting towards the left side, that is friction, that's 5 Newton. Now, there's a resultant force, that's 10 Newton. Now, because of this resultant force, at what acceleration is this object going to move? That's what we cover in this topic. So that's basically given by this formula. Resultant force equals mass into acceleration. So if you have a resultant force acting on an object, because of that force, how much acceleration is it going to move at? That's going to be calculated using this formula. Resultant force equals mass into acceleration. We sometimes also write it like this: forward force minus the backward force equals mass into acceleration, because that's the idea of resultant force. Whatever are the forward forces acting in the direction of motion, we subtract from that the forces acting in the opposite direction, forces acting opposite of the direction of motion. And that gives us this formula that we call the Newton's second law of motion. Resultant force equals mass into acceleration. Now you see, you've got force on one side, you've got acceleration on the other side. Forces is what we talked about in the first topic. Forces in equilibrium. Acceleration, it comes from kinematics. This is basically the topic. This is the formula that connects the forces topic and the kinematics topic, right? So if you've got some forces given in a particular situation, and you have some information about velocity of the particle, displacement of the particle, acceleration of the particle, this is the formula that's going to connect the forces part with the kinematics part, right? So mostly when you have both, when you're talking about both forces and the kinematics quantities in a specific question, you use this formula to connect them and find any unknowns that you have there. Now, This is a very simple example that we looked at before, that we have a force acting towards right, that's 15 Newton, a force acting towards left, that's 5 Newton. The resultant force is 10 Newton. What's the acceleration because of that? If the mass of this object was 0.4 kg, we can just input values in this formula. Forward force minus the backward force, that equals mass into acceleration, that's 0.4 into A. And that gives us the value for A, that's 25 meters per second square. Okay. Now, mostly what you would have would be, you would have some objects that are connected to each other. You'll have multiple objects like this. For example, let's consider this scenario. You have this kind of situation where you have a pulley that is at the corner, at the edge of a table, and there's a string passing over the pulley, and two objects are connected to that string. One on this side that's resting on the table, that's object A, and the other is hanging like this, that's the object B. Now, what are the forces acting on both of these particles? For A, we've got friction acting because it's a rough surface. There'll be some reaction here as well. There's weight acting in the downward direction. At B, we have tension acting in the upwards direction. We've got weight acting in the downward direction. At A, we also have tension acting towards right side. These are all the forces that we have acting on these objects. What we want to do is, we want to find the tension in the string and the acceleration when these objects start moving when the system is released from rest. So let's say we are holding the object A initially, and we release that from rest. Because of that, B is going to move downwards. What's the acceleration at which it is going to start moving? And also, what's the tension in the string? Now, tension on both sides is going to be the same in this case, right? Because we've got a single string, it's passing over a pulley. Tension on both sides is supposed to be equal. What we do is we apply Newton's second law of motion on both of these objects one by one. Okay. We apply Newton's second law of motion on A separately. Now, in which direction is A going to move? It's going to move towards the right side. So we consider that as the forward direction for A. So what's the forward force for A? Tension. Backward force, that's friction, right? So we say the resultant force for A is T minus 3. That equals mass into acceleration. Mass for A is given to be 1. So 1 into acceleration, that gives us one equation. Similarly, for B, B is going to move in the downward direction. What's the forward force for that? That's 5 Newton. Subtract from that the backward force, that's T Newton. Equate that to mass into acceleration. Mass of B is 0.5, and that gives you 0.5 times acceleration on the right side. You get two equations, solve them simultaneously, and that gives you the values of tension and acceleration. So that's what you do when you have multiple objects that are connected by a string. We apply Newton's second law of motion on both of them separately like this. Now, this is very important. A lot of times, you will get problems that will involve both Newton's second law of motion and kinematics. And that's understandable because in this topic, this is just this formula, but there will be other things happening in that same question as well. There'll be particles moving. You have to find displacement somewhere. You have to find final velocity, initial velocity somewhere. You might have some force missing as well that you might have to find out. Now, look at this formula. We've got two quantities that can vary, acceleration and resultant force. Whenever all the forces acting are constant, that would mean that the resultant force is constant. And if the resultant force is constant, then acceleration would also be constant. So we talked about when we can use constant acceleration formulas earlier. One possibility is that you're given in the question that acceleration is constant. The other possibility is that it's motion under gravity, it's free fall, or it's an inclined surface with a smooth inclined surface with no force acting apart from weight. In that case, we say acceleration is 10 sine theta. This is the general rule for when you can use the constant acceleration formulas. What's the rule? Whenever all the forces acting on an object are constant, acceleration is also constant. And if that is the case, then you can also use the constant acceleration formulas in that situation. If you're not sure about it, do not use constant acceleration formulas in that case. Mostly, the alternative with that in those cases would be that you use the work energy methods, work energy principle that we'll talk about in the next topic. But you only use constant acceleration formulas, the Stewart equations, the equations of motion, when you are sure that acceleration is constant. And how do you decide that? If all the forces are constant, then the acceleration is going to be constant. Now let's consider some examples in this. This is all that we've got in terms of concepts, the basic concepts here. But now there's a lot that comes in questions that we'll have a look at now. Let's have a look at this example. So we've got two objects that are connected to each other. One is P and the other is Q. And they're hanging like this with the string passing over a pulley. We need to find the acceleration of P and the tension in the string before P reaches the ground. Now remember, whenever two objects are connected like this and the string is taut, they're connected to each other, acceleration magnitude for both of them is always going to be equal, right? Because whatever speed, whatever acceleration one moves at, since the other is connected to that, the other is also going to move at the same at the same acceleration, at the same velocity. So if P moves downwards and Q moves upwards, their accelerations magnitudes are going to be equal to each other. Okay. Now, how do you find this? Represent all the forces acting on P and on Q. On P, we've got tension and weight acting. On Q as well, we've got tension and weight acting. Since P is moving downwards because it has more weight, so that will be moving downwards. We say 6 minus T equals 0.6A for object P. And similarly for Q, since Q is moving upwards, T minus 2, that equals 0.2 times A. That gives us two equations. We solve them simultaneously, find the value of T. Now, in the second part, you see, they're asking us for the time taken for P to reach the ground. Now, how do you figure that out? In this case, acceleration has a constant value. It's just 5, right? So it's a constant value. What we can say is the system started from rest. We know the acceleration. Acceleration is 5 that we found in the previous part. And the distance traveled is 0.9. We can find that using equations of motion. S equals ut plus half at squared. And that will give us that displacement covered in this case. Let's have a look at this example. So you can have objects connected this way as well. For example, you have something like this. We have two blocks connected to each other, and B is moving in which direction? Let's quickly try to figure that out. Does that say anywhere here? Okay, it doesn't. So we've got these forces acting. We just represent all the forces acting on both the objects. In the forward direction, we've got 36 Newton acting on B. In the backward direction, we've got the weight of B, and we've got this tension. We also have the weight of A acting in this direction. We've got weight of a component of weight acting in this direction. Now, how do we know in which direction the objects are going to move in? We are given the value for tan alpha here. Now, when you have tan alpha given, you can find the values of sine alpha and cos alpha from that. You can do this on your calculator. You should also know the method for finding them using a right angle triangle that you know from paper 1. But assuming that you have those values, you can actually figure out in which direction the objects are going to move in. Because overall on the system, think about it. Overall, the force acting towards right side is 36. And the force acting towards the left side on the whole system is 40 sine alpha. Sine alpha is 7 over 25. If you evaluate the value for 40 sine alpha, that will turn out to be less than 36. So the forces acting up the plane, they are greater than the forces acting down the plane. That basically tells you that the objects are going to be moving in the upwards direction because of these forces. So the objects move in the upwards direction. We also consider this 40 sine alpha and also 50 sine alpha, by the way, as the backward forces. You can find the sum of them and figure out that this sum, 40 sine alpha and 50 sine alpha, this is going to be less than 36. So that basically tells you that the objects are going to be moving in the upwards direction. Now, once you figure that out, all you have to do is apply Newton's second law of motion on both of the objects one by one. For A, for instance, what are the forward forces? We've got tension acting in the forward direction, backward force, that's 40 sine alpha. These are the only two forces that are acting on the object A. After we resolve the forces, this is what we end up getting. Now, we say T minus 40 sine alpha, that equals 4 times A. Similarly, for B, we've got the forward force, that's 36 Newton. We've got the backward force, that's T, and also 50 sine alpha. And that gives us that 36 minus T minus 50 sine alpha, that should equal 5 times A. And that is going to give you the value for tension and the value for acceleration on this. You can see what that turns out to be by just solving them simultaneously like this. Okay. And then they ask you to find the speed of the blocks. You can use the Newton second. You can use the equation of motion for that. You've got everything that you need for that. You have the distance traveled. You've got the speed, and you've got the acceleration. You can use that to find whatever is missing. You have to find time here. You can do that. Okay. This is another way that they will connect objects. So we'll have two inclined surfaces like this, one on this side and another on this side. Now, again, the particles are connected to each other. We've got one particle here, that's particle P, another particle here, that's particle Q. And the question again says, find the tension and the strength. Whenever they ask for tension, acceleration in problems like these, when you have connected objects, all you have to do is apply Newton's second law of motion on both of the objects one by one. So in this case, again, we represent all the forces acting on both the particles. What are the forces acting? What are the forces acting at the point P? At P, we've got weight acting that acts downwards, that's 6.5 Newton. We've got tension acting in this direction. These are the two forces that we have acting. These are smooth surfaces. If it was if it was a rough surface, they could also be friction acting in that case. But in this case, we only have two forces along the surface, and that they are weight and tension. We can resolve weight. The component of weight in this direction turns out to be 6.5 sine alpha. And now we figure out in which direction the objects are going to move in, first of all, before we apply Newton's second law of motion. So for that, we also need to find the forces acting on the other particle. On Q, we've got weight acting downwards. We've got tension acting in this direction. What are the components of weight that are acting here? 6.5 sine beta here, if this angle is beta. And the other component is going to be 6.5 cos beta. We don't need that. Generally, we need the perpendicular components and reaction when we have friction involved. When we don't have friction involved, we can just ignore them because they're not relevant. And now we have resolved all the forces. In which direction are the objects going to move in? How do we know that? This is 6.5 sine alpha. This is 6.5 sine beta. On the left side, towards the left side, you've got this force acting. Towards the right side, you've got this force acting. Which force is bigger? You have sine alpha and sine beta given in the question. You figure that out. And that would basically tell you that 6.5 sine alpha is going to be a bigger value because it's on a steeper surface. You can just evaluate that P will be going in the downward direction. Now, once you figure that out, all you have to do is make two equations. Forward force for P, that's 6.5 sine alpha, minus the backward force, that's T. That equals 0.65 times acceleration. Similarly, for Q, the forward force, since Q is moving in this direction, that's going to be tension, minus the backward force, that's 6.5 sine beta. That equals mass of Q into acceleration. You get two equations, solve them simultaneously, and that's going to give you the value for tension. That's all that we had to do here. Now, how do we know that we can use constant acceleration formulas in problems like these? In the first part, you see, we found the value of acceleration that was 1.2. 1.2 is a constant. That's just a number. That's a constant value. If it's a constant, that means we can use constant acceleration formulas. 1.2 is a number, right? It's a constant value. Okay. Now, sometimes what happens is, in more complicated problems, at some point, string becomes slack. Now, whenever string becomes slack at some point, that means it no longer remains straight, it no longer remains taut. The tension is going to become zero in that case. The tension is going to become zero in that case. Let's have a look at this example. If you've got two particles that are connected to each other like this, there's one particle here, that's particle A. We have another particle here, that is particle B. We've got these two particles, okay? Now, they're connected, and we've got these forces acting on A and B respectively. On A, we've got weight, we've got tension acting in the upwards direction. And at B, we have weight acting in this direction, reaction acting in the upwards direction. Is the surface rough? No. So in this case, surface is smooth. We could also just ignore these reaction and weight because they're not going to contribute to any equation. So you can just reduce the clutter and just remove them. These are the forces acting on both the particles A and B. Now, what's the forward force for A? A is going to be moving downwards. That's 3.2 backwards T. And you make one equation for this. For B, there is no backward force. There's only forward force, and that's T. So we say T minus 0, that equals 0.248 times A. Now, that will give you the value for acceleration and the value for tension. Now they're saying, find the time taken for the instant that B is released from the instant that B is released for A to reach the floor. Now, once the particles start moving, how much time does A take to reach the floor? We've got the initial velocity given, a starting from rest. We've got displacement given. We found the acceleration already in the first part. We can just use constant acceleration formulas to find the value for A here. But the complicated part is when they say, find the time taken for B to reach the pulley. Find the time taken for B to reach the pulley. How do you find that time taken? Now think about this. The total distance from B to the pulley is 1.4 meters. And the distance for A to reach the ground, that is 0.98 meters. Now, as A travels 0.98 meters downwards, B would be traveling 0.98 meters to the left side. And let's say it reaches this point that I've called Y here. At this point, what happens is A hits the ground. When A hits the ground, at this point, B would be in this position, right? Such that this distance is 0.98 meters. At this point, what happens is string becomes slack. The string becomes slack. String becomes slack after this, right? It's no longer taut because this is the length of the string. When B crosses this point, the string is going to be longer. The string is going to be longer, and the distance between B and the ground, that's going to be shorter. So it's going to be something like this. It'll be, it'll not be straight anymore, right? If it's not straight anymore, the string becomes slack. Now, in these types of problems, I would recommend you label your diagram like this. So I'm calling this point X, this point Y, and this point Z. X to Y part is when the string is taut, when the string is straight and the particles are still connected by that string. And Y to Z part is when the string is slack. And that will make it easier for you to refer to this, refer to these points in your working, and that will make it easier for the examiner as well to check what you're trying to do. So you break your journey into two parts. You say from X to Y, the string is taut. Now, what do you know about X to Y part of the journey? For X to Y part of the journey, we know that B started from 0. Its acceleration was 4, the same acceleration that we found here in the first part when the string was taut, 4 meters per second square. And the distance traveled is 0.98 meters. And the time taken for that part, we've already found in the first part, that's 0.7. Now, the final velocity for this part of the journey will be the velocity of the particle at the point Y. That will become the initial velocity of the second part of the journey when the string becomes slack, because Y is common between them. Whenever you have 2 points common like this, velocity from one part of the journey, final velocity for one part will become the initial velocity for the second part of the journey. So in this case, what we can do is for the XY part of the journey, when the string is taut, we can find the final velocity. That becomes the initial velocity for Y to Z part of the journey. Now, what do we know about Y to Z part of the journey? We know the initial velocity, that's 2.8, right? And we know the displacement, the distance that was left here, that's 0.42, 1.4 minus that. And now, if you look at this, whatever were the forces that were acting earlier, tension gets removed from that. Now, tension was the only force acting in this case. So if tension gets removed, we've got no forces acting now. If there are no forces acting, that means acceleration is 0. The particle is now going to move at constant speed. So acceleration is 0. You can find the time taken from this equation, or in this case, you could also just do time equals distance over speed directly because the speed is constant. And that gives you the time for the second part of the journey. You add these two values up, and that gives you the total time. The total time becomes 0.85. Okay? Taut is when the strings are straight like this. When they're connected to each other like this, they're straight. Now, in this case, A can pull B towards itself. B can pull A towards itself. So tension at B will be acting in this direction. Tension at A will be acting in this direction. Compare that with a string like this. That's not taut. Now, even if A was to apply some force towards the left side, B is not going to change. B is not going to move at all. It's not going to feel any force because the string is not straight. It will take some time before the string becomes straight. Until that point, there will be no tension. So this is when you have slack string, this is Okay, when you have string taut, there is tension. When the string is slack, there's no tension in that case. Okay. Yes, so for problems like these, we first have to identify in which direction the object is moving in. Okay, because otherwise you'll end up making wrong equations, and that will be a bit problematic. Although, even if you end up doing something like this, you would end up getting a negative value of tension sometimes, and that will tell you that you have taken the wrong direction. Okay, so at the end, you can correct that as well. But it's a good idea to figure out first so that you don't get confused in the exam. Figure out in which direction the objects are going to be moving in, and then apply Newton's second law of motion afterwards. If it's not clear from the question statement, figure that out yourself first. This is another example. And this is where things become slightly more complicated now. We've got this diagram. We've got two particles. One particle is A here, the other particle is B. We've got some forces acting. We've got some forces acting on both of these particles, A and B. We've got weight, reaction, tension. Okay. Now, plane P is smooth in the first part, plane Q is rough. So P is not going to have any friction, Q is going to have friction. What about the forces acting on B? There's weight acting downwards, there's tension acting in this direction, reaction acting in this direction, and they are saying the particles are in limiting equilibrium. Again, in which direction are the particles about to move? How do you figure that out? Look at the forces acting on both sides. 20 sine 10 on this side, 30 sine 10 on this side. Which one is bigger? 30 sine 20 on that side. 30 sine 20, that's the bigger force, right? 30 sine 20 is the bigger force. So which direction is the friction going to act in? If this is the bigger force, friction is going to oppose that. Friction acts in this direction, and that's the direction of friction that we've represented here. Now, in the first part, it says the particles are in limiting equilibrium. Limiting equilibrium means opposite forces are equal to each other. So we just equate the opposite forces. For A, we equate tension and 20 sine 10. In this case, we don't need reaction because there's no friction. We can just ignore that. For B, we have to make two equations, one for these forces and the other for these forces. We get two equations from that, solve everything simultaneously, put F equals mu r because it's limiting equilibrium, and you can find the value of coefficient of friction from that. Now, the second part is what is a bit tricky now, and we will see more of these when we do work energy power later as well. It says it's given instead that both planes are smooth and that the particles are released from rest at the same horizontal level. Now, what does that mean? A and B are at the same horizontal level like this. What we need to figure out is the time taken until the difference in the vertical height of the particles is 1 meter. Difference in the vertical height, that is 1 meter, time taken until that point. Now, how do you figure that out? So we've got a situation like this. We've got A right here. We've got B right here. When both surfaces are smooth, there's going to be no friction in that case. What's the weight component acting in this direction? For A, the weight component acting in this direction was 20 sine 10. The weight component acting in this direction for B, that was 30 sine 20. Which one is bigger? 30 sine 20 is bigger. So the particles start moving in this direction. Okay. Now, when they start moving in that direction, what happens is B moves some distance in this direction. Let's say it comes from this point to this point. Similarly, A moves some distance in this direction, right? So A is moving in this direction and B is moving in this direction. Let's say this is particle A, this is particle B. Now, the difference between their vertical heights, so let's say A is at this position, B is at this position, vertical height between those 2 points at this instant is supposed to be 1 meter. Find the time until this happens. Now, how do we figure this out? Now, let's focus on A. A and B are connected, remember. Let's suppose A moves a distance of x meters to the right side. Okay. Now, B will also move the same distance in this direction because they're both connected. This distance traveled by B in this direction is also going to be X in this case. All right, let me just get rid of this. That's okay. So both particles move X units along the surface. Now, the vertical heights between the surfaces, that's supposed to be 1 meter. Now, what does that mean? When X travels this distance along the surface, we know the angle here is 10 degrees. So we can make a triangle like this for A that looks like this. We've got X here. We've got a right angle triangle. The base is unknown. Let's say this is the height that A is increasing. The height for A from its starting point to the end point. And we know that this angle is 10 degrees. Can we find HA in terms of X here? That turns out to be this using the sine function, right? This is what we get. HA equals X sine 10. We do exactly the same thing for B as well. Now, as B moves down the plane, what happens is we get a right angle triangle that looks like this now for B. This distance is X. This is the height for B. And this angle here is 20 degrees. Again, we can find HB in terms of X. That turns out to be X sine 20. So A is moving HA units in the vertical direction, upwards direction. B is moving HB units in the downward direction. So the sum of HA and HB, what should that be? Have I done that here? Yeah, here. Sum of HA and HB, that should be equal to 1, right? The total height is 1, and that will give us the value for X, that's 1.939. That means the particles are traveling a distance of X units in this direction. And we found the value for X, and now we know the displacement that each particle is covering. Once we know the displacement value, we knew the initial velocity, that was 0. We knew the acceleration. We found that in the previous part, that was 1. Did we find that somewhere? No, we have to find that again because now the surfaces are smooth. So we apply Newton's second law of motion on both the particles separately. We find the value for acceleration from that. We've got acceleration, we've got that displacement, and we know the initial velocity. We can find time from that, and that turns out to be this. This is happening a lot in recent papers, that they give you something about vertical heights between particles. How do you find how much distance the particles have traveled? You find them by using right angle triangles like this. Okay, that's the idea. We'll come back to problems like this again when we do work energy power as well, but that's something that can also happen. This is another thing that you will see in past papers sometimes, that the value for tension in some cases will turn out to be negative. Let's take this example. So we have a horizontal test track, and what we have is a car that is towing a trailer of 700 kilograms. So we have this car and we have this trailer. They're connected by a tow bar. There's some forces acting. So on the car, there's no driving force. There's a braking force that the car is applying brakes. So this is the braking force. And this is the tension acting in the backwards direction. There's resistance of 600 Newton. These are forces acting on the car. There's some forces acting on the trailer as well. And they are the tension acting in the forward direction, the resistance acting in the backward direction. Now, again, since there's no friction involved as such here, we can just ignore the weights and reactions. They're not going to be used anywhere. They want us to find the magnitude of the force in the tow bar. That means the value for tension. How do you figure that out? You do it the normal way, just like we normally do it. We apply Newton's second law of motion on the car. What does that turn out to be? Forward force, that is 0. In this case, in fact, since we're looking at the tow bar, in case of car, we've got two unknowns. We've got tension and braking force. In the for the first object, we only have one unknown. That's only tension. So we can apply Newton's second law of motion on the trailer first of all. The forward force is T for that. Backward force is 200. That equals 700 into acceleration. They gave us that the value of deceleration is 12. That means acceleration is going to be negative 12. Okay. We find the value of tension from that. It turns out to be negative. Now, do not get confused by this. This is sometimes possible. You can sometimes end up getting a negative value for tension when it's not a string, but some other rigid object. It's a tow bar. That's a rigid object. In this case, tension can sometimes turn out to be negative. All you have to do is, they wanted the magnitude of the tension. You just write that as 8200, ignore the negative sign, and you say that the magnitude of the tension, the magnitude of that force is 8200 Newton. Okay. Now, why does that happen? The rule that we have studied earlier, that the tension always acts away from the point of reference, that was for strings. When we have something other than string, for example, if you have a rod that is connected to an object like this, now a rod can both pull an object and it can also push the object. If I apply a force to the right side on the rod, the block will start moving to the right side. So the rod can both push and pull. A string could only pull an object towards itself, but a rod can do both. So when you have a rigid object like a rod or tow bar, sometimes when we take our standard direction for tension, the actual direction was the other one. We don't care about that. It doesn't matter. We will do everything the normal way. The tension value will turn out to be negative at the end. And that will tell us that, okay, the tension direction that we took earlier, that was actually the other way around. It was supposed to act in this direction. We actually call this thrust. We will just do it the normal way. The negative value, we will just make it positive at the end because they asked us for the magnitude of the force in the tow bar. We will say the magnitude is 8200. Okay. Yeah, so in this case, what's happening is, since the car is applying the brakes, the car is stopping, but the trailer is still moving forward. So what's happening is the tow bar is pushing the trailer towards the backside, so that trailer also stops, and it's pushing the car in the forward direction because the tow bar was also moving at a speed. If the car slows down, the tow bar starts pushing it in the forward direction. But all of that detail is not required for you. You will do everything the same way. You'll do everything the same way, okay, as you normally do. At the end, in these cases, when you have something other than a string, in this case, you have a tow bar. In this case, it is possible sometimes that the tension value ends up being negative. Now, you don't worry about that. That is a possibility. You will just write that as a positive value, and you say the magnitude is 8200 Newton. That's all that you need to know about. In the second part, they now say find the braking force. How do you do that? Apply Newton's second law of motion on the car now, because that's where the braking force is applying. There's no forward force, right? Because we're applying the brakes. When you're applying brakes, you don't press the accelerator at the same time, hopefully, right? So when you're applying brakes, there's no driving force. There's only a braking force. So 0 minus t minus b, that minus 600, that equals 1600 into minus 12, and that gives you another equation. You already have the value for tension. Now be careful. When you input values of, when you input the value of t in this, input the actual value of t, and that's minus 8200. According to your directions, the t value is negative 8200. You will input that value as it is here in place of t, and you'll get the value of the braking force that turns out to be 26,800, and that's what we were looking for. Okay. That's the braking force. I've represented the braking force by the letter B here. Okay, that's the braking force acting on the car. Okay, I hope that makes sense. Let me go back to this. So there was some question here. No, in such questions, there's a question that why is HA not going to be equal to HB? The angles are different. This is 10 degrees. This is 20 degrees. So one side of this plane is more steep and the other is less steep. So if the distance traveled along the plane is the same, the vertical height that is changed, that is going to be different for both of them. It's not going to be the same. Okay, so we cannot assume that HA and HB, they're both going to be 0.5. That will be wrong because the angles are different. If the angles were the same, then yes, that would be true. But in this case, that's not true. Because A is moving in the upwards direction, B is moving in the downward direction. And the total difference between their heights, that is 1, right? So that means this plus this, that has to equal 1. All right? Because the question says that. Find the time until the difference between the vertical height of the particles is 1 meter. Okay? All right, let's move on. Now, sometimes you have lift and elevator problems like this. Lift and elevator problem. We'll have a break after this, 5-10 minutes. Yeah, that's okay. This is another type of problem that you will see in past papers sometimes. Very rare, but you will see that more in recent papers. I think a couple of times in the recent papers I've seen that. So there are two children named these. They're standing on the floor of the lift. The lift has mass 250 kilograms. Okay. Now, if the mass is 250 kilograms, what's the weight of the lift? The weight of the lift acting in the downward direction, that's going to be 2,500 Newton. Now, the lift is raised vertically upwards. It's going in the upwards direction. With constant acceleration, the tension in the cable is 3616. So this tension is 3616. They've given that value as well. Now, they're saying as the lift accelerates upwards, the floor of the lift exerts a force of magnitude 565 Newton on Alan and a force of 226 Newton on Bhavana. So the lift is applying forces of this and this magnitude on these two people. These are basically the reaction values, right? When you have somebody standing on a surface, they apply some force on the ground, and the surface applies some force in their direction, in the upwards direction. They're saying these reactions are 565 Newton and 226 Newton respectively. These are the reactions. Now they're saying by considering the forces acting on the lift only, find the acceleration of the lift. Now, what's the acceleration on the lift going to be? Acceleration of the lift going to be using forces on the lift. What are the forces acting on the lift? In the upwards direction, we've got tension acting, that's this. In the downward direction, we've got the weight of the lift acting, okay? And apart from the weight on the lift, why do I have 10 written here? Where's that coming from? Okay, that's what I'll just remove that from here for now. Forces acting on the lift. We've got tension acting in the upwards direction, and we've got weight of the lift acting in the downward direction. These are the two forces that we've got acting on the lift. Now, the reaction that the lift is giving to these people, that is 565 Newton. That will be the force that these people are applying on the lift as well. On the lift, the force applied by these people, that's going to be 565 Newton in the downward direction, 226 Newton in the downward direction. So that gives us this equation, 3616 minus 2500 Newton minus 565 minus 226, that equals 250 times acceleration. And the value of acceleration turns out to be 1.3. Then they ask us to find the mass of Alan. Now, this is very important. Mass of Alan. Now, do we assume, so this is Alan, do we assume that the weight of Alan is 565 Newton? No. When the lift is moving in the upwards direction, okay, I'll explain that in a few minutes. I'll go back to that. Okay, so I see a lot of questions coming on this. What I'll do is, let me explain this concept first, and then I'll come back to this question again. Okay, just give me a minute. Let me explain this concept in detail first, and then we'll come back to this example again. Okay, all right, I get you. So let me come back to that example in 3-4 minutes. So for lift elevator problems, when you have lift elevator problems, we need to know something about this concept called apparent weight of an object. Let's think about this situation. We've got this block. It has a weight of 30 Newton that acts vertically downwards. It has reaction acting in the upwards direction, that's 30 Newton upwards. Now, the block is applying a force of 30 Newton in the downward direction. Because of that, the surface gives it a reaction in the upwards direction. That's also 30 Newton. The surface feels a weight of 30 Newton. It gives a reaction to that. That's also 30 Newton. Compare that with this example. Same block, But now we are also applying a force in the upwards direction on that block of 20 Newton. Now, because of that force that you're applying in the upwards direction, 20 Newton, the surface is not going to feel all of this 30 Newton force, because 20 out of that is going to be balanced because of this force that you're applying in the upwards direction. So the surface is only going to feel 10 Newton, right? The net force. And that is what it gives the reaction for. The reaction value is 10 Newton. This reaction, we can also call it the apparent weight of the object. In the first case, the surface was feeling 30 Newton. That's the apparent weight of the object in the first example. In the second example, the surface is only feeling 10 Newton. That's the apparent weight of this object. So reaction can also be thought of as the apparent weight of an object that's felt by the surface. Okay. Now, that's important. Now, what happens in the case of a lift? Let's consider a scenario when you have a lift moving in the upwards direction. We've got this block that is inside a lift like this, and the lift is moving in the upwards direction. Now, as the lift moves in the upwards direction, we've got this set of forces that are acting. Tension, that's the tension in this cable. We've got mass of the lift. I'm representing that with capital M, mass of the block inside, small m. Reaction, normal reaction on the block. So this force, this is reaction. And gravitational acceleration, that's G. Now, if you were to consider forces acting on the whole system, so on all of these objects, what would be the total forces acting? Overall, we've got tension acting in the upwards direction. We're considering the whole system right now, both the lift and the block. On the whole system, in the upwards direction, we've got tension acting. In the downward direction, we've got the two weights, and the two weights are mg and mg. These are the two weights that are acting in the downward direction. So T minus mg, that equals total mass, which is capital M plus small m, mass of the block and the lift, times acceleration. That's one equation that we can make using this. So what you normally think of when you make an equation like this, you're actually thinking of the whole system. So some of you were asking why we're considering reaction there, why we're subtracting that. Because you were thinking that you have this whole system. Yes, when you make an equation for the whole system, in that case, you say, okay, there's a force acting in the upward direction. There are two forces acting in the downward direction. And that's an equation that we can make here. T minus capital mg minus small mg, that equals the total mass times acceleration. And that works. If you were to consider only the block, what are the forces acting on the block? On the block, there's a forward force. Since the lift is moving upwards, there's a forward force of R. And what's the backward force on only the block? On the block, there's a weight for block. What's that going to be? Mass of the block times mg. So for the block, we say we've got this equation, R minus mg, that equals m times a. So if you were to make an equation for only the block, then we've got this. Then, if we consider the lift only, forces acting on only the lift, what are the forces acting on the lift now? Think about the lift now. On the lift, we've got tension acting in the upwards direction, and we've got the weight of the lift, which is mg, and also the weight of the block that is felt by the surface, not the actual weight of the block, the weight felt by the surface, the apparent weight. Apparent weight, that's the same thing as R. That's also acting in the downward direction on this. When we consider the whole system, we've got T minus mg minus R. Now, R in this case is not the reaction. We're considering that as the apparent weight of the block. That's the force that we got in this case. Okay. So we could make any two of these equations and find those unknowns. Generally, this lift equation is a bit confusing. So if the question does not specify anything that you have to use forces acting on a particular object on just the lift, I would recommend make one equation using this, the whole system, make one equation for the block inside only, and solve them simultaneously. That will give you the result. But if you do have to consider only the lift, then you have to understand this concept of apparent weight. On the lift, you have this R acting like this. When we consider the whole system, we do not consider this R, because on the whole system, when we consider this whole system, that R gets cancelled out. Surface of the lift is applying R in this direction, block is applying R in this direction, they get cancelled out. Okay, so that's why for the whole system, we don't consider that. Okay, all right, let's move on. If the lift is moving downwards, what happens in that case? Almost exactly the same thing, just the directions become reversed now. Since the lift is moving downwards, the downward direction is positive in this case. So if you consider the whole system, the forward force in the downward direction in that case, what would that be? On the whole system, we've got mg plus mg acting downwards, and we've got tension acting upwards, equals m plus m times a. For the block only, we've got mg acting in the downward direction, r acting in the upward direction. That gives us this equation. For the lift only, we've got reaction acting, apparent weight of the block acting downwards. We've got the weight of the lift acting downwards. So r plus mg minus t, that equals this. When the lift is at rest, when it's not moving, in that case, the opposite forces are going to be equal to each other. When it's not moving, or it's moving at constant velocity, in that case as well, acceleration is going to become zero, or constant velocity. In that case, acceleration is zero, so the opposite forces are going to be equal to each other. So in this case, for the whole system, we can say tension, that equals mg plus mg, the total weight acting in the downward direction. For the lift only, we could say tension equals mg plus r, weight of the lift, plus the apparent weight of the block. And for the block only, reaction equals mg. Reaction is going to be equal to weight only when the lift is at rest, or when the lift is moving at constant velocity, because in that case as well, acceleration is zero. So now let's go back to that example that we looked at earlier. In this case, the question specifies that you want to consider forces acting only on the lift. For that reason, what we do is, we say on the lift, we've got tension acting in the upwards direction, we've got the weight of the lift acting in the downward direction, that's some value here, 2500 Newton. And we've got the apparent weights of these two people. Apparent weights. What are the apparent weights acting in this direction? We've got 565 Newton acting in this direction, and we've got 226 Newton acting in this direction. That's what we get from this. When we consider only Allen, on Allen, we would say the forward force in the upward direction, that is the reaction, that's 565 Newton, when we consider Allen only. And in the downward direction, it'll be the weight of Allen, that's mg, or you can say 10 times m. So that's what we're doing here. 565 minus 10m, that equals mass into acceleration. We knew the acceleration was 1.3 from somewhere here. We found that in the previous part, and that gives us the mass of Allen. That turns out to be 50 kilograms. Okay. All right, let's move on. Apparent weight is for the objects that are inside the lift. For the lift, we consider the actual weight. Mg is the actual weight of the lift. For the objects that are inside the lift, for the lift only equation, we consider their apparent weights like this. Okay, all right, let's move on. So that's how you deal with elevator problems. You will see examples like this sometimes as well, when you have strings connected in a way like this. When you have strings connected in a way like this. So we've got this point O, from which a string is hanging. And there's a particle hanging here. There's another particle hanging from another string that's connected to B, connected to A. We need to find the tension in S1 and the tension in S2 if it's in equilibrium. So we consider the opposite forces. If we consider object A, at A, we've got weight acting downwards, that's 30 Newton. We've got tension acting in the upwards direction. Let's call that T1. If it's in equilibrium, T1 is supposed to equal 30 Newton. Then we consider forces acting on B. On B, we've got tension acting in the downward direction. For the lower string, we've got tension acting in the upward direction for the upper string, T1 and T2. And we've got the weight of P as well, that's acting in the downward direction. So T2 should equal T1 plus 20. We already have the value for T1, that's 30. And that will give us the value for T2 as well. Okay. And then it says S2 breaks, the string S2 breaks, and the particles fall down. The A resistance on A is 1.6 Newton, and the A resistance on B is 4 Newton. Okay, find the acceleration of the particles and the tension in S1. Now, how do you think about this? So the upper string that breaks, when the upper string breaks, and what happens is, we've got only this part left. Okay, we've got only this part left. Now, when only this part is left, this is what the forces look like. We've got object B that has some forces acting like this. We've got tension acting in this direction. We've got weight acting in this direction. We've got A resistance acting in this direction. And similarly for A, we've got some forces, tension, resistance, and weight acting in the downward direction. We apply Newton's second law of motion, both of them separately, like we normally do. Find the value of tension and acceleration from that. And that's what you're looking for. When you have a situation like this, represent forces on each particle separately and just apply Newton's second law of motion on each of them like this. All right. Okay, good. Let's move on. This is another difficult type of problem that you'll see in some questions in some older past papers, and it can come in recent past papers as well. Let's move on. Okay, let's have a look at this now. We've got two blocks. Okay, equation for B in the previous question, 30 Newton acting in the downward direction. Sorry, on B. On B, we've got T1 acting in the downward direction because of the tension in the lower string. The string is still going to be taut. Why? Because this has less weight. This has more weight, right? 20 Newton is smaller, 30 Newton is bigger. A has more weight, B has less weight, so the string is going to remain taut. What are the forces acting on B? We've got tension, weight, and in the backward direction, we've got resistance. The upper tension will get eliminated. Right, the tension that we had in the upper string, that is no longer there because the upper string is now gone. This 4 Newton is resistance. Yes, there's resistance there. Okay, all right, let's move on. This is another type of question that you will see in past papers. You'll have two blocks on top of each other like this. And they say something like this, first of all. Show that the two boxes will remain at rest for a certain value of force. P is less than or equal to 6. When P is less than or equal to 6,000, the forces remain at, the boxes remain at rest. Now, how do we think about this? So both of the boxes, they have mass 400 kilograms. That's what is given. They are at rest. And there's a force of P Newton acting towards the left side. The friction between the lower box and ground is this. Between the two boxes is this, the coefficient of friction. That's the value of mu given for both the particles, for both the boxes. They're saying show that both the boxes will remain at rest if P is less than or equal to 6,000. How do you figure that out? The force acting towards the left side is P Newton. When you try to move the objects to the left side, friction is going to oppose that. Friction acts in this direction. Boxes are going to start moving when the force acting towards the left is more than the maximum possible value of friction here. Can we find the maximum possible value of friction? F max is mu times R. Find the maximum value of friction. How do you do that? The total weight at this point is 8,000 Newton. 400 kilograms is the mass for each box. So 4,000 Newton plus 4,000 Newton, that becomes 8,000 Newton. That's the total weight acting on the ground at this point. So what's the reaction going to be then? Reaction at that point is also going to be 8,000. So F max is mu times R, and that turns out to be 6,000 Newton. So if the value for P is less than or equal to 6,000, then that means the block is going to remain at rest. If this value becomes greater than that, then they're going to start moving. right? That's the first part. That's pretty straightforward. Now, the next part is what is confusing. It says the boxes start to move with acceleration A. So now the boxes start moving. Now the boxes start moving. In which direction are they going to start moving? Towards the left side. They start moving in that direction. Given that no sliding takes place between the boxes, show that A is less than or equal to 4 and reduce the maximum possible value of B. No sliding takes place. What does that mean? If you were to push this lower box too hard, so think of two matchboxes on top of each other. If you push the lower one, what happens to the upper one? That slides down like this, right? If you apply a big force on the lower matchbox, the upper one will slide down and fall down like this. They are saying no sliding takes place. Given that, show that A is less than or equal to 4. So think about it. As I said, if acceleration becomes too big, the box is going to slide down. What's the maximum possible value of acceleration for which the upper box is not going to slide down? How do you find that? Let's represent the forces acting on the upper box as well now. What are the forces acting on the upper box? 4,000 Newton, that's the weight acting downwards. Normal reaction from the lower box to the upper box, that's also 4,000 Newton. And there will be friction. In which direction does friction act? Boxes are moving to the left side. We would intuitively think at first that the friction should act in this direction. However, why is the upper box moving in the first place? Why is it moving? The upper box is moving because the force is applying on the lower box, right? The force is applying on the lower box. The upper box is connected to the lower box and they have some friction between them. Because of that friction, the upper box remains connected to the lower box and it starts moving to the left side as well. The upper box, if there was no friction, it would actually try to stay in its current position and slide down like this, right? That's how sliding would take place. If you were to push the lower box to the left side, the upper box will try to slide down like this. So upper box is trying to move to the right side. Friction is what is going to keep it in its position above the upper lower box. So friction opposes this possible motion and it acts in the left direction. So on the upper box, to stop the upper box from sliding down in this direction, friction acts towards the left side. So the upper box is actually moving because of the friction in this case. That's a bit counterintuitive, but that's what is happening because the force is only applying on the lower box. The upper box is moving because of the friction between the two boxes. So friction acts towards the left side in this case. Now, what's the maximum possible value of friction that you can have between the two boxes? We can find that as well. The maximum possible value of friction, mu times r again. R there is 4,000. Mu between the boxes is 0.4. The maximum possible value of friction turns out to be 1,600 Newton between the two boxes. Now, corresponding to that force, what is the acceleration that you can have? What's the maximum possible acceleration that you can have? The maximum possible acceleration that you can have using F equals ma turns out to be 4. Forward force 1,600, mass into acceleration. The value for A turns out to be 4 from this. If acceleration was to be even slightly more than this, what would happen would be the box will slide down because friction cannot go beyond 1,600 Newton. So for more than that acceleration, the friction, the upper box is going to slide down. So this is the maximum possible value of friction that you've got in this case. That's what we were looking for. Then they say, deduce the maximum possible value of P, value for P. Now, what's the value of P going to be? P is the force acting on the lower box, right? So now we consider forces acting on the lower box. What are those forces acting? Towards the left side, we've got P acting. Towards the right, we've got friction acting. That should equal mass, the total mass, that's 800, into acceleration. So the maximum possible value of acceleration that you find there, what's the corresponding maximum possible value of P that you get from this? You input values in this, you get the maximum possible value of P. If P becomes even slightly more than this, what would happen would be acceleration would become bigger and the boxes will start, the upper box will slide down like that. And that is not what we want. All right. So that's how you deal with problems like these. A bit confusing. Make sure that look at the solution again. Try to think about this. It's a 7-mark question. The second part, look at the working. It's just this. The marks are for this thinking process behind this. Okay. All right, let's move on. So just a couple of problems left before we end. Okay. Just a couple of problems in which you have strings becoming slack, because again, this is a common type of problem that we see in past papers. We've got these two particles that are attached to a string, and the string is passing over a pulley like this. We need to find the tension in the string and the time taken for B to reach the plane. We have seen this problem before. We make two equations using Newton's second law of motion for both the particles one by one. And then we have the value for acceleration and tension from that. Once we've got that, we have to find the time taken for B to reach the plane. We've got displacement, we've got initial velocity, we've got acceleration as well. And that gives us the value for T. All right? Okay. Then part B is what we want to focus on right now. Yes, so that's correct. The inequality questions that you get in the exam generally they involve friction. Yes. Okay. Now in the second part, now they're saying what happens is we want to find the time taken for A, for which A is at least 3.25 meters above the plane. Now, what does that mean? B was moving in the downward direction, and A was moving in the upward direction, right? Now, when B travels 2 meters downwards, A would have also traveled 2 meters upwards. So A will reach this point. At that point, the string becomes slack. At this point, string becomes slack. And then A will move up for a bit more, and then it'll come down. They're saying find the time for which A is at least 3.25 meters above the plane. Now, until this point, it will be 3 meters in total. 1 meter was already there before, and then 2 meters more. So the total height that you end up getting from this, that's 3.25 meters. Sorry, 3 meters until this point, but then you want 0.25 meters more after that. Until this point, the string is taut. When B hits the ground at this instant, the string becomes slack. So we'll have to divide this journey into two parts. We'll have to break this journey into two parts. One, when A travels this 2 meters distance, in that part, string is taut, and then a further 0.25 meters after that. So we divide the journey like this. And then we find that time taken. How do you do that now? Let's consider the part when string is taut. When the string is taut, we know the initial velocity, we know the displacement, that's 2 meters. We know the acceleration, we found that in the previous part. We can find the final velocity from that. And that turns out to be this. Why are we finding the final velocity? As we do in such problems, the final velocity in one part of the journey becomes the initial velocity for the next part of the journey. So while the string is taut, we get the final velocity is under root 10. That will become the initial velocity for the second part of the journey now. So now we consider the second part of the journey. After B hits the plane, the string is slack. Let's see what happens in that part of the journey now. For that part, the particle is now going to be in free fall, right? Because there's no force acting on this. It's not connected to the string anymore. It's in free fall now. There's only weight acting on this. So it's free fall. So now we can say after that point, after it has already reached a distance of 3 meters above, from this point onward, we have string that is slack. For this part, acceleration is -10, displacement is 0.25, right? We want to find the time for which it's at least 3.25 meters. So I'm first finding the time when the displacement is equal to 3.25, and then we'll think about that further. Acceleration is -10, displacement is this. Initial velocity from here is under root 10. From this, what we can do now is we can find the value for time. Using this equation, we get two values of time. One is this and the other is this. Now that tells us while the particle was going upwards, its displacement became that first when time was equal to this. And then on its way back, the displacement became that same value again at this value of time. So what's the time duration for which the particle is above that point? You just find their difference. and that turns out to be 0.447, and that's what we were looking for. So again, when you have a string that becomes slack like this, you break your journey into two parts, one when the string is start and the other when the string is slack. The initial velocity for one part becomes the final velocity for, the final velocity of the first part becomes the initial velocity of the next part. And then you do these calculations like this. When it's in vertical motion, the acceleration after that point, when the string is slack, that becomes -10. Another example like that, but now it's not free fall, but it's an object that is on a surface. In the first part, again, we have to find the tension in the string and the magnitude of acceleration. That's a standard question in which you just use Newton's second law of motion on both the objects one by one. You represent all the forces. You have weight, friction, normal reaction, tension. Represent all of them, resolve them. Perpendicular to the surface, these forces are always going to be equal to each other. And in the direction of motion, you just apply Newton's second law of motion on both of them individually, and that gives you the result. You get the value for acceleration and the value for tension. That's 7 marks, a lot of marks for just this. You can have a look at this working. That's fairly straightforward. But now the second part says, when B reaches the ground, it comes to rest. Find the total distance that A travels down the plane from when it is released until it comes to rest. You may assume that A does not reach the pulley. How do you think about this now? So as B moves downwards, it travels a distance of 0.25 meters in the downward direction. At this point, B is going to hit the ground. A would have traveled 0.25 meters in this direction as well. At this point, the string becomes slack. So I've marked these points like this. This point is X, this is Y, this is Z. From X to Y, the string is taut. And then from Y to Z, the string is slack. So what's point Z? They're saying it comes to rest at some point. Because of friction, it stops at some point. It does not reach the pulley. It comes to rest at some point. So we have two parts of the journey, one from X to Y and the other from Y to Z. X to Y is when the string is taut. And Y to Z is when the string is slack. What do we know about X to Y part of the journey? It started from rest. We knew the acceleration from the previous part when the string was taut. Acceleration was this. And we know the displacement as well. From that, we can find the final velocity. The final velocity turns out to be 2.4. That under 2.4, that becomes the initial velocity for the second part of the journey. What do we know about the second part of the journey now? We know the initial velocity. We know the final velocity because it comes to rest. That's 0. Displacement is what we want to find out. But that's not enough information. We have got final velocity, initial velocity, and that's it. We need one more piece of information. Can we find acceleration somehow? In the previous example, we had free fall. We knew that acceleration is -10. In this case, it's on a surface. You have to consider all the forces acting on this object at this point. We did that in the previous part as well. We made an equation for the particle when it was going downwards like this. This was the equation that we made for that. 2 sine theta plus t minus f equals 0.2 times it. Now, when the string becomes slack, what changes? Tension becomes 0. Tension becomes 0. So when tension becomes 0, in this equation now, we can get rid of that tension. So now we have just 2 sine theta minus f, and we don't have t there. So 2 sine theta minus f equals 0.2 times f. So the same equation with tension removed from it. From this, what we can do is we can find the value for acceleration. Once we have that, we can find the corresponding displacement from that, add those individual displacements, and that gives you the total displacement, the total distance traveled by A until it comes to rest at that point. These are the different types of problems that you will see when the string becomes slack. And that's it. I hope that was helpful. We stop here. Work energy power. This is the next topic that we're doing now. Now, in the previous topics, forces, kinematics, Newton's second law of motion, most of the quantities that we talked about, they were vector quantities. Okay, now in this topic, work, energy, and power, all of these three quantities are scalar quantities. That means their directions do not matter, only their magnitudes matter. Now, work is the first one that we're talking about. It has a unit that's called joule. It's represented by this letter J. Work is defined as force in the direction of motion times the displacement. Okay, or W equals F times D. If you have a force acting like this, 25 Newton, and it's making an object move by 20 meters to the right, let's say, the work done by this is 500 joules. If it's acting at an angle, for example, this is 50 Newton, and the angle is 30 degrees, and the distance that the object travels because of that is 15 meters, you find the component of that force in that direction, and then you multiply that by the displacement. So 50 cos 30, that's the component of that force in this direction, times the displacement, that gives you the result. And that's what you get. Now, this can actually be generalized to something like this as well. W equals ft cos theta. If you want to use that, you can do that. Otherwise, this resolving thing always works as well. But this is another formula that you could use for work when you have a force acting at an angle with the direction of motion. Fd cos theta, in this case, theta represents the angle between the force and the direction of motion. And if you just input the values of f and d directly in this and the value of theta, you would not have to think of resolving the forces in this case. But if you want to do it just this way, by resolving forces, that's also fine. That will also give you the same value. Now, if you have something like this, that you have a force acting in this direction and the distance traveled is in this direction. In this case, if we were to find the work done by the force P, that would just be zero, because force P does not have any component acting along the direction of motion. So that will just be zero. If you were to find the work done by the force Q, this is force Q, not angle theta, this is force Q. If this was 30 Newton, that would just be, all of this will be worked done by the force Q, that will be 750 joules. Now, if you have a situation like this in which there's also friction, so you have a force acting in this direction at an angle of 60 degrees, and there's friction that's opposing the motion of 15 Newton. In this case, one thing that you may have to find would be the work done by the force P. Now, when you find work done by a particular force, you just use that force in the formula directly. So 45, what's the component of that? 45 cos 60. Multiply that by displacement, that's 40, and that's 900 joules. You do not subtract friction from that. The work done by that force P would just be 900 joules directly. We are not going to subtract friction from that. If we had to find, I'll talk about that in a minute again. If we had to find work done against friction, what would that be? We would multiply friction by the force, by the distance traveled, that is 40 meters, and that turns out to be 600 joules. That's this value. Now, why did we not subtract this 600 joules from that 900 joules when we talked about work done by P? This work done by P, that's actually doing two things. The total work done 900 joules. Number one, it's working against friction. So this is the work done by P against friction. So out of that 900, 600 is being used against friction. And the remaining then, 900 minus 600, which is 300 joules, that is being transferred to the object as its energy. And that is what is going to make the object move to the right side. Okay, so the total work done by P, that is simply calculated using the formula directly. That turns out to be 900 joules. But then some of it is used against friction, some of it is transferred as energy to the object. Yes, you could call it that. You could call it that. Okay, now, what if you have something like this, vertical motion? In this case, what's the work done by the force P? If you have a force P acting like this, 750 Newton, and because of that force, the object is moving 25 meters in the upward direction, you just multiply those two, and the work done turns out to be 18,750 joules. Work done against resistance, what's that? We have a resistance of 100 Newton. The displacement opposite of that is 25. We just multiply those two numbers, and that gives us work done against resistance. That's 2,500 joules. Work done against the weight. So we have this force acting in the upwards direction. It's also doing some work against the weight, because weight is opposing that force. Weight is opposing the motion. Now, how much is that? Just multiply weight by the distance traveled, and that turns out to be 7,500 joules. Now, in this case, what's happening is the total work done by P is 18,750 joules. Some of it is being used against resistance. Some of it is being used against weight. And the rest of it is transferred to the object as the energy of the object. Okay? Yes, so this total work done includes work done against resistance, against weight, and this. Okay? Next, we've got energy. So this energy that we talked about, now in our syllabus, there are only two types of energy. There are many different types of energy, actually, but in our syllabus, there are only two, and they are kinetic energy and potential energy. For any other energy, we will assume that that's negligible, and we would not be considering that. Now, what's energy? Energy is also a scalar quantity. Its unit is also joules. There are two types of energy that we'll be talking about. One is kinetic energy, and the other is gravitational potential energy. Kinetic energy is defined by this half into mv squared. It's mainly because of the speed of the object, right? That's the differentiating factor in kinetic energy. It is because of the speed of an object. Of course, mass plays a part as well, but mass is going to be in the other types of energy as well. But the speed is the distinctive part of this. Kinetic energy is because of speed of an object. It's defined as half mv squared. Gravitational potential energy, it's because of height of an object, and it's defined as mgh, where g is 10 and h is the height above the ground level. Now, mostly you'll be dealing with, you'll have to find out the difference, the change in kinetic energy and the change in potential energy. How do you find that? Let's say you've got a particle like this, an object like this, a block like this, and it's moving in the upward direction. And we know that it started from 2 meters per second and it reached a speed of 0.5 meters per second. And it traveled a distance of 30 meters in the upward direction. If we have to find the change in kinetic energy, we can think of it like this. Change in kinetic energy, what would that be? The final kinetic energy, we can say half mv squared minus the initial kinetic energy, half mu squared, where v is the final speed and u is the initial speed. We can come up with a formula like this from that. Half into m into v square minus u square. You can subtract them separately as well if you want, but this is slightly more efficient in questions. When you want to find change in kinetic energy, you can just say half into m into, you take half m common from this, right? And that leaves you with v square minus u square inside. That's the change in kinetic energy. What about change in potential energy? Now, in this case, potential energy at this point would be mgh1. At the other point, it will be mgh2. But we do not know the values of h2 and h1. How do you find change in potential energy then? We could say it's mgh2 into mgh1. Sorry, mgh2 minus mgh1. Take mg common, and that leaves us with h2 minus h1, the difference between the heights. So the change in potential energy is actually given by this mg into delta h, change in height. So whatever is the change in height, that's what we use in the formula right here. That's 30 meters, and that will give you the change in height. So again, mostly we will just be dealing with the changes in potential energy rather than absolute values of potential energy, rather than actual values of energy, especially for potential energy. In kinetic energy, sometimes we do find the absolute values. In potential energies, we mostly talk about the change. Okay. So in this case, the potential energy, for example, is going to be 5 into 10 into 30. Change in potential energy, and the change in kinetic energy is going to be this, half into 5 into 0.5 squared minus 2 squared, and that gives you this. When it's a negative value, that means the change is negative. The kinetic energy is decreasing. When the change is positive, that means the energy is increasing. Okay, so when the change is positive, that means it's an increase. When it's negative, that means it's a decrease. If you know that it's a decrease, make sure that you have a negative sign there. If you know it's an increase, you have a positive sign there. Now, we talked about how the work done by something is used for multiple things. Some of it is used against resistance, some of it is used against some other thing, and then the rest of it is transferred to the object as its energy. This is something that connects work and energy. It's called the work energy principle. You'll be using this a lot in this topic. Work done by the driving force, that is equal to the change in kinetic energy plus the change in potential energy plus the work done against resistance. So the work done by a driving force, it's used against resistance, and the rest of it is transferred to the object as its energy. In short, we can write it like this: work done by driving force, that equals change in kinetic energy plus the change in potential energy plus the work done against resistance. Now, what is a driving force and what is a resistive force? Now, we've talked about forward forces and backward forces earlier in Newton's laws of motion. When we use F equals ma there, we say forward force minus the backward force. That equals mass into acceleration. Now, in forward forces, we've got all the forces that are acting in the direction of motion. In the backward force, we've got all forces that are opposing the motion, that are acting opposite of the direction of motion. So forward force and backward force, they just mean all forces acting in the direction of motion and opposite direction of motion, respectively. Driving force and resistance that we will mostly be using in this topic, this driving force and this resistance, their definitions are slightly different. They're not the same as forward force and backward force. Driving force is any forward force except weight. Weight is not considered a part of driving force. Except weight or any of its component, we will not include that as driving force. Resistance as well, it will be any force opposing motion, so that means all backward forces, except weight. We will not be considering weight as as a resistive force. Okay, weight is not going to be considered here. The work done by the weight or the work done against the weight is actually already incorporated in the change in potential energy. Remember what this is? Mg into delta H. That's what potential energy is. Mg into delta H. Mg is weight. Weight into change in displacement. Weight into displacement. That's the work done by the weight or the work done against the weight. That is already incorporated in change in potential energy. If we also include that in driving force and resistance here, that will be double counting. So we don't include that here. Okay. So driving force does not include weight, and resistive force does not include weight. We use this in all cases, but just remember, in driving force, we will not include weight. In resistance, we will not include weight. So we can use this for horizontal surfaces, inclined surfaces, any surfaces, curved surfaces. This always works, this work energy principle. Just remember that weight is not going to be considered as part of driving force or resistive force. Okay. Then you have conservation of energy. It's actually a special case of this work energy principle. This will work everywhere. There's a special case for this, and that is when there is no driving force and no resistance. So sometimes what happens is there's zero driving force and there's zero resistance. Okay, there's zero driving force and there's zero resistance. So driving force is zero and resistance is zero. In that case, in this work energy principle, what happens is this value becomes zero, this value becomes zero. That means the total change in kinetic and potential energy, that turns out to be zero. The total change is zero. If the overall change is zero, that means whatever was the initial initial sum of kinetic and potential energies, that's going to be the same as the final sum of kinetic and potential energies. Okay. That's called conservation of energy. When there are no external forces, when there's no driving force and there's no resistance, when both of these conditions are met, in that case, we can say the total energy of the object remains conserved at any point in the journey. If you were to find the total energy, kinetic energy plus potential energy, their sum will always be equal to each other. Okay, so this is what happens. Not necessarily that loss in kinetic energy is equal to gain in potential energy or something, because sometimes you have both happening at the same time. So you, at some point, you might have both kinetic and potential energy. So this is a more general form for that. At every single point, when you add these two things up, they should be the same, right? That's the general rule. When there is no driving force and there's no resistance. Now, this is optional. If you want to use this, you can use it. Otherwise, everything can be done using the work energy principle as well, because that's just coming from this general equation. You could also just write this as zero, and then just find change in kinetic energy here, change in potential energy here, input their values, and you can find any unknowns that you have to. That'll work in every case as well. This is just going to work when there's no driving force and there's no resistance force. In that case, you can use this conservation of energy as well. Now, the next thing is power. Power is also a scalar quantity. Its unit is watt. Okay. Power is defined as the rate of work done. And one formula for that is power equals work done over time. In short form, we can say that's power equals P equals W over T. And that can then be converted to a form like this as well. Power equals driving force into velocity. These are the two power formulas that we've got. Power equals work done over time, and power equals driving force into velocity. Okay. Now, mostly we will be using this formula, driving force into velocity. In some cases, when you have time given or you have to find the time somewhere and you have power involved, in only those few cases, you will have to use this first equation as well. You need to know both of them, of course, but mostly you will see that the second formula is going to be used here. Okay, W is work done, right? So W can be written as F times D, force into displacement. So that gives us this. So this is one equation, and this is another. This is another formula. These are two formulas that we've got for power. You need to remember them. None of these formulas are given in the formula sheet. You need to remember them. Okay. Now, a lot of times you will see that you will be using these two formulas together in this topic. Power equals driving force into velocity, and resultant force equals mass into acceleration. For example, if we have a situation like this, we have an inclined surface and we have this block and it has some forces acting on this. There's a driving force acting in this direction. There's a friction acting in this direction. There's just a normal reaction here. We've got weight components acting. All of these are there. And we have some power given. And we have to find something missing in the data. Maybe driving force might be missing. We might have to find acceleration. We would often be using these two formulas together. Power equals driving force into velocity and resultant force equals mass into acceleration. Why? Because they're connected by this driving force that's common between them. So we can connect them using the driving force. When we write down the equation for the Newton's second law of motion, we would have a driving force minus the backward forces equals mass into acceleration. And this is going to connect these two things then, these two formulas. So these will be used together a lot. Just keep that in mind. These two formulas are used together a lot in this topic. Okay, let's move on. Now, in some questions, you will see they will tell you that the acceleration at a particular point is maximum or minimum. Speed or velocity at some point, velocity or speed at some point is maximum or minimum. Now think about the velocity time graph. It would look something like this, right? When you have a maximum value, that means the gradient at that point is going to be 0. So whenever you have maximum speed or velocity, what that means is they're basically telling you that acceleration value is going to be 0 in that case. So when you use Newton's second law of motion there, you would say resultant force equals mass into acceleration. That means if acceleration is 0, then resultant force is going to be 0. That means the forward forces minus the backward forces, they should equal 0. And that gives us the forward force is equal to the backward forces. In this case, when acceleration is 0, forward forces and backward forces are going to be equal to each other. Okay. The other cases when acceleration is 0 are when velocity is constant, or so they could say it's constant velocity, constant speed, or they could say it's steady speed or steady velocity. In that case as well, acceleration is going to be 0. And this is going to hold true there as well. Forward force is equal to backward force. It could be true at rest. And also, as we talked about, maximum speed, because that's the turning point of this graph. At that point as well, acceleration is 0. In all of these three cases, remember, resultant force is equal to 0, or you can say the forward forces and the backward forces are going to be equal to each other. It's not always going to be that driving force is equal to resistance, because we could have some other forces as well. For example, in this situation, if it was constant velocity, you would say driving force equals friction plus W sine theta, right? Forward forces equal the backward forces. It's not always just driving force equal to resistance. It's all forward forces equal to all backward forces. All right. Okay. Let's have a look at some questions now. That's all that you got in terms of the basic concepts in this topic. But now in questions, you will see some more complications coming up. Let's say we've got this example. It's a fairly straightforward one. First up, we've got mass of a crate, that is crate of mass 50 kilograms. And we are given that it's moving on a horizontal surface by a force of magnitude 400 Newton acting at an angle alpha from the horizontal. So you can see that here, there's a force acting here. Because of that force, the object is moving to the right side. And it's moving a distance of 20 meters. So it's moving a distance of 20 meters because of this. There's resistance of 250 Newton that is opposing the motion that acts in this direction, 250 Newton. First of all, what's the increase in kinetic energy? Just use the change in kinetic energy formula. Work done against resistance, how do you find that? You've got the resistance value, that's 250, times the displacement, that's 20, and that gives you the work done against resistance. Now, whenever they talk about work done against resistance, and you can figure out that they're talking about speeds, they're talking about the height changing somewhere, that's a clear indication for you that you would be using work energy principle. Especially this thing, work done against resistance, in almost all questions that involve this, because of this being there in this equation, you'll be using this work energy principle. So they are saying now in the third part, find the value for alpha. So now we have already got the change in kinetic energy. We've gotten the work done against resistance. We know there's no change in potential energy because the height is not changing. That's going to be 0. Using all of this, we could say, let's input those values in this work energy principle. Change in kinetic energy, that's 100. Change in potential energy, 0. Work done against resistance, 5,000. Work done by the driving force, what would that be? We had that force given. That force was 400 Newton. 400 into cos of alpha, that's the component of force acting in that direction, times 20, that's the work done by driving force. And just solve that, find the value of alpha from that. So this equation will be used a lot in this topic. Let's have a look at another example. We've got this car of mass 1200 kilograms that is traveling along a straight horizontal road. We've got the power of the car given, that's 20 kilowatt. Be careful about this unit. A lot of times they give power in kilowatts. That means it's 20,000 watt. In the formulas, you will always input the standard unit, that's watt. You will convert it to watts first of all, and then input that value in the formula. The resistance to the car's motion is constant, and it's equal to 500 Newton. The car passes through points A and B with these speeds. Find the acceleration of the car at A. Now, how do you find that? Power is constant. The resistance is also constant. Do we know anything about driving force? Is the driving force constant? We don't know that. So we cannot assume that we can use constant acceleration formulas here. In work, energy, power questions, avoid using constant acceleration formulas. Avoid using equations of motion. You can use this, of course. This works every time. But the constant acceleration formulas, they will very rarely work in work, energy, power questions. So as long as you can find a way to do it using work energy methods, prefer that. That's going to be easier as well. Use work energy methods. You can only use constant acceleration formulas if you are sure from the question statement that all forces are constant. In that case, yes, you can say that acceleration is constant, so you can use those formulas. Otherwise, avoid them. You want to find the acceleration of the car at A. How do you do that? You've got power given, and you've got the speed given at the point A, that's 10. Using that, you can find the value of driving force. And then use Newton's second law of motion to find the value of acceleration. That gives you this value. And then it says, by considering work and energy, find the distance AB. Now we've already found, we already know the value for the driving force. That's 2000 Newton. Using that, we can find the work done by the driving force, because the distance is 30. The distance is what? No, okay. So we do not use that because the distance is not given. We have time given instead. That's 30.5 seconds. If we have time given, we can use the other power formula to find the work done, because power is given, time is given, and that gives us the work done by the driving force. That turns out to be this. And then change in kinetic energy plus the change in potential energy plus work done against resistance. That will be 500. That's the force. times the displacement, and that's what you have to figure out. It's called that D. Simplify that, and you get a result from that. Okay. Now, something just came to my mind, but I'm forgetting now. Work done against resistance. There was a small point that I wanted to mention here. Yeah. So a lot of times you end up confusing resistance with work done against resistance. Please make sure that you don't do that. Resistance here is a force. This is 500 Newton. In the formula here, this is work done against resistance. Do not just input 500 here. It's supposed to be the work done against resistance. So 500 times the displacement, and that will give you the result. Okay. Let's have a look at this now. It says a cyclist and his machine have a total mass of 80 kilograms. The cyclist starts from rest and then he freewheels. Okay, so that was the important thing that I wanted to mention from this question. When they say there's a cyclist and that's freewheeling, he or she is freewheeling, that means there is no driving force. Driving force is zero. In this case, they've explained that here as well. Without pedaling or braking, what does that mean? There is no driving force. There's no driving force in this case. So there's no driving force. Just keep that in mind. And the rest of it, you can do it relatively easily. I'll just show this working for you. You can have a look at this in your own time. It's just the use of that work energy principle multiple times. Okay. All right. Yes, that's also fine. Work done. But how do you find work done here? Because work done against resistance is also unknown. So you can't find the work done by the driving force unless you've got this value here as well. It'll be in terms of D. So then you'll have to make that equation in terms of D and then input that there. That's possible. That will also work, but it might be slightly more lengthy, but that's possible. Yes, you can do that. A smooth slide AB is fixed so that its highest point A is 3 meters above horizontal floor. Now, whenever you have a curved surface like this, never use constant acceleration formulas here because direction is changing at every single point. So the acceleration can never remain constant. Now, in such problems, a lot of times, you can use conservation of energy. Why? Because in many cases, this will be a smooth surface. Not always, sometimes it can be rough as well. In that case, you'll have to use the work energy principle, work done by driving force that equals change in kinetic energy plus change in potential energy plus work done against resistance. In general, you would use that. But when it's a smooth surface and there are no forces acting externally, no driving force, no resistance, you can also use conservation of energy. And that's the case in this case. There's no driving force, there's no resistance. So you can use conservation of energy here. So they're saying P is released at the point A. It's released from rest. Now, we have to find the value for H such that the kinetic energy of P at B is 1.62. So all we do is find the total energy at the point A, find the total energy at the point B, kinetic plus potential, equate them. Since the energy is conserved here, there's no driving force, there's no resistance. So energy is conserved at every single point in this journey. The total energy is going to be the same, right? So we use that to find the value of H there. Then it says kinetic energy of the particle immediately before it reaches the ground. So at this point, what's the kinetic energy? Again, use conservation of energy, and that will give the result. You can do that. And then they want you to find the ratio Vg to Vb. Now, sometimes they ask you for ratios like this. How do you deal with this? You'll find the Vg value, you'll find the Vb value, and just find their ratio by writing them as a fraction. So in this case, what's Vg? Vg is the velocity at this point. Vb is the velocity at this point. Now, again, you can say the total energy at every single point should be the same. So whatever is the total energy at the point B, and the total energy at the point A and the total energy at the point G, they should all be the same. So we can make equations like this. Kinetic energy at, in fact, in this case, we had already found the kinetic energy earlier. Yes, that's actually done in the previous part. We have found the kinetic energy at the point G. Using that kinetic energy at the point G and the kinetic energy at the point B, we already know the kinetic energies both of those points. So we can find their velocities corresponding to them and find their ratio like this. So when they ask you for ratio, what you do is you find these two values separately and then provide them as a fraction like this, and then simplify that, whatever it comes to, that's going to be written in ratio form like this. So when they ask you for ratio, you find those values, write them in fraction form, and then you write them in ratio form like this. How do you know that energy is conserved? Because there's no driving force. The particle is released from here. There's no forward force that's acting. There's no driving force, and there's no resistance because it's smooth. It's a smooth slide. There's no friction. There's no resistance. So when you have both of these conditions met, no driving force, no resistance, that means that the energy is conserved. Now, in the case that P is released from the point X, what happens in this case? Now they're saying it's released from rest at this point. It's a separate case. Whatever we found in the previous part, that's no longer relevant, except, of course, the height of H. That's not going to change. If the height is 2.2, that remains 2.2. But now the particle is released from the point X, from rest. We need to figure out the value of capital H to two significant figures. Now, for this, again, we use conservation of energy. We say energy at this point, energy at this point, energy at this point, they are all going to be the same. So we make three equations from this like this. We say the total energy at X, total energy at B, total energy at G, they should all be the same. And from this, we can break it down into two parts like this. We get three equations. One was given in the question already, VG over VB, that was 2.55. And then the other two, we end up having to solve three simultaneous equations. We will eliminate the variables that we do not need and find the value of capital H from this. So sometimes this algebra can sometimes be a bit more complicated. You have three unknowns and you have three equations. The value that you're looking for is capital H. You try to eliminate the other variables from the other two equations and then just find the value for H like this. Okay. So in this case, if you were to use work energy principle, that will make things more complicated because that will be a more complicated equation, right? So once you understand that there is no change in, there's no driving force and there's no resistance, in that case, it's easier to use conservation of energy directly. In this case, it's much easier this way. The question says it's released from rest. So let me find that again. Okay, yeah. So the particle is released from rest at a point on the slide. Okay. So in the first case, it's released at A. So it's released from rest at A. And the second case as well, it's released from rest at this point. Okay, so it's given in the question. All right, let's move on. So we just use conservation of energy. We equate all of them and we get the result from them. We solve these equations simultaneously. You can have a look at this working. It's just algebra. That's how it works. Let's have a look at this example. Now, sometimes you have inclined surfaces. Sometimes you have inclined surfaces. Okay, let me come back to that at the end. At the end, you can ask me any specific question that you have there. The car comes to, so there's a car that comes to the bottom of a straight hill that has the length of 316 meters. So you can have inclined surfaces like this as well in work energy problems. In this case, what you're given is that this length is 316 meters. And the angle that this plane, this surface makes with the horizontal is theta. I'm calling that theta. The angle is given to be sine inverse of 160. So that means theta is equal to sine inverse of 160, which implies that sine of theta, that is equal to 1 over 60. Okay, so that's the value that we're given. We're given the work done against resistance. We're given power that remains constant at 16,000 watt. Resistance is no longer constant. So in the previous parts, the resistance was constant in this question, but in this case, they're saying resistance is not constant. If it's not constant, It's a clear indication that you cannot use constant acceleration formulas here. The time taken is given to ascend the hill, to go from the bottom to the top. The car is traveling at 20 meters per second at the bottom, and we have to find the speed at the top. Now, it's a classic case of work energy principle. You've got power given, you've got work done against resistance given, you've got this hypotenuse given of this triangle. You have the speeds given. You can find the height somehow, and you can use concept work energy principle. Work energy principle looks like this: work done by the driving force that equals change in kinetic energy, and so on. What's the work done by driving force going to be? We've got the power value given, that's 16,000 watt. We've got the time given. Since we have time given, we use this formula to find the value of work done, and that turns out to be 240,000. We input that value here. Change in kinetic energy, what would that be? If we consider the final velocity as v, the change in kinetic energy, that's going to be half into m. Mass of the car was given as 1200 kilograms. 1200 into v square minus 20 square, that gives the change in kinetic energy. Potential energy, for that, you'll have to find that change in height. How do you do that? You can make a right angle triangle like this. You're given the hypotenuse, that's 316. You know the angle, that's theta. Find the value for h. And from that, you can find the change in potential energy, plus the work done against resistance, that's this. And that will give you the value for v that we were looking for. That's 6 marks, fairly straightforward. Just a simple application of work energy principle like this. Okay. Sometimes it can become more complicated. So you have you've got multiple objects like this. You've got a car and a trailer. They're connected like this by a string. And you've got some forces acting on them like this. In the first part, they say F is equal to 100. Find the acceleration and the tension in the tow bar. How do you do that? Represent all the forces acting on both of them, like we normally do in Newton's second law of motion. Tension, there's no resistance here. Okay, so resistance is given. Resistance is given. We don't have to consider friction separately. When they give resistance, that includes friction anyway. So that means we can ignore normal reactions because they are only going to be required when you have friction involved. So we can just ignore them for that reason. Represent all the forces, apply Newton's second law of motion, both of them separately, and then find the values of T and A. That's really straightforward. That's Newton's second law of motion. Do not forget the weight components. A lot of times people end up forgetting the weight components. There are going to be weight components acting in this direction as well. You have to consider them. In Newton's second law of motion, you do consider weight. But then in the second part, it says it's given instead that the total work done against F in moving a distance of 50 meters up the road is 6,000 joules. So we know there's a force, there's a friction acting in this direction, and its value is given. Resistance acting in this direction, its value is given as F. Work done against that resistance, what is that? That is 6,000 joules. Again, work done against resistance. Does that remind you of something? Again, work energy principle. And they're specifying here as well, whenever they say use an energy method, that means this equation. Okay. The speed of the car at the start is given, that's 50 meter, that's 20 meter per second. And this journey is of 50 meters. How do you find the speed of the car at the end of the 50 meters? Now, notice the car and the trailer, they're connected to each other. So whatever is the speed of one is going to be the same speed for the other as well, because they're connected to each other. They've given the speed of car, the speed of the trailer is going to be the same as well. Now, to find the energy here, you can see both of them are moving in the same plane. So whatever is the change in height for one, it's going to be the same for the other as well. And whatever is the speed for one, it's going to be the same for the other as well. So we can consider this thing as one whole system. Rather than calculating them separately, you can calculate them separately as well, that's possible. But you could just consider it as one whole system and just do the calculations together for them. How do you do that? Work done by the driving force. What's the work done by driving force? We are given the work done against resistance. Did we have any value here? Okay, so driving force was given here. That's 3,000 Newton. That was given in the beginning. That is 3,000. That's still 3,000 here. You're traveling a distance of 50 meters. So 3,000 times the displacement, that's the work done by the driving force. Change in kinetic energy. Now, for change in kinetic energy, you consider the total mass of the car and the mass of the trailer. The total mass turns out to be 2,100 kilograms. So in this formula now, you can directly just input half into 2100 into v squared, that's the final speed, minus u squared, which is 20 squared here. And that gives you the change in kinetic energy. You can also do them separately, but that will just make it longer, but that's also possible. You can do that. Similarly, for potential energy, you find the change in height. How do you do that? Making this right angle triangle. The hypotenuse is 50. What's the height going to be? You can find that using sine. And that gives you the change in potential energy. And then work done against resistance. What's the work done against resistance going to be? They have given us the work done against the force F. We do not need to find F here. I'll just remove that from here. We are already given the work done against the resistance. That's 6,000 for the trailer. But for the car, it's not given. On the car, there is another resistance acting, and that is 800 Newton in the backward direction. So for that, you have to find the work done against resistance separately now, because they only gave it for the trailer. They did not give it for the car. So for the trailer, it's 6,000. For the car, it's 800 times 50. And then you just solve this equation, find the value of V like this, and that gives you the result. So you can have multiple objects like this sometimes. You can consider that whole thing as a single system if they are both on the same plane like this. But then sometimes okay, just a couple of examples. Sometimes they talk about vertical distance, just like we did one example earlier in Newton's second law of motion. Let's consider this now. It's given that this plane is rough, so we have this plane, and we have the particles that are in limiting equilibrium. In the first part, they ask us to find the coefficient of friction between V and the plane. We just represent all the forces, equate the opposite forces, and that gives us the coefficient of friction. That's pretty straightforward. The first part, 6 marks, easy 6 marks, the first part. But then it says, now what's happening is, it's given instead that the plane is smooth. And the particles are released from rest. The particles are released from rest. When the difference in the vertical heights of the particles is 1 meter. So initially, at this point, A is here, B is here. The difference between their vertical heights, that is 1 meter. And they are saying, use an energy method to find the speed of the particles at the instant when the particles are at the same horizontal level. Now, how will they be at the same horizontal level? A will move downwards in this direction by some distance, and B will move up the plane by some distance. Now, we don't know how much distance they're traveling, but they're connected to each other. If this distance is x, this is also going to be x, right? But then, since we want to use the energy method, we have change in potential energy here. For change in potential energy, we need to figure out exactly how much is A moving down vertically and exactly how much is B moving up vertically. That's the key part here. The rest is very straightforward because we've got the speeds given. We can find the change in kinetic energy from that. We've got the value for resistance given as well. I think we'll have a look at that. In fact, there's no resistance. It's a smooth surface. There is no resistance. So that's just going to be 0. So the only complication is how to find change in potential energy because we do not know how much are the particles moving in the vertical direction. Now for that, we do something like this. We say, if A is moving x meters downwards, then B is moving x meters in this direction. Now for B, what we can do is we can make a right angle triangle like this. So I've made that bigger on the right side. We know this side is x. We know this angle is 30 degrees, right? Corresponding angles. And now, if this total distance was 1 meter, A is going down by x. When they come at the same horizontal level, how much has B moved up by? 1 minus x. So the vertical height, change in vertical height for B, that is going to be 1 minus x. So in that triangle now, we can say this side is 1 minus x, this is x. And we can find the value of x from this, use sine, and that gives you x equals 2/3. So now we know exactly how much vertical height is changing for both of them. The value for x is 2/3, so this is 2/3, and this is 1/3. 1 minus x, that will become 1/3 then. So we know that A is going down by 2/3, and B is going up by 1/3. And now using that, you can find the change in potential energy. How do you do that? Work done by driving force, there's no driving force here. So we ignore that. Change in kinetic energy. Now, speeds are going to be common between them, right? Whatever speed A is moving at, B is also connected to that. B is also moving at the same speed. So we can consider that together for both of them. If you want, you can also do it separately. You could also do half into 4 into v squared minus 0 squared for A, and then half into 3 into v squared minus 0 squared for B separately. That will work. But since the speeds are common between them, we could just combine them like this in one expression. The total mass is 4 plus 3 into v squared minus u squared divided by 2. That's the change in kinetic energy. But potential energy cannot be calculated together because the changes in height are different for both the particles, right? Changes in height are different. A is moving down by 2/3 and B is moving up by 1/3. We have to calculate the change in potential energy separately for both of them. Now for A, how do you do that? mg into change in height. Mass is 4. G is 10 into change in height. Height is decreasing by 2/3. So we put a negative value here. When it's a decrease, we put a negative value. You can either put a negative value with the height there so that the overall number becomes negative, or just directly put negative value here because it's a decrease in potential energy for A. For B, we can say it's mass of B into 10 into change in height. That's 1/3. And then you just solve this equation, find the value for B. It's a 6-mark question. Again, it's more for the thinking involved in this. The actual calculation is not that much. That's the value that you get from this. Why are we considering it? Why would we not consider it? Both particles are moving, right? The overall for the whole system, we know that the driving force, work done by driving force, is supposed to be equal to change in kinetic energy plus change in potential energy plus work done against resistance. We have to consider everything in the system, right? Let's consider this example. Again, it's about change in vertical height. They're saying two particles P and Q of masses 2.5 kilograms and 0.5 kilograms. They are connected by a light string. P is 2 meters above the level of Q like this. Vertical distance between them is 2 meters. And again, what they're saying is, find the acceleration of P first of all. When P is released from rest, the string taut, the pin is rough with the coefficient of friction this. You just represent all the forces, apply Newton's second law of motion on both the objects, you find the acceleration. From that, the first part is pretty straightforward. Simple application of Newton's second law of motion. But now in the second part, it says, use an energy method to find the speed of the particles at the instant when they are at the same vertical height. Again, we think of it the same way as before. P moves down the plane, Q moves up the plane. If Q moves up by x units, P moves down by x units, right? For P, then, we can make a right angle triangle like this. In that right angle triangle, we can say, if this is x, then the remaining part, this part, that's going to be 2 minus x. So we have this right angle triangle with perpendicular is 2 minus x, hypotenuse is x, sine 30 equals this. Find the value of x from that, and you get 4/3. That means the change in height for Q is 4/3. If that's 4/3, what's the remaining change in height for P? That's 2/3. And again, height for P is decreasing. So we put negative with that in this equation. Height for Q is increasing. We put positive with that. It's a smooth surface, so there's no resistance, and there's no driving force because there's no force acting apart from weight in the forward direction as well. Solve this equation, find the value of V. Again, 5 marks. This is what you have to do. Exactly the same question. These are both from recent papers. You need to make sure that you understand this well. Yes, in this case, you could use conservation of energy as well because there's no driving force, there's no resistance. Conservation of energy would also work. Yes, that's correct. You could use that. That will work in this case because there's no driving force and there's no resistance. All right, I hope that was helpful. We stop at this point. If you have any questions, you can let me know. Okay, so let's look at the next topic that we've got, and that's momentum. Momentum is again a vector quantity now. The direction matters in this case. Okay. Momentum is defined as mass into velocity, and it's a vector quantity. In short form, we often write it like this: rho equals m times v. Since m is already used for mass, we don't use m for momentum. It's a symbol called rho in Greek, but you can just think of it as p as well, very similar to that. Unit for momentum is kg meter per second. Kg from mass, meter per second from velocity. That's the formula that we've got for momentum. Let's suppose we got these people running like this. One has a mass of 70 kilograms, the other and he is running at a velocity of 4 meters per second to the left. And similarly for the others, what are their momentum going to be? 280, 490, and 665 respectively. The person who is heavier, he's going to have more momentum. The person who is running fast, he's going to have more momentum. So it depends on two things: mass and velocity. Now that's one formula that you need to know of. And then the next main thing, and the only main thing that you have in momentum is conservation of momentum. And that basically says whenever you have two objects that collide with each other, so you will be using momentum when you have two objects colliding with each other. You would say the total momentum before collision, that's going to be equal to the total momentum after collision. The momentums before collision and after collision, they're going to be equal to each other. All right. Now, what does that mean? Let's say you've got a set of objects like this, object A and object B. These are two balls or two spheres. A is moving towards the right side, B is moving towards the left side. A is moving at a speed of 5 meters per second to the right. B is moving towards the left side at a speed of 2 meters per second. We know the initial speeds. Now, at some point, they're going to collide with each other, assuming that the surface is smooth. So they keep moving at the same velocities, and then they collide with each other. After collision, what happens is B starts moving to the right at a speed of 4 meters per second. What's the velocity of A after collision? Now, for finding this, we can use conservation of momentum. We can say before collision, we know that the velocity for A is 5 meters per second to the right. For B, it's 2 meters per second to the left. Now, in momentum, it's important that you consider one direction positive for all objects. In kinematics, that was not necessary. And as we will see later, we'll have questions in which we'll have both kinematics and momentum. For kinematics, you can use different directions positive for different objects. So if you have one object moving in this direction, I could say for A, this is positive, for B, this is positive. In kinematics, we could do that because we were making separate equations for them and then solving them simultaneously. In momentum, we cannot do that. For all the particles in the system, we have to consider a single direction positive. Okay, so because we have to put them in a single equation, conservation momentum equation, we cannot consider different directions positive. So if I say right side is positive, then the velocity for A is 5 meters per second, and the velocity for B, that is going to be negative 2 meters per second. After collision, velocity for B is 4 meters per second to the right. And we have to find the value for VA. How do you do that? You can just input values in that conservation momentum equation now. Momentum before collision, that's going to be mass of A into velocity of A plus mass of B into velocity of B. That equals momentum after collision. After collision, mass of A into velocity of A, that's what you have to find out. And mass of B into velocity of B after collision was 4 meters per second. Solve that and you get the value for V from that. And that's it. That's conservation momentum. So in terms of concepts for momentum, this is pretty much all that you have. As far as momentum is concerned, you just have to use conservation momentum like this. But the complications come when it is combined with other topics. Sometimes it's combined with energy. They ask you about the energy before, energy in the very beginning, the total energy at the very end, the loss in energy or the gain in energy. That's generally easy to figure out. But when they combine it with kinematics, that's where you get some very difficult questions, as I'll show you later. In this case, the velocity of A after collision turns out to be minus 5.8. Since we were considering the right side is positive, and it's turning out to be negative, what that means is A is moving towards the left side at a speed of 5.8 meters per second. While applying conservation momentum, as we discussed, keep the same direction positive for all objects in the system. All right, let's have a look at this example. We've got three different spheres. They have their masses given, and we know their speeds. They were at rest initially, and what happens is A is projected towards B at a speed of 6 meters per second. B is at rest, they collide with each other. What's the speed of B? We can find that using conservation of momentum, right? You can see that here. Then what happens is B collides with C, and in this collision, both of these spheres coalesce. Coalesce means they merge, they combine and become one single object. So their masses get added together as well. Find the speed of D after this collision. So now, in the second part, what's happening is after the first collision, B started moving at 8 meters per second to the right. C was at rest. So B now collides with C, and the particles coalesce and become this object D. All right. Now, before collision, we know what their momentum is. After collision, we know what the momentum is. We can solve this equation, find the value of V from this. Okay. All right. Then they're saying find the total loss of kinetic energy due to the two collisions. We have to show that the total loss in kinetic energy is this. How do you do that? Find the initial kinetic energy in the very beginning. What's the initial kinetic energy? Initially, only A was moving, and that was moving at 6 meters per second to the right. What's the energy for that? That's half into 4 into 6 squared. At the end, at the very end, we have D that is moving at 3.2 meters per second now. And we've got A that's moving at 2 meters per second. So the final kinetic energy for A, that's this. And the final kinetic energy for D, that is this. Input values in this, we get the result. And you can see what that turns out to be. It's 33.6 joules. Find the difference. That gives you the change in kinetic energy. Since I talked about the loss is just 38.4 joules. That's what we were looking for. Okay. All right. Let's have a look at this example. Sometimes they make it slightly more confusing. For example, in this case, they're saying we have two objects. They have these masses, 4 kilograms and 10 kilograms. They lie on a smooth horizontal plane. Initially, B is at rest, and A is moving towards B at a speed of 6 meters per second. All right, so B is at rest, and A is moving towards this side. After the collision, A moves with speed 1.5 meters per second, and B moves with speed 3 meters per second. And they have not specified in what directions they are going to be moving. We just know that A is moving at 1.5 and B is moving at 3 meters per second. Now, how do we know? B was at rest. A is coming from the left side and hitting it at some speed, right? Now, the only direction that B can move in is the right side, right? You can't have it like this, that A hits B from the left side and B starts moving towards left. That does not make any sense. So B can only move in the right direction. That's the only possible direction for B. But A, it could either move towards the right side at 1.5 meters per second, or it could move towards the left side at 1.5 meters per second. Both possibilities are there. And it's not clear from the question statement which direction it is going to be moving in. So what do we do then? We consider two cases. They want us to find the two possible values of the loss of kinetic energy. Where do two possible values come? Because of these two possible scenarios. Case one is that A moves towards the right side. In that case, its velocity is considered positive after collision. In the other case, A moves towards the left side after collision. Find the mass for we have mass missing, right? That's the only thing that's missing. Yeah. Find the mass for object B using both of these cases. And then what you can do is you can find the change in kinetic energy at the end, and that will give you the two possible values of the loss in kinetic energy. Make sense? All right. In the previous case, when two objects coalesce, when they combine and become one single object, remember, the mass is going to get added. So when B and C coalesce, the total mass is going to be 2 plus 3, and that is 5 kilograms. The total mass is going to be 5 kilograms here. For B, we're using 5 kilograms here. Okay, let's move on. Let's consider this now. We've got these smooth, small spheres. They have equal radii, and we have their masses given 4 kilograms and 2 kilograms like this. B is at rest and A is moving towards B, and we have to find the speed of B. That's simple conservation of energy, conservation of momentum concept. Let's look at part B here. That's the important part that I want to show you. In this case, it says there's a third small sphere that's right here. It's at rest. B collides with C after the first collision. After this collision, B continues to move in the same direction with 1/3 the speed of C. Now, what does that mean? Whatever was the speed of B, the speed of C would be 3 times that. So if you consider this as VB, this would be 3 times VB, right? Or you could also consider the other way around. You could say if the velocity for C was this, then the velocity for B would be 1/3 times VC, right? Either way works. It's better to avoid fractions and just write like this. If this is VB, then this is 3 times VB. What you can do now is, using this, you can find the velocity of B and C after collision using conservation of momentum. They're saying show that there's another collision between A and B. How do you show that? After the first collision, in the first part, A was moving towards the right side at 5 meters per second. Now, what about the velocity of B after this collision, after the second collision? When we calculate that, that turns out to be 4 meters per second. And now think about what's happening. A is moving at 5 meters per second to the right. B is moving at 4 meters per second to the right. How do we show that there is another collision? A has a greater speed, B has less speed. Eventually, A is going to catch up with B, right? Eventually, A is going to catch up with B. So that means there is a collision. Since velocity of A is greater than velocity of B, that means they are going to collide with each other. Okay? All right, let's move on. Yes, of course, that can happen as well. They can have same mass as well. That's possible. Of course, there's no restriction on that. Then the third part is relatively straightforward. You have to find the total loss of kinetic energy after another collision. So that's not that difficult. But that's the point. If you want to prove that there's another collision, you find the speeds of both the particles. And then based on that, you can argue if one is greater than the other and the one that has greater speed is behind, that will eventually catch up with the other object. Okay, let's consider this now. So again, we've got these 3 particles that we have their masses given. It's a smooth horizontal plane. P is projected towards Q at a speed of 5 meters per second. After P and Q collide, P rebounds with speed 1 meter per second. So after collision, this is what happens. What about the velocity for Q? Do we know what that is? We can find that. That's what we want to find out in the first part. We just use conservation of momentum, find that value. That turns out to be 3 meters per second. That's really straightforward. In the second part, it says Q now collides with R. Immediately after the collision with Q, R begins to move with speed v meters per second. So now we've got a collision between Q and R. Okay, so we've got these 2 objects, Q and R. Now they collide with each other. We have their masses given. Q was moving to the right at 3 meters per second. R was moving at 0 meter per second. And after collision, what happens is R starts moving with speed v meter per second. Of course, it's going to move to the right side because it was at rest. Q hit it from the left side, so R is going to move towards the right side at a speed of v meters per second. Now, they want, given that there is no subsequent collision between P and Q, find the greatest possible value of P. How do you find this? How do you find that there is no subsequent collision? Now, after the first collision, P was moving towards the left side at 1 meter per second. Okay. After collision, P was moving towards the left side at 1 meter per second. what speed will Q have to move at such that no collision happens between P? What's that cutoff point? If Q was moving towards the left side, or let's consider this first, if Q was moving towards the right side at any speed, would there be another collision? No, because P is moving towards left, Q is moving towards right. There will be no collision in that case. If Q was moving towards the left side at 3 meters per second, let's say, will there be another collision? Yes, because Q will eventually catch up with P and there will be another collision. If Q was moving towards the left at 0.5 meters per second, what about that? Then there will be no collision because it will not be able to catch up with that. At what point do you have that cutoff? When it has the same speed, 1 meter per second to the left side, when they're traveling at the same speed to the left side, they will keep moving at the same distance. They will be same distance apart from each other throughout, and they will never collide when the speeds are the same. If Q's speed increases even slightly more than this, even slightly more than 1 meter per second, then what happens is they end up colliding. So what we do is we consider this extreme case, and that will give us the corresponding greatest possible value for V. This is where you have that cutoff point that is going to give you the extreme value. The extreme value that we have for Q, that's going to give you the extreme value for the velocity for R. So we consider this velocity as -1 as it's traveling to the left side. Apply conservation of momentum on this, find the value of V from that, and you get this. This is the maximum possible velocity of V that we get. That's 1.6 meters per second. If V was even slightly more than this to the right side, to balance that, Q will have to move at a greater speed to the left side and they will end up being collision. So we consider this cutoff point, 1 meter per second. When you have the maximum velocity for Q in the left direction, that gives it corresponding maximum velocity for V for R in the right direction. And that turns out to be 1.6 like this. Okay. All right. Now comes the more difficult part when you have kinematics and momentum coming together. Okay. Let's have a look at this example. So we've got this particle P that's right here. And it's going down the plane like this. This plane is smooth. And what happens is that this particle comes down, reaches this point at the bottom of the plane. Let's call that point Y. And then it travels to the right side. And after the collision, P continues moving in the same direction with speed 2 meters per second. So P comes here and then goes towards Q and it collides with Q. There's a collision that happens and then it continues to move in the right direction. We have to find the speed of Q after collision. Now, how do you do that? You break the journey into multiple parts. First of all, P has to come down from that point to this point. How do you do that? You know, initial velocity is 0. Displacement is 2.5, acceleration 10 sine 30. It's a smooth plane with weight as the only force. We can find the final velocity at the point Y. Once we have that velocity, then we consider the Y to Z part of the journey. Now, this part is also smooth, right? The flat part of the plane, that is also smooth. If that is smooth, that means acceleration is 0. It's going to move at constant velocity. Whatever was the velocity at the bottom here, 5 meters per second, it keeps moving at 5 meters per second and hits Q at a velocity of 5 meters per second. And then use conservation of momentum, find the velocity of Q after collision. That's how you can do it. That's fairly straightforward, the first part. That will give you the velocity of Q after collision. But now they're saying it's given instead that the plane is rough. The horizontal plane is rough. The inclined plane is still smooth, but the horizontal plane is rough now. And when P and Q collide now, they coalesce and move with speed 1.2 meters per second. We need to find the coefficient of friction. How do we think about this? Now, smooth means constant acceleration. In this case, for horizontal plane, acceleration is 0 because there's no friction. That means there's no force. No force means 0 acceleration. If there's no forces acting, that's 0 acceleration. Okay. If you have forces acting and they're constant, then that means it's constant acceleration. It could be some non-zero value as well in that case. Okay, what about this? If the plane is rough now, This part of the plane is still smooth. So whatever was the velocity that we found here, 5 meters per second, that is still the same. That's still 5 meters per second at the bottom of the plane. But then after that, in this part of the journey, there's going to be friction. Okay. What they have given us is that P and Q collide and coalesce and become one single object, and we're given the velocity of the combined particle as well. Now, there are two things that we can do. Number one, for P's journey from Y to Z, we can use Newton's second law of motion to figure out at what velocity P is going to hit the particle Q. How do you do that? Use Newton's second law of motion, resultant force equals mass into acceleration, and see what that gives you. Forward force is 0, backward force is friction, equals mass into acceleration. We have to find the coefficient of friction. You get something in terms of mu here. This is what we're getting. Let's leave it like this for now. Then use conservation of momentum. Before collision, we know that P and Q were moving at these velocities. Velocity for P was Vp. Velocity for Q was 0. After collision, we know that that's 1.2 meters per second for the coalesced particle. Use conservation of momentum, and that gives you the velocity of P just before collision. And now you know at what velocity P arrived at the point Q. And you also know the acceleration in terms of mu, right? So now look at this part of the journey. It started from 5, ended at 2. The displacement was 1.5. You can find the acceleration value from this. Input that in that equation and find the value of mu from that. So when you have one part in which the particle is moving, you have to use constant acceleration formulas there sometimes, Newton's second law of motion there. And for collision, for the point of collision, you use conservation of momentum to find any velocity that is missing there. When it's a smooth inclined surface, we consider 10 sine theta as the acceleration. Yes, when weight is the only force. If there are other forces acting, then we have to use Newton's second law of motion. If there's no other force acting apart from weight, then yes, that's 10 sine theta for a smooth inclined surface. Okay. Now, these are, as I said, more complicated types of questions now from here on. So I'll be going through them. You will understand some of it, you'll not understand some of it. I will be posting all of them as a separate video. I'll post a link to that in the group and also in the recording that you get for this in the description below that as well. But I'll be adding all of these questions, okay, where you can have a look at them in detail and see how they will be done, okay? But I'll just quickly skim through them as in the different types of things that you need to know here. So I'll not go into a lot of detail here because it's not going to make a lot of sense if you're seeing these questions for the very first time. Just by going through them in 1 minute, they will not make a lot of sense. So in this case, what they're saying is, but let me just expose you to these questions that these exist in past papers. You need to be able to solve them, okay? There's a particle A that's projected vertically upwards from level ground with an initial speed of 30 meters per second. At the same instant, there's a particle B that's released from rest 15 meters vertically above A. So we've got these two particles. There's a point B here on top, there's a point A here at the bottom. A is projected in the upwards direction, B is coming down from there. The mass of one of the particles is twice the mass of the other particle. Now, they have not specified which mass is bigger, right? So that is a clear indication that we would have to consider multiple cases. One case in which one mass is bigger and the other case in which the other mass is bigger. And then during the subsequent motion, what happens is A and B collide and coalesce to form particle C. Find the difference between the two possible times. So that's where those two different values of time are going to come from because of those two cases that we've got, right? Now, A and B collide and coalesce to form particle C. Find the difference between the two possible times at which C hits the ground. Now, let's understand the situation. This is what is happening. A is projected from ground. B is coming from top. They collide at this point, and they become particle C. And then that particle C, it could, if it's moving upwards at this point, it might go like this. If its velocity is downwards, it might go like this. And at some point, it's going to hit the ground. Now, the time at which it hits the ground we have to find two possible times for that, two possible values of that time using the two cases that we will make and find their difference. That's what we're looking for. Okay. So how do you do that now? So there are different parts of the journey. First of all, before collision. Before collision, let's call this point X at the point they collide with each other. Before collision, A is going from the ground to the point X. We consider the upwards direction positive for that. Initial velocity is 30, acceleration is minus 10. And then for B, initial velocity is 0 in the downward direction. We're considering downward positive for that because it's moving in the downward direction. Initial velocity 0, acceleration positive 10. We've got these two values for this. Now, what are other values that are common between them? They both started at the same instance and they're colliding with each other. That means time is common, right? Time is going to be common between them. So we used time as another variable. And then we know something about displacement as well. If A is going up to this point here like this, its displacement from its starting point will be S times will be SA. And B is coming down from there, its displacement will be SP. Their sum is going to be 50. We get one equation from this, we solve this, find the values of T from this, find the value of T from this. Once we get that value of T, we find their velocities at the point of collision. Why do we need them? Because we have to use conservation of momentum to find the velocity after collision. So for that, we need the velocity at the point of collision. So once we have this time, we can find their velocities at the point they collide with each other. Okay, so we find the velocity like this. And then once we have that, use conservation of momentum. B is coming downwards, A is going upwards. We have their initial velocities. Afterwards, they coalesce. Now we have to consider two cases because their masses, we don't know which mass is twice the other. So we consider one case in which mass of A is M and mass of B is 2M. The other case in which mass of A is 2M and the mass of B is M. Mass of C is going to be 3M in either case because the total is going to be 3M. We use conservation of momentum. In one case, we get that the final velocity of C after this collision is going to be 5 meters per second. And in the other case, 15 meters per second. These are both positive values. We consider it upwards positive. What that means is after collision, C is initially going to move in the upwards direction. So now we consider what happens after collision. So in one case, C is going in the upward direction at 5 meters per second. It goes up and then it comes down at some point. In the other case, it starts at 15 meters per second after collision, and then again it comes down at some point. We need to figure out the time at which it hits the ground. How do you figure that out? Now this is free fall. What do we know about this part of the journey? We know the initial velocity. We know 5. If you're considering upwards positive, it's two-way motion, so we consider upwards positive. Acceleration is negative 10. That's all that we know. We don't have any other information. We don't have time. In fact, we have to find that. We don't have final velocity at which it hits the ground, but can we find displacement somehow? C starts from the point of collision. Can we find that point of collision somehow? That's the displacement of A from the starting point. So using the initial part of the journey, we can find the value for SA. That will give us the height of C above the ground at the point this collision happened. All right, so that's 13.75. So this height at which C was, that's 13.75. So what's the displacement value that we have then? You start from this point, you end at this point. Upwards is positive. You're going in the downward direction eventually. Displacement is minus 13.75. Whatever happens in the middle, that's irrelevant. In displacement, only the starting point and the end point matters. So displacement is minus 13.75. That's the value for displacement that we get. So that's the third piece of information that we've got. We use S equals ut plus half at square, find the value of time from this. One value turns out to be negative, the other positive. Then we do exactly the same thing for the other case. We find another value of t from this. And after doing all of this, you get 7 out of 8 marks. You have to do one more thing. They wanted you to find the difference between the two times. You find the difference. And that turns out to be 1.50. All of that for 8 marks. All right. So that's what happens when kinematics and momentum, they're combined. It becomes something so complicated. Okay. You will get better at these with practice. You make sure that you attempt these questions. They're added to the notes. Let's have a look at this now. 3 particles P, Q, and R of mass is 0.6 kilograms, 0.4 kilograms, 0.8 kilograms. They are at rest. P is projected directly towards Q with speed 3 meters per second. Find the speed of Q after collision. That's simple conservation of momentum. Then it says in the subsequent collision, Q and R, they coalesce. Speed of the combined particle, again, use conservation of momentum. That's straightforward. The next part says, find the time that it takes from when P is initially projected. So P was projected in the very beginning. From that point until the instant at which P collides with the combined particle. Okay, now what does that mean? There are multiple collisions that are happening. First of all, P and Q collide with each other. And that gives us the velocity of Q after collision. Then Q and R collide with each other. And we have this combined particle, we have its velocity. And now they're saying the particle P that was still moving from before and that combined particle, they collide. Find the time that this whole thing takes. How do you do that? First of all, we would have to break this journey down. Initially, P was projected at 3 meters per second, right? How much time does P take to collide with Q, first of all? That distance was 1.5 meters. That distance was 3 meters. So we can find the time taken for this first part of the journey. Time taken for this first part of the journey. It's a smooth surface. We can just use distance equals speed over time, or time equals distance over speed. Time until first collision, that's 3 over 3. That's 1 second. That's the time taken until first collision. Then what happens is Q and R collide. Now, how much time do they take? Q was moving at 2.25 meters per second after that collision. Distance is 3 meters. How much time does that collision take? 3 over 2.25, that's 4 over 3. That's the time until second collision, between first and second collision. Now, while Q was traveling to the right, P was still moving. P was still moving at some speed. What speed was it moving at? It was moving at 1.5 meters per second after that first collision. So in this time, P has already traveled some distance as well to the right side. How much distance has P traveled to the right already before the second collision happened? 1.5 was the speed into time, speed into time. That's the distance traveled by P. 2 meters. What that means is the total distance between Q and R, that was 3 meters. When Q hit R, P has already traveled a distance of 2 meters as well. So P is now at this point such that the distance between P and that combined particle, that is 1 meter. Distance between P and the combined particle, that is 1 meter. What happens now? After that second collision, now how much more time does it take? Time taken between the second and third collision now. P is moving at 1.5. C is moving at 0.75. What's the distance between the particles? 1 meter. What's the relative speed that we get from this? Both of them are moving at the same speed. We discussed this in kinematics. What's the relative speed going to be? 1.5 minus 0.75. That's the speed at which the distance between the particles is being covered, 0.75 meters per second. The distance is 1. Distance over speed, that gives us the time taken after the second collision. And then the total time turns out to be 1 plus 4 over 3 plus 4 over 3. And that's this. Okay. Now, the important point here is when you have multiple collisions like this, do not forget that the particle that was already moving while the other particles were colliding, that first particle will still keep moving. So we also have to consider how much distance that might have traveled already while the second collision was happening. Okay, so we have to consider that P had already traveled 2 meters here. And then this concept of relative speed that we discussed in kinematics. Okay, let's have a look at another example. Okay, just give me a second. Okay, let's have a look at this now. It says a particle A is projected vertically upward from a point O with a speed of 80 meters per second. 1 second later, a second particle B with the same mass as A is projected vertically upwards with a speed of 100 meters per second at time t seconds. The two particles collide and coalesce to form particle C, so that t is equal to 3.5. Now again, remember kinematics. In kinematics, we discussed what we do with time delay problems. B was projected later. B was projected later. We are considering the time for the first particle by t. So time for A is t. Then for the second particle that was projected later, its time is going to be considered as t minus 1. The particle that starts late, its time it takes less time if it reaches the endpoint at the same time instant. Okay, now we just use that. We have to find the value of t when they are at the same height. So we have information about their initial velocities, acceleration, and time. Initial velocity, acceleration, and time. We equate their displacements and we find that value. That's a simple kinematics problem. Now, if you've done enough practice, that's coming from there. But then it says, find the height above O at which the particles collide. Okay. Now, what's the height there? We can just find SA in this or SP. Any of them will work. B and A, both of them were on ground. And then they collide at this point X. I've just represented them separately on right and left, so just to make it easier to understand, but they're in the same vertical line. So at point X, they're colliding. So SB or SA, that's the height at which they collide. So you can either find SA or SB, and that will be the height at which they collide. This is the important part now. That involves both kinematics and momentum now. Find the time from A being projected until C returns to O. What does that mean? A was projected. And what's happening was, yeah, they coalesced to become particle C. All right. So what happens is A and B both were projected. A was projected initially, B was projected 1 second later. Then they collide with each other here. And then what happens is the combined particle is going to reach the ground. Very similar to the earlier problem that we discussed earlier when there was particle C. So what you do is, first of all, you consider the final velocities just before collision. You will need them for applying conservation of momentum, right? What are their velocities at the point X? So you find those velocities. We've got all the information that we've got here. We have the value for time as well now. We use V equals U plus AT to find both of their velocities. Okay. Now, these are the velocities just before collision, 45 meters per second and 75 meters per second. We apply conservation of momentum, and that gives us the velocity of the combined particle just after collision. The masses were given in terms of m, so we just use that in terms of m, like this. Masses were m for both of them, so the total mass becomes 2 times m for the combined particle. Momentum before collision and the momentum after collision, they're going to be equal to each other. We use that to find the velocity of the combined particle. That's 60 meters per second. So now we've got the initial velocity, we've got the acceleration, and then we have to figure out at what height they started from. We found that in the previous part already, 218.75. However, since we are taking upwards positive for kinematics now, u is equal to 60. Initial velocity was positive, it was in the upwards direction. Acceleration is minus 10. Displacement is also going to be negative in this case because the particle is eventually going downwards from the starting point. So displacement is minus 218.75. Use constant acceleration formulas, find the value of t from that. That turns out to be 14.93. It had already taken 3.5 seconds earlier before collision. So it takes this much more, and the final result turns out to be 18.4 seconds. All right. So that's what can happen as well. Okay, now for the last two questions, these are quite complicated. I'm not sure how to go through them very quickly. So what I'll do is I'm just going to scroll down a little, go through them. You can have a look at the solution and look at the working, the detailed working for that, and the other video that I'll post. But these are good questions to just go through them. This is probably as complicated as it can get sometimes. Have a look at this. Again, in this case as well, we have to use the concept of relative speed. Finding the time between collisions. And this again, you've got kinematics in one part. So this that particle P coming down up to Q, and then they are colliding. After that collision, then they're moving down a certain distance. So you again have to use kinematics. You have to use kinematics for one part, then use momentum to find the velocities after collision, and then the time that it takes after collision for the combined particle to reach some point. So that's a lot of working. I will share the solution with you. You have this in the notes, and I'll share that video with you, in which you can find the detailed video, detailed solution for this. Yes, I will include this. All of these questions, I will include their solutions in that video, inshallah. All right. So that's it for today. That's it on momentum. I hope that was helpful. If you have any quick questions, you can let me know. Otherwise, that is it. I hope this workshop was helpful, although the time that it took was way more than I was expecting. So this is it. If you have any questions, let me know. Any feedback, any suggestions for the next ones.